Welcome to the C Programming for Beginners course. My name is Kevin Brown, and in this course we'll be going over how to write programs in the C programming language. C is a great language to learn because it's a very old language that most newer languages actually trace their ancestry back to. C is kind of like the great-grandpa of languages like Python and Java. C is still very widely used as a systems programming language to write compilers and operating systems, as well as a programming language for embedded systems. In this course, we'll be covering introductory concepts like variables and if statements, all the way to more advanced concepts like pointers, dynamic memory allocation, and structs. If you do like the course, please subscribe to our YouTube channel, where we post regular videos on C programming and many other topics. And check out our website, portfoliocourses.com, where we host paid courses to help you create projects for your developer portfolio that will impress employers. So let's start off with, why do we use C at all? Why do we use a programming language like C in general? So ultimately what we want to do is write programs that tell our computer what to do. Maybe it's calculate our taxes, maybe it's a video game, but it's some kind of program that tells our computer to do something. Now our computer works by executing what's called machine code. Machine code is very, very low-level instructions made up of zeros and ones that represent things like add these two numbers together, multiply these two numbers together. And that machine code is very difficult for humans to read and understand. So when we go to write computer programs, what we prefer to do is write them in high-level languages, like the source code on the left. That's a basic C program there. Now, even if you don't know anything about C programming, just by looking at it, you might be able to guess what's going on. Because we have that printf, hello world, you might guess this is going to print hello world to the screen without even knowing anything about C programming. Whereas we can't really say the same about the code on the right. So the code on the left is going to be far easier for us to understand and maintain and write than if we try to do it with the code on the right. So that's the primary reason why we bother with high-level languages like C. They make us more efficient as programmers. So as C programmers, we're going to write text files made up of what's called source code, as on the left-hand side, and we're going to use what's called a compiler to compile them into executable programs, actual programs we can run on our computer. So the first thing we need to figure out is how are we going to write these source code text files, and then how do we compile them into these executable programs made up of machine code that we could then run and interact with. So because this course is for complete beginners at C, what I really suggest you do is go to Google and just type in online C compiler. Because nowadays, there's a bunch of really great online integrated development environments. And by integrated development environment, we mean an environment where you have a text editor and the ability to compile and run the program all in one place. And one that I really like is called Tutorials Point. All of these are actually pretty good, but the one I like is called Tutorials Point. You'll find they're pretty similar, so I'll show you one of them. This one here gives you the source code on the left-hand side, and then you can compile and run the code by clicking execute here. So this program here prints hello world to the screen. We're going to write a program like this together really soon, and we'll explain it step by step. But if I go to execute, what's going to happen is this source code is going to get compiled, and we're going to see the result on the right-hand side. So I click execute, and we get hello world here. And that's the result of our program running. This here, this GCC and this main here, that's actually the compilation of our program occurring, and this is our program running. So the IDE kind of does everything for us, and we can even save our files so we can get to them later. So it's a pretty good way to go if you're really just starting up. Now, the other thing with these IDEs is they also allow you to see compilation errors. So if we ever write our C program incorrectly, if we have what's called a compilation error, the compiler is going to let us know about that. So one of the things we have to do in C is we have to end most of the lines of code we write with a semicolon. If I take out that semicolon, I'm going to have what's called a compilation error. And a compilation error occurs when we don't follow the exact rules of the C language. At that point, the compiler can't figure out how to turn our source code into machine code. And so it'll actually output an error that tries to help us figure out what we did wrong. So we can click on execute here. And now we'll see this error here where it says error expected semicolon before return 0. And it's basically trying to indicate to us where, in terms of the line number, the error is approximately taking place. And it's also telling us what the error is. So expected semicolon. Now, sometimes these compilation errors are going to be very helpful. Sometimes they're going to be very difficult to interpret, but it's important that we're able to see and understand these compilation errors. And you get that with this sort of IDE as well. So that's why I really recommend, if you're a total beginner, perhaps just go with one of these online editors. There are many, many different options for writing and compiling C programs, depending on the operating system you're using. So if you're on Windows, you might want to look into using Visual Studio. If you're on a Mac, you might want to use Xcode, specifically the Xcode command line tools. If you're on a Linux machine, it very likely comes with what's called the GCC compiler. The GCC compiler is pretty much the most standard C compiler there is. This tool here is actually using it. You can actually see it here where it says GCC. That's the GCC compiler. So it really depends on the platform you're on. In order to keep this video focused on actual C programming, I'm going to leave it here and just assume that you're either going to use this tool or that you're going to figure out something for your own local environment. Because I'm on a Mac, I actually did install the Xcode command line tools, and that lets me use the GCC compiler from my terminal like this. And I installed Visual Studio Code. That's my favorite text editor. When I write C code with Visual Studio Code, it's going to highlight important words for me in order to make the code easier to understand. You'll find that online IDEs will do pretty much the same thing. So let's actually write our first C program now. And I'm going to zoom in and zoom out on the source code depending on the size of it. So I'm going to say here, $ include, then I'm going to say stdio.h. So what this line is doing is it's telling the compiler to go get this library and use it as part of our program, because we're going to access the functionalities inside of it. Now, stdio, that stands for standard input output. So the functionalities in this library allow us to output things and input things. That's why it's called standard input output. Now, if we include this statement here, we're going to have access to those functionalities. If we don't, we're not. The standard input output library comes with C, so you're always going to have access to it. You can always say $ include stdio.h and get access to it. So next up, we're going to say int main void. Then we're going to say open squiggly bracket and close squiggly bracket. And you'll notice that the text editor actually filled in that close squiggly bracket for me. That's another benefit you get with using a text editor, is it does things like that for you that just make writing your code easier. So this is what's called the main function. And the main function is where the execution of our C program is going to begin. It's going to turn out that our C programs are largely going to be made up of functions that we're going to create and define and use. And the main function is the important function because that's where execution starts. Now, the first thing we're going to do is we're going to say here printf, and then we're going to say hello world. And I'm going to say /n here, and then I'm going to put a semicolon here. So what I'm doing is I'm using this printf function that's going to print hello world to the terminal. Now this printf function is something the compiler is actually going to get for us from this stdio.h library that we're including here. That's why it was important to include it. Now to actually compile and run this program, we're going to say gcc-o.dd.c. Now if you're using an online editor, you don't have to worry about this. But what this is basically saying is run the compiler and compile the file d.c, which is what I saved this file here as. And then this -od means produce an executable file called d. So I can run this here, and then I can run the executable file that's been created with /d, and I get hello world here. And we output hello world to the screen. Now this is the standard first computer program to write. So as you learn languages, you're going to find that hello world is kind of like the de facto standard thing to print to the screen first, just to show that you can run a basic program. So there's a lot here though that we don't really understand yet. Like, what does this mean that we're running the function printf? What is this return 0 here doing? What is hello world? Why is it in these quotes here like that? These are all questions we're going to have to answer one at a time here. So first off, printf here, that is a statement. And statements in C are a line of code that does some work for us. And statements are ended with a semicolon. And you can kind of think of a semicolon as like the period at the end of a sentence in English, in the sense that it denotes the end of the statement, the end of that line of code. And we have to have a semicolon. If we don't, we're going to have an error. So we could try to compile the program now. I've just saved it. We could try to compile it without the semicolon, and we're gonna get the compilation error again that we saw before. It says error expected semicolon after expression, one error generated. And it's basically trying to tell us that you have an error here. It's kind of outlining, it's trying to outline for us like, hey, put a semicolon here, buddy. And so we could do that and save it. And then we could recompile it. And now it's going to compile okay. We didn't get any errors that time. And if we ran it, we're going to get hello world again. I could say clear here to clear the screen, and that's okay. If you're using an online editor, you don't even have to worry about that. But that's what we're doing here is we're writing statements of code. And the way that C works is it's going to run one statement at a time, one after the other, in the order that they're found in the main function, unless there is some kind of control structure, which is a way of modifying which statements get executed and how many times statements get executed. So we're going to say here printf, and I'm going to say line 2, exclamation mark /n. Then I'm going to say printf, I'm going to say line 3, exclamation mark /n semicolon. And now I've got 3 statements here. And what's going to happen is they're going to execute in order. So we're first going to execute the first printf. It's going to say hello world. Then we're going to do line 2. Then we're going to do line 3. And we're going to find that if we compile this and we run it, we get hello world, then line 2, then line 3. And that's because statements in C are going to execute in order from the top of the main function on down. So we said that printf is a function and that main is a function. What does that mean to be a function? We'll get into it quite a bit later in terms of defining and using functions. But for now, let's think of it like this. In math, we have functions, right? We have like f at x is equal to x plus 2. And this means that f with 2 is equal to 2 plus 2, which is equal to 4. And we could have a function like this, g xy is equal to x times y. And if we gave g 2 and 3, it would be equal to 2 times 3, which is equal to 6. And these would be mathematical functions that accept some numbers and produce some value based on the numbers they're given. In C, we have a bit of a similar concept. It's not exactly the same, but it's a little bit similar. What we're doing here is we're giving printf the value hello world, and we call this an argument. And we say that we're passing the argument hello world to printf. And what printf does is it actually outputs to the screen then hello world. It outputs to the terminal hello world. And that's what printf does. That's the work it does. And we typically use functions like this that carry out some functionality for us. And we're eventually going to define our own functions that carry out some functionality we've defined. Now this argument here, hello world, this is what's called a string in C. And a string is basically a sequence of characters. And so the quote here is denoting the beginning of the string. The quote here is denoting the end of the string. Now the reason why I have this /n here is that /n is a special character. It's actually one character, even though it's 2 characters in the editor here. It's actually going to be interpreted by printf as one character, a special character called the new line character. And when printf sees that character, it's going to output onto a new line. And so if we did something where we didn't have a new line, it's going to look kind of weird. So let's say I took out the new line here. I'll take out the new line on that line 2 there. What's going to happen is that printf is no longer going to output a new line. And so line 3 is actually going to start right here where line 2 ends. So if I do a recompile here and then I run it, I get hello world, and then I get line 2, and then just line 3 immediately afterwards. So you're going to see me use the new line character just to make the output format nicer in the terminal here when it gets output. One thing I should mention is that this open squiggly bracket here and this closed squiggly bracket here, they basically denote the beginning and end of our main function body. So all the statements of our main function, they need to be defined in here. They need to be enclosed in this block it's called. If I were to take a printf and try to use it outside of that block defined by the open and closed squiggly bracket, the compiler is not going to like that very much. So I'll save this here and we'll try to compile it here, and we're going to get all kinds of errors. The compiler does not like that one bit. So we just can't do that. So we have to put all of our statements for now inside of this open squiggly and closed squiggly bracket. Now I'm actually going to leave the rest of the discussion about what this means and what this return means for when we actually talk about how to define and use our own functions, because it'll make more sense at that point. For now, let's just focus on writing code inside the main function here, and we'll get to those things later. One thing you might wonder about is why is printf and return kind of shifted over to the right like this, where there's 2 spaces and then printf, and then 2 spaces and then return. Is there any reason for that? There isn't really a technical reason for that. If I were to move things over and then try to recompile it, it'll actually work okay. So I could save this and then we could recompile it and it works just fine. I can do other things as well. I can also kind of move this squiggly bracket up here and save it. And I could do a recompilation and run it. And again, it'll work fine. So the reason why we do that is because it makes our code more readable. When we space things over like this, it's going to make it more clear to the reader that these statements here are part of this main function body here. So that's really the only reason for it. And you could use spaces or you could use a tab. It's really up to you. Developers sometimes like to argue and have fun about that, about which one is better than the other, but it's really up to you. Just pick one and stick with it though. C also allows us to add what are called comments to our code. And comments are annotations that are aimed at the reader of the code, not the compiler. So we could say here // and I could say print 3 lines. And this is a comment describing what's going on in the code. And the compiler won't even consider this. Now we could try to recompile the program and it'll work just fine. And that comment here has no effect on our program's execution. It's actually intended for the reader of the code to help them understand what's going on in the code. And this here is called a single line comment. We say // and everything for the rest of this line here will be considered a comment. We could put a single line comment at the end of a statement. So we could say here like // and we could say like line 2, and this is a valid comment as well. There's also what's called a multi-line comment, and you might see these at the top of a file especially, where we could say here like /* and then // and everything between this /* and this // will be considered a comment. So it's all considered a comment. And you could see stuff like this where it says like author, like Kevin Brown, and we could say like program, hello world, and we could describe the program maybe. We could have a description, this program prints hello world to the screen. And you might see comments like this at the top of source code files, just kind of describing what's going on in the program in general. And that's a multi-line comment there in contrast to a single line comment. So next up, let's write a C program that does some processing, that actually produces some result. We're going to find that many programs follow an input, processing, output model, where the program starts off with some input, maybe like a speed and a time traveled. And then the program does some processing, like calculating the distance traveled, given the speed and the time. And then the program does some output. So it outputs to the screen maybe the distance traveled, given that time and that speed. And we call that the IPO model. So if our program is going to work with pieces of information like speed and distance and time, we're going to need somewhere to store that data and represent that data. And that's where variables come in. They allow us to store pieces of data. And we declare variables like this. We say int speed, for example. And what this does is it declares a variable called speed. And the int here means that the variable is going to store integer values. So what this does is it basically goes out and creates a spot in memory, in the computer's memory, where speed is going to be stored. And it's kind of like we've got this box in memory where we could then store speeds like 5 or 10 or something like that. And we can think of them like a box in memory that stores a chunk of information. And they have a type. So in this case, the box is going to store integers. So integer values are whole numbers like 50 or 10 or 3. They can also be really large numbers like 12,000 or something like that. They can also be negative numbers. So it could be like negative 45, and it could also be 0. These would be integers. Something that's not an integer would be something like 50.55. That would be what's called a real number. And there's other types we could use to represent that kind of number in C. But once we've declared a variable, we can assign values to it. So I could say here, int speed is equal to, and I'm going to say 20. And maybe that's a speed of 20 kilometers an hour. And what I've done is I've then initialized this variable. So I initialized the variable to the value of 20. And it's like we've now stored the value 20 in that box there. So we can make more than one variable. I could say here int time is equal to 7. And we could say that this stands for 7 hours. And what we're going to try to figure out is what's the distance we could travel at a speed of 20 kilometers an hour for 7 hours. And when I do this, int time is equal to 7, I'm declaring and initializing another variable. So it's like another box has been created in memory, this time for storing time, and we're going to store the value 7 in there initially. And now we've got another variable that's storing time. We could also create a variable for distance, and we could actually use speed and time in what's called an expression to actually calculate the distance. So we're going to say here, int distance is equal to speed times time. So here we've declared a variable called distance, but this time we're not initializing it to a value like this. We're initializing it to this expression here that's going to take these two variables and multiply them together. And this here we call an operator. That's the multiplication operator. So it's going to multiply these two values together. And we're going to get 20 times 7, which is going to be 140. So we know that distance is going to be initialized to 140. And we could say that's another box in memory that's storing another value that our program is going to be using. And so far here we have the input set up. We've got input of speed and time. We now have some processing in terms of speed times time giving us the distance. And so the last thing we want to do is the output, which is output the result of our program. And let's see what we actually get for the distance. So to do that, we can use printf to output. But how are we going to output what distance is? We might think we could do something like this, like printf distance, but unfortunately it doesn't work that easy in C. In C, we're going to have to use what are called placeholders inside the string that we give as an argument to printf. So we're going to say this, we're going to say dist : %d/n. So dist is just a string, it's just characters that stand for distance really. I'm just using that as a way to describe the data I'm about to output. And then this %d, that's what's called a placeholder. And what it's telling printf is I'm going to give you another argument, and that argument is going to be an int value. And I want you to put that int value right here in the string when you output it. And then the /n again means output the data on a new line. So then I can put distance here, and this is what is going to fill in this placeholder here. It's going to be the value that printf is going to use in this string here. So we can save this now, and we'll just clear this, and we'll do a recompile and run it. And we get a distance of 140. And we've effectively created our first sort of quote unquote useful program where we've got some input to the program, we have some processing going on, and we have some output as well. So one of the things that makes computer programs so powerful is that we can change the inputs and get different outputs without having to do something like rewrite the entire program. So I could say here, let's change speed to 15 and let's change time to 9. So now we're going to figure out how far we can go at 15 kilometers an hour if we go for 9 hours, say. And then we can do a recompile of the program here and run it, and we get a different result. We get a distance of 135 here now. And so that's really what makes computer programs very, very powerful tools to use. Because you can imagine that our program is doing a whole bunch of very complex calculations here, and we're having to just give it different input, and we're able to get back different outputs. Now, unfortunately, with the approach we're taking here, we have to recompile the program every time we want to calculate a new result. So if I want to now change, speed to 12 and time to 22, I again have to recompile the program. I have to do a recompile. I have to run it again to get a different result. This isn't going to be very effective over the long term because I have to keep on recompiling the program. What would be nice is if I could run the program and then just give it the input as the user, just sort of type in the input and then have it actually produce the different outputs for those different inputs each time. So to do that, we're going to have to use a tool called scanf. And scanf is another function that comes in the stdio.h library. And scanf allows us to read in user input. There are other methods besides scanf for reading in user input, but if we're just starting off, scanf is one of the easier ones to learn. So what I'm going to do now is instead of initializing speed to 12 and time to 22, I'm going to initialize them both to 0. And then I'm going to use scanf to actually read in speed and time values. So it's going to look like this. I'm going to say here, printf, and I'll say speed, then I'm going to say scanf %d, and speed. So what I'm going to do is I'm going to ask the user to enter in his speed. Then I'm going to say scanf, and scanf works a little bit like printf, but kind of backwards. So scanf, we're giving a placeholder here, and we're saying expect an integer value to be input from the user. And then this here is where we're going to store it. And this AND operator, we'll explain that more later, but the AND operator is basically telling scanf, I want you to store it in this variable here. So we have to have that AND there. That's actually key to having scanf store the value the user enters into that variable there. And then what I'll do is the same thing, but for time. So we'll say here, printf time, then I'm gonna say scanf %d and time. And what we're doing now is we're gonna have the user enter in a time. So we're saying enter a time basically, and then scanf %d means accept an integer as input, and this means store it into the time variable. And so now what's going to happen is our program doesn't need to be recompiled. We can actually just ask the user for the speed and time each time. So we'll have to recompile it one more time, and we run it here. And now let's say I put in a speed of 15 and a time of 9. I get a distance of 135. Now let's say I put in a speed of 12 and a time of 22. I get a distance of 264. And I'm not having to recompile my program anymore. I can just run it however I want. So I could say like speed 20, time is 7. I can just put whatever user input values I want as the user. And so now we really have a true input processing output program. It's a simple program, but we're going to find that a lot of programs we write follow this model more or less. One thing you might be wondering about is why did we bother to initialize speed to 0 and time to 0 if we were just going to set them using scanf anyways? Like if we're just going to use scanf to set them, why do we bother setting them to 0? Why don't we just do this? So the reason why we still initialize them to something is the way that C behaves. So when variables are uninitialized in C, when there's nothing actually setting them to some initial value, there's actually no defined behavior there. You might think that they're automatically going to be set to 0 or something like that because they're maybe like blank values, but that's not the way it works in C. In C, whatever is in memory, in that place in memory that's been set aside for the variable, at the time the variable is declared, that's actually what would be the variable's initial value. So there could be some garbage data in memory like 55 or something like that. And maybe if we just didn't initialize speed, then speed is actually going to have the initial value of 55 because that piece of data, that chunk of information, just happens to be in memory in the spot that was set aside for speed when we declared the variable speed. So that's actually why it's important in C that we actually initialize our values to something, because otherwise our program can end up with bugs that are really hard to figure out because we think our variable is initialized to 0 and really it's some garbage value, and our program ends up using it thinking it's the wrong value, and it ends up being a really, really challenging thing to debug. So always as a practice, initialize your variables to something. So now we can make different types of variables besides integers. So I'm just going to delete this here, and I'll just kind of start over again here. So two of the other types we can make are doubles and floats, and they look like this. I could say float x is equal to 5.2, and float is short for floating point value. And floats basically allow us to store real numbers. In other words, numbers with decimal points. So we can store numbers like 5.2 or like 25.444 or 44445 or something like, negative 91.25. 0 is also a float as well. And that's the big difference, is that floating point numbers can have the decimal point. And oftentimes we need to work with data that has decimal points. A double is very similar. So we could actually say here double, and we could say y. So double y is equal to, and we could say here negative 9.8. And so a double also stores real numbers. So a double also allows us to store numbers with decimal points. The difference with a double is that it can store numbers with a higher level of precision. So we can actually store numbers with more accuracy. In other words, we can effectively store numbers with more decimal points, also with a greater range. So all these variables here like float and double and int, they have particular ranges of values they're allowed to store. A double can also store numbers with a higher range. For the most part, that's really not going to come up when you're working with introductory programming. It can come up though, say, if you're doing something like video games or scientific computing, where you're doing maybe a lot of generation of graphics, or something like astronomy, where you're doing really, really accurate calculations with large numbers. But the difference between double and float doesn't really come up much when you're writing introductory computer programs. They don't really get into that kind of heavy mathematical work. If we want to use scanf and printf with floats and doubles, it looks pretty similar. So we could say here printf, and we could say x to enter x. And then we could say scanf, and we're going to say here %f, and then and x. And we're basically saying store a floating point value into the variable x. And that's why we have to have that and there. We're telling it to store it into this variable here. And then we could print the float. So we could say printf, and we could say x, and we'll say %f, and then x. And this is just a different placeholder. It's just telling printf that we're going to give you a floating point value as an argument, and we want you to put that value here. And so we could then clear this, and we'll just add a new line here. Just that way it formats a bit nicer. And we're going to say here gcc-out d.c to compile it, and we'll run it now. And it asks us for a floating point value. So we could say here like 5.2, and we then output 5.2. Notice how it's formatted. We get this 5.2000000. That's because it's a floating point value. And there's an expectation there's going to be decimal digits associated with that value. We can actually use some modifiers here to actually modify how this value gets output, but we'll leave that for later. So if we run this again and I put in something like negative 52.245, look what I get here. I get as output negative 52.244999. It's a number that's really close to 52.245, but it's not 52.245 exactly. And that's just interesting because you think that like it would store exactly this number, but with floating point values and double values, just so you know, the precise exact value is not always stored. It's sometimes a number that's actually very close to that value. Often that's actually the case. And it's just because of the way that computers store data. It would be sort of long-winded to really get into it, but computers store data as zeros and ones. And so it uses a system involving fractions that actually allows us to approximate real numbers that have like a decimal digit to them. And it's able to store numbers more efficiently by doing so. And that sort of system it uses to store numbers in an efficient way, it doesn't allow for numbers to be stored in a completely accurate way. It allows them to be stored in a very accurate way, but not in a completely accurate way. And so that's just an interesting quirk that you got to be aware of. Now, with doubles, we could also do printf and scanf as well. So we could say here, printf will say y, semicolon. Then I'm going to say scanf, and I'm going to say here %lf. And then we're going to say and y. And this is basically the placeholder we're going to use for scanf to store a double into this variable here, y. And we could printf y as well. So we could say printf, and we could say y colon. Now you could say %lf, and most C compilers nowadays will support this and be okay with that. But you can also just say %f, and it'll actually have the exact same effect. So %f will actually work fine. And we could say here y, and then we could print out y. So we could recompile the program, run it again, and I'm just going to actually throw in my new line there, just that way things format a bit nicer. And then I'll do another recompile here and run it here. And so it says x, and I'll say 20.2, and I get this number here that's very close to 20.2. And then I'll say here for y, maybe negative 10.88, and I get negative 10.88. And we're now using floating point values and double values, which allow us to work with these sorts of numbers that have decimal digits associated with them. Now, there are other types of variables as well. So there is the char type. So we could say here char, and I could say C, and then I could say that this is equal to, let's say, a D. Now, this here is a character. And so characters can be things like letters, they can be things like numbers, they can be punctuation marks, all kinds of things. And the characters we're going to create with the single quotes. So it's got to be single quotes and not the double quotes. Double quotes is for strings. And characters actually fundamentally are integer values. And what there is there's a character representation for that integer value. And so we can actually go to Google here and we'll figure out which characters are associated with which numbers by Googling ASCII table. So ASCII is the mapping of characters to numbers. And you can find these ASCII tables online that kind of show you the mapping here. So for example, if we scroll down here, the letter D, the capital letter D, that character, that is actually the number 68. And the number, say, 100, that's actually the lowercase letter d, and so on. And this is basically just because really all the information on our computer is ultimately zeros and ones like this, which are ultimately representing integer numbers like this. And those numbers then in turn represent characters. But ultimately your file, your actual file, your code file, every kind of data on a computer is ultimately boiling down to zeros and ones, right? So that's why we have to have this mapping of those numbers to characters for our computer to be able to represent them, because that is how our computer represents information. So with characters, we can also use scanf and printf with these as well. So we could say here like printf C, and then we'll say scanf, and we'll say %C. So C is going to be the placeholder to store a character here. And we're going to say and C to store the character that's entered into this character variable here. And then we'll say printf, and I could say here, let's printf C, and I'll say %C here, and we're going to print out the character. And so %C is the placeholder we're going to use for characters basically. So we'll clear this, we'll do a recompile, and we run it. So for the character, we'll put in the character D, and we get C is D here. Now, interestingly, because characters are really just int values, what I could also do is this. I'm going to say here printf, and I'm going to say C again, but this time here, instead of %C, I'm going to say %D. Now, %D is the placeholder that we normally use to print out an int value. But because C is fundamentally an int value, it's going to turn out this is going to work. We're actually going to print out the int value for C. And so we'll recompile this and run it, and I'll put in D again, and we get CD there. Oh, I didn't save it here. Got to save it here before you compile it. So recompile it, run it, put in D, and I get C:D, and I get C:100 there. And what's happening is that I'm printing out the char value here, the character value here, as an integer. And so what I get is actually the integer for that character, which was 100. If you remember, we actually said that the lowercase letter d is actually the character, is actually the int value 100. And just be aware of that with characters, that really fundamentally under the surface, they are int values. Now, one thing you may have noticed is that we're using these sort of specific values like this. Like I'm saying like the car C is equal to this value specifically to initialize them. For ints, I had stuff like this. I had like int, and I said speed is equal to 10. And for doubles, I had things like this. I said double x is equal to 5.5, and float y is equal to -2.5. So things like the car D and 10 and 5.5 and -2.5, we can call these literal values. So these are literal values. And we can use literal values to initialize variables, or we can use them as part of expressions that compute some kind of value. Now with variables, we can actually initialize multiple variables and declare multiple variables on a single line. So I could say double x is equal to, we'll say 5.2, and then I'll say y is equal to 2.5 with a comma separating them here. And what this allows us to do is create two double variables, x and y, with x set to 5.2 and y set to 2.5. There's all kinds of operators we can use with these different variable types. So we could say here, we'll say double mult is equal to, and I'm going to say x times y. And that's multiplication, which we've seen before. We could also say double add is equal to x plus y, and that's going to add x and y together. Then I could say here double, and I'll say div, and I'll say x divided by y, double sub, and I'll say x minus y. And these are some of the common operators that you'll see in C programming, and they're just sort of our classic multiplication, addition, division, and subtraction operations. So I could say printf, and let's printf these results here. So I'll say multiplication, %f/n, let's print out the result of multiplication. I could say printf, and I could say here add %f, and I could say let's print out the result of the addition, and we'll do the same thing for division and subtraction. So I'll say %f, let's print out the result of division, and we'll say printf, and I'll say subtraction, %f, and we'll print out the result of doing the subtraction. And we could then clear here and we'll do a compilation and run it. And we get multiplication is 13. That seems about right. Add is 7.7. Division is 2.08 and subtraction is 2.7. And so we're getting the expected results there. Now there are other operations as well. One operation that is relevant for integer values is called modulus. And so modulus works like this. We're going to say here int, and I'm going to say, let's say x is equal to 11. Then I'm going to say here y is equal to 3. So we can do all the usual operations with integers. So we could say like int div is equal to x divided by y. And what's going to happen here is what's called integer division. So it's going to take x and divide it by y. But what it's going to return back is how many times does 3 go into 11? And it goes into it 3 times, right? So the result would be 3 when we output the result of doing the division here, because it does integer division, it's called. So if we do a recompilation here and run it, we get back that the division operator produces the value 3 because 3 goes into 11 3 times. Now the modulus operator actually returns the remainder of division. So I could say here int mod is equal to x modulus, and we're going to say y. And what this is going to return is the remainder of x divided by y, the remainder of 11 divided by 3. And the remainder is going to be 2, right? Because yes, 3 goes into 11 3 times, but you've got 2 left over, so you have 2 remainder. So the result of the mod operator in this case should be 2. And that's the modulus operator. And we can actually use that in some, and you see the result here, the mod operator produces the value 2. And the mod operator is actually useful for different things like determining whether a number is even or not. So let's do an example of that actually. We'll say here int x is equal to 11. And now I'm going to say here int mod is equal to x modulus 2. So here I'm using the modulus operator again, and I'm using it with one of these literal values. So I can use literal values like this in my expressions, and that's totally fine. And what we're going to find is that the modulus of x modulus 2 is going to be 0 if x is even and 1 if it's odd. So x is odd, so we're going to find that mod is going to be 1. So if we do a printf of mod here and we do an output of it, and we'll just clear the screen here and recompile here, we're going to find that we get 1. If x was even, let's say because it's 14, then we're going to find that x modulus 2 is going to be 0. And so we can actually use the modulus operator to determine if a number is even or odd. And that can actually be pretty helpful in our program to let us work with different numbers in different ways. And that actually brings up our next topic, which is control structures. So oftentimes we want our program to handle different numbers in different ways. We want our program to behave differently based on the input it's given or based on the data that it's working with. So maybe the program outputs that a student passes, maybe the program outputs that a student fails, but that's going to depend on the grade of the student. So for an example of our first control structure, I'm just going to kind of delete this stuff up here and we'll just start working up here again. I'm going to say here int grade is equal to 0. And so we're going to have a student grade, and we're going to actually ask the user to enter the student grade. So we're going to say here printf, and we'll say grade, and then we'll say scanf, and we'll store the grade that's entered into this grade variable here. And we're going to have a control structure that's going to do something or not do something depending on the value of grade. So we're going to say here if grade is greater than or equal to 50, we're going to say printf pass. So what's going to happen is if I enter a grade that is greater than or equal to 50, we're going to printf pass. Otherwise, the program is going to do nothing. So we have this thing here that the program is going to optionally do. Now we can do a recompile here. So I'll say clear, then I'll say gcc-out d.c, and I'll run it, and I get grade here, and I'll put in 70, and I get pass. I can put in 50, and I get pass. But if I put in 49, I get nothing. Nothing happens. And this control structure, it's altering the flow of our program. Because what we said was that our program is going to execute statements one at a time, right? It's going to execute this statement, then this statement, then this statement, and then this statement. But this statement here is doing something special. It's not doing this printf here. It's not outputting this unless this is true, unless this condition here is true. And this is what we call a control structure because it sort of modifies the flow of execution of our program. And we can potentially have different branches of execution even. So we could actually put this printf here. We could say printf if the grade is greater than or equal to 50, and we have the printf here. This will also be acceptable so long as we've only got one statement here. And so we could say here GCC, compile it again, we run it, we can put in a grade of 51 and we get pass. And so this is an okay format as well. Now, if we want to have multiple statements run in response to this condition being true, then what we're going to do is we're going to say open squiggly bracket and close squiggly bracket, and we're going to enclose those statements inside of this block here. We call this a block, and we would enclose those statements inside of this block. So we could say printf pass, and we could also say printf, and we could say congrats, and then /n, and now we're going to printf two things, and we're going to have two things execute in response to this condition being true here. So let's try this now. We'll recompile here, we'll run it here, we can say 67, and we get pass and congrats printed out. Now, we said condition multiple times here. What does condition mean? So condition is something that is going to be true or false. And this here, this greater than or equal to, that's another operator. And this is what's called a relational operator because it's relating this value here to this value here. And it's going to work with the value of grade, right? So whatever we entered for grade, it's working with that value. And it's checking like, is that value greater than or equal to this value? And if it is, then this is going to be true. And we're going to do whatever is in this block here. If it's false, then what's going to happen is execution is going to jump down here below the if statement. And we could say printf, we could say here if statement done, or we can just say like if done. And what's going to happen is if this is not true, control flow, execution of statements basically, is going to jump down here and we're going to printf if done. So we could do clear, recompile and run it. And I put in, say, 44. We get to if done. This block never executes. Control flow execution jumps down here. If we did put in a grade that was greater than 50, we get pass congrats, then we get if done. And so what's happening is control flow would jump into here because this condition is true in that case because 52 is greater than or equal to 50. We do these prints. And then again, control flow would continue down here below the if statement block here. And so that's a basic if statement in C. Now there's actually variants on the if statement that extend what it can do. So there's something called an if-else statement. And the if-else statement allows us to add a block that's going to handle the case that this condition is false. So we're going to say here else, and I'm going to say here printf fail. And what's going to happen is if this condition is false, if it's not true, then this statement is going to execute here as opposed to this block here. And we're going to printf fail. And then similarly, after that's done, we're also going to jump down here and print out if done. So let's actually compile this and give it a try. We'll do a compile here, we run it. If I put in 52, we get like pass, congrats, and if done. If I say though 45 now, I get fail and if done. And so what's happening is control flow, the execution of statements, can go down two branches now. It can go down this branch here in this block of statements, or we can have our else case execute, depending on this condition being true or false, and then we're going to printf fail. Now, similarly to the block of statements here associated with the true case of the if statement here, we could also do this. We could also say else printf fail, and this is okay. So we could do a recompile here, and we could run it, and we could say like 44, and we get fail and if done. I could also say here, open squiggly bracket, close squiggly bracket, and I say printf fail, and then I'm going to say here printf, and I'll say, good luck next time, ! /n. And we could then do a recompile here and run it, and I could say grade 44, and I get fail and good luck next time and if done. So we can also have a block that's going to execute for the else case, the case that this condition here is false. So we would call this an if-else statement or an if-else control structure. And this ability to have different branches of control flow, to have different branches of execution, is very, very important in computing to allow our programs to solve harder and harder problems. So we can actually extend this kind of control structure further. So let's actually delete some of this stuff here. We'll just kind of start over here. And let's actually go over another type of if statement called the if, else if, else statement that adds in more potential conditions. And we'll use grades again. So we'll say here int grade is equal to 0. And we'll say here printf grade, and we'll ask the user to enter a grade. Then I'm going to say scanf, and we're going to store again into the grade variable the grade that is entered. So we're going to have an if, else statement now. So it's going to work like this. I'm going to say if the grade is greater than or equal to 90, we're going to say that that is an A. And we'll say printf A. And we'll print out the letter A. Else if the grade is greater than or equal to 80, we're going to printf the letter B. And then we're going to say else printf will say other /n. And so what we're doing here is we're actually checking multiple conditions here now. And so the way it works is we're going to enter a grade, and if the grade is greater than or equal to 90, we're going to printf A. Now, if this is false, what's going to happen is we're going to check this next condition in this else if portion here. So we're going to check this condition now, and we're going to check if the grade is greater than or equal to 80 at this point. And if it's greater than or equal to 80, we're going to printf B. Now, at this point here, we know that the grade is not greater than or equal to 90, because if it was, then this condition would have been true, and we would have printed out A at that point. So at this point, we know for sure that the grade is less than 90, but we're also doing a check here now. We're checking to see if the grade is greater than or equal to 80 here. And if it is, we printf B. If neither of these conditions are true, then we're going to print out other. So let's just give this one a try here. We'll clear this, do a recompile and run it. If we put in a grade of 92, I get an A. And similarly to before, once this is true and we printf A, control flow is going to jump down here now. I'm not going to show that explicitly because we kind of know that now, but we could run it again and put in, say, 89. And what happens here is that this condition is false. The grade is less than 90. It is not greater than or equal to 90. But then we check this next condition. We check to see if the grade is greater than or equal to 80. And it is. It's 89. So we print out B. If we put in a grade like, say, 77, then we get back other. And that's because this condition is false and this condition is false. And then we default to this else case. And so the else case in the case of an if, else if statement, it's going to execute its statement or block of statements if none of these conditions are true. So it's kind of like the catch-all case. If none of these conditions are true, this is the one that's going to execute. So we could have as many else if branches as we like. We could say here, else if, we could say grade is greater than or equal to 70. We're going to say printf a C. We could say else if the grade is greater than or equal to, we'll say 60 here. We'll say printf D. So we could do it in a block like this. And we could also mix, statements that are just a single statement like that and a whole block of statements like this, and that's okay. Otherwise, we're going to say printf fail. So maybe a passing grade has become a 60 now. And so we could test this out here, and we're going to get the same kind of results. So we could say /d. If I put in a grade of, say, 72, I get a C. If I put in a grade of, say, 63, I get a D. Oh, I forgot the /n there. So because I didn't put in the /n there, it kind of blurred in the text there with the next line on the terminal there. So I'll just clear that, compile it, and just give it another test here. So I put in a grade of 62 and we get D there. If I put in a grade of, let's say 54 now, we're considering that a fail now, I get printf fail. That's going to execute. And so we would call this an if, else statement. Now, all these variants on if statements, they all depend on conditions. So let's go over some of the different ways we could do conditions. Because conditions are typically going to depend on what's called relational operators. And we said that that greater than or equal to operator was kind of like our first relational operator, but there are others. And there's ways of combining these sort of boolean expressions, they're called, that produce either a true or false value into combinations that are more powerful. So let me show you what I mean here. We could say here int, and we could say height is equal to 0. And then we'll do a scanf for height. So we'll say printf height, and we'll say, enter height, and then we'll say scanf, and we'll ask the user to enter the height. So we'll say scanf, and we'll store the height into the height variable here. And we could have different checks. So we had greater than or equal to. We could also have a less than or equal to check. So we could say, like, if the height is less than or equal to, we'll say 155. And we'll say here not tall enough. Maybe we're checking to see if somebody's tall enough to ride a ride or something like that. Otherwise, we'll say printf tall enough. And then we'll do a clear here and a recompile here. And we'll run this and we'll say height. And if we say like 154, we get not tall enough. If we say like 156, we get tall enough. And we're just checking now, is the value less than or equal to some number here? And that's the less than or equal to operator. Now there's other operators as well. There's less than and greater than. So we could say less than here instead of less than or equal to. So less than is going to be checking only if it's less than. So we could say here, if I put in a height of 155, we're going to get tall enough. If I put in a height of 154, we get not tall enough. Whereas before, when I had less than or equal to, if I had said 155, then I would also get not tall enough instead of tall enough. So that's the difference in behavior. Just going to check, up to this point or up to and including this point, basically. There's also greater than as well. So we could say like if height is greater than a number, we could say if the height is greater than 160, printf tall enough. And this is only going to, printf tall enough if the height is greater than 160. And it's just sort of like the greater than or equal to operator. It's just that it doesn't include 160 itself. It has to be greater than 160. And otherwise we could printf not tall enough. And so we'll do a clear here and we'll recompile this and run it. And if I put in like 161, we get tall enough. But if I put in 160, we get not tall enough because greater than will not include this value here in the same way that greater than or equal to does. And that's the basic sort of relational operators that compare two values for greater than and less than, and possibly greater than or equal to or less than or equal to. But there are a couple others. So the equality operator is going to check if something is equal to something else, if a value is equal to something else. So we could say here, if height is equal to 160. So it's two equals. And it's very important you put two equals and not one. It's two equals. And we're going to check if the person's height is equal to 160 exactly. And we could printf here, like maybe like, height is 160. And down here we'll say, height is not 160. And we're checking here if the height is equal to 160 exactly now. So if I do a clear here, do a recompile and run it, if I put in 160, we get the height is 160. If I put in 161, height is not 160. If I put in 159, height is not 160. So this is going to be true only if this value here is equal to this value here. Now, like I said, it's actually really important that you don't put a single equals here. So the single equals in C is for assignment. It assigns the value on the right-hand side to the variable on the left-hand side. This here, this double equals, is checking for equality of these two values. And so if you actually had an equals here, this is where C is kind of funny. If you put an equals here, this will actually compile and it'll actually run your program, but the behavior might not be what you expect. So we'll say clear here and we'll do a recompile and we'll try it with that equals there. So it's giving us warnings already. These are warnings and they're telling us like, use double equals to turn this assignment into an equality comparison. And even the compiler is trying to tell us here, like, hey, you're doing something wrong here. And like, even I can tell you that. And so we try to run it now. And if I put in, let's say 155, I get the height is 160. So why is that? Why is the program running? Why am I getting, height is 160 if I put in 155? So what's going on here is, technically speaking, this assignment operator is actually returning a true value in this case. It's returning something that's considered true. It evaluates to something that is considered true, I should say. And so technically speaking, this is considered true, and therefore we printf that the height is 160. And so just be very mindful of that the compiler may actually allow you to create an executable with this kind of thing here, but it's always got to be double equals. And the only reason why I'm repeating that is because it's actually a common error that you see in C programming, that people will put that there and then get really confused as to why the program isn't working. So that's the check for equality. We can also check for does not equals. So we could check, is the height not equal to 160? And that is ! Equals. So ! Equals is checking that the height is not equal to 160. So we'll just kind of flip this around here. We'll say height is not 160, and down here we'll say height is 160. So let's give this a compile here. We'll clear this here, compile it and run it. If I put in 160, we get height is 160. And that's because 160 is equal to 160. And therefore this is false because the height doesn't equal 160. That's going to be true when the height doesn't equal 160. In this case, it does. We put in 160. If I put in 159, this is going to be true because 159 doesn't equal 160. And therefore this is going to evaluate to true in that case. And we're going to print out height is not 60. Height is not 160. If I say here like 171, similar thing happens, right? Like 171 doesn't equal 160. Therefore, we're going to print out height is not 160. And so that is the not equals operator. And these operators, we call them the relational operators because they're relating one value to another and they're returning true or false based on that relation. Now, there's all kinds of operators in C. Another type of operator in C is the logical operators, or sometimes called the boolean operators. And these allow us to combine booleans into new boolean values. And so we could check maybe that some condition and another condition is true. And so they allow us to make these compound complex conditionals. So I'll show you what I mean by boolean operator. Let's say that we don't just want to check height. Let's say we want to check weight too. So we'll say here int weight is equal to 0, and we'll say printf, and we'll say weight, and we'll also ask for a weight. So we'll say scanf, %d, and weight, and we'll store a weight too. Let's say that we want to check the height and weight to see if somebody is large enough to go on a particular ride. We could do that with what's called a Boolean operator called and. So we could say here, if the height is greater than, we'll say 150, and the weight is greater than, let's say 50 here, then we're going to printf good to ride. Else we'll printf not good to ride. And if we compile this, what's going to happen is both of these conditions are going to be checked. So I'll do a clear here, we'll do a compile, and we'll run it. If I put in, say, 155, and I put a weight of 55, we get good to ride. If I put in like 145 and say 55, I get not good to ride. So what's going on here is that this and operator is going to check that this condition is true and this condition is true. So in order for this complex condition now, this sort of compound condition here to be true, both things need to be true. This needs to evaluate to true and this needs to evaluate to true. If they ever don't, then this is actually going to evaluate to false altogether. And so it allows us to check for multiple things. And this allows us to have more complex logic in our program. And so we call this the AND operator, and it's the one that's going to be true if both conditions are true. So in this case here, when we had weight set to 55, this condition was true, but height was only 145. So this condition was false. And so we had false and true. That evaluates to false altogether. And then we go to this else case and we printf not good to ride. That's what we got there. And that's the AND. So the other thing we could have is an OR operator. So the OR operator looks like this. It's these two sort of pipe symbols here together. And the OR operator is going to check if this condition is true or this condition is true. And it's what we call an inclusive OR. So both conditions could be true, and this would all be considered true together. So let's give this one a try here. Let's save this. We'll do a recompile here and we'll run it. If I put in a height of, say, 155 and a weight of 45, we get good to ride. So that's because this condition here is true and this one is false. But with the OR operator, it works differently than the AND operator. The OR operator is going to be considered true. It's going to be considered true if either one or both of the operands, like each of these expressions here, is considered true. And so because we have height true, this height greater than 150 true, it doesn't matter that the weight being greater than 50 is not true. This is okay. And we get, that we get good to ride. Now, both conditions can be true, and it'll also evaluate to true as well. So if we ran this and I said like height 155 and weight 55, both conditions are true and we still get good to ride. So either condition can be true or both conditions can be true for this to evaluate to true. The only way it's going to evaluate to false is if both of these conditions here, both of these expressions here, evaluate to false. So we could clear this here, do a recompile and run it. And let's say I put in like a height of 145 and a weight of 45. In that case, both conditions are false. So because both conditions are false, that's why we get not good to ride, because this is then at that point going to evaluate to false. Now there's one more logical operator. There's one more Boolean operator called not. And not basically takes a true and flips it to false, and takes a false and flips it to true. So it looks like this. It's just an exclamation mark. So you just say exclamation mark. And we could just do one variable here. So we could just say maybe like height. So we could say like, if it's not the case that the height is greater than, let's say 150, then we're going to printf not tall enough. And then we'll just say exclamation mark /n. Otherwise, we're going to print f tall enough. And we'll take out the check for weight in this case, because we don't really need that right now. And what we're doing here is we're saying, if it's not the case that the height is greater than 150, then we're going to printf here not tall enough. Otherwise, we're going to printf tall enough. So we could clear this here, and we'll do a recompile here, and we'll run it. And if I put in a height of, let's say, 145, we get not tall enough. And so what's going on here is that if we're doing 145 greater than 150, that's going to be false, right? So why are we getting not tall enough? So what's happening is that false is basically being flipped to true by this not operator. And the way we'd read this is we'd say is, if not the case that height is greater than 150, then printf not tall enough. And so that's what's going on there, is that this is going to evaluate to false, but then this here flips that to true. And so we'd printf not tall enough. And that's the not operator. Now the not operator, strictly speaking, we usually don't need it. Like we could kind of rewrite this and we could just say like, well, if the height is less than 150, printf not tall enough. So oftentimes we don't, strictly speaking, need the not operator. Oftentimes it's just sort of making our code potentially more readable by allowing us to express something in a way that makes more sense for the reader. So if the height is not less than 150, printf not tall enough, right? And that might make more sense for the reader, let's say. Now with this operator here, you notice that I've got this part of the expression here in brackets. What would happen if I took these brackets away? I'll take these brackets away here. Let's just delete these brackets and then let's try to compile it here. We get this warning here. So result of comparison of C constant 150 with Boolean expression is always true. So what's going on here is that if I do this without the brackets, what's happening is this not operator is actually being applied first. So we're actually kind of saying not height is this less than 150? Because this operator is actually going to be applied, it's going to be used before this operator here. And so that's why we're getting this warning here telling us that like you're doing something wrong here, basically, that this comparison is always going to be true. And that's because this operator here will be applied first. We'll basically be doing a not height operation. And then we're going to be doing a comparison of that with 150 using the less than operator. So what we need to do is we need to actually put this in brackets to make sure that this comparison happens first. And then we take the result of that and we use the not operator with the result of this. So these brackets here, they can be used to influence which operation is going to happen first. And if I put the brackets around these things, around these sorts of expressions, it's going to ensure that this expression happens first. Now, with operators, there is a default precedence. So by default, the behavior was that the not operator happens first, then the less than operator is going to happen. And you can find charts online going over operator precedence. In this video, if it's ever unclear, I'm basically going to be putting brackets around things to make it clear. Now that said, in general, that can actually be a good practice because a lot of times programmers forget operator precedence. It's not the kind of thing you keep top of mind because there's all kinds of operators and remembering the exact precedence can actually be kind of tricky. So using brackets is actually not a bad programming practice in many cases anyways. Another type of control structure we should talk about in C is the loop. And C has three types of loops. So if statements are about deciding to execute one block of statements or another block of statements, loops allow us to execute a block of statements again and again, repeatedly. So let's go over the first type of loop. And I'm going to talk about a while loop first because that's one of the more common loops to use first. So what we're going to do is we're going to make what's called a counter variable here. I'm going to say int I is equal to 0. And this is going to help me determine how many times my loop has been run. And now I'm going to say here while I is less than, and I'll say 5. And then I'm going to make a block here, and I'm going to say printf I colon %d/n I. So I'm going to print out I every time through this loop body here. Then I'm going to say here I is equal to I plus 1. And so what I've got here is my first while loop. And we've got a condition here. And the condition here looks a lot like the conditions in our if statements. What this condition is deciding is whether this loop body here, this block of statements here, is going to be executed again. So if this is true, if this condition is true, the block of statements here gets executed, and then we check it again. And if it's still true, this block of statements gets executed again. And then if it's still true, it gets executed again. And then eventually when it's no longer true, that's when it's going to stop. And so what we're doing here is we're starting off with I being 0. And we're going to check for I being less than 5. We're going to print out I each time in the loop body here, but we're also going to increment I by 1. We're going to increase I by 1 each time in the loop body here. So eventually I will be 5. And at that point, 5 is not less than 5. And at that point, the loop should stop. So let's actually give this a try here. We'll say clear, do a recompile here, and run it. And we get I0, I1, I2, I3, I4, and then it stops. So what's happening here is this loop body here is repeatedly being executed. And each time it's executed, we're printing out I, right, for its current value. And each time through the loop body, we're also incrementing I by 1. And so we end up with eventually I being 5. At that point, the loop body stops. And that's why there's no I colon 5 here, because at that point it's done and it's over. And so this is, a standard loop in C. And these three pieces of it are actually pretty standard. You usually have some kind of counter variable that's set to some kind of initial value. You have a condition, and the condition is determining whether the loop body is going to continue to be executed or not. And then you usually have some change made to the counter variable. You're usually altering some variable in some way such that the loop will eventually end. Now this here, what we're doing here, adding 1 to I, that is such a common thing to do that they actually give you a bit of a shortcut in C. So you could actually say this. There's two shortcuts to it. We could say this. We could say I plus equals 1, and this will add 1 to I. So plus equals will add like whatever we put over here. We could say 5 here, it'll add 5 to I. So we could say here plus equals 1, and it'll add 1 to I. Or we could just do this. We could just say I plus plus, and that will also add 1 to I each time through. So we could save this and recompile and run it, and we'll get the exact same result as last time. So let's try some variations on this now. Let's change 5 to 10 here, and then we'll do a recompile and run it, and we'll see what happens. And we can run it, and we get this. We get I from 0, 1, 2, 3, all the way up to 9. And this shouldn't be too surprising, right? Because all we've really done is we've just changed the condition so that I will go up to, but not including 10. If we said I is less than or equal to 10, then at this point it will include the case that I is 10, but it won't include the case that I is 11, because at that point it'll be beyond 10, right? So we could do a clear, we could do a recompile, we could run it, and we'll see that I goes up to 10, but then no further. We could try some other things too. We could set here maybe I equal to 2, and we're going to say here plus equals, and we'll say, let's say 3. And so now we'll do a clear, we'll do a recompile, we'll run it, and we get I2, I5, I8. So what's going on now? So what's going on now is we changed the counter variable's starting value to 2. So that's why the first time through the loop we get I2. And now we're incrementing the counter variable by 3. And so the next time through the loop, I is going to be 5 at that point, which is still less than or equal to 10. So it's going to run. And then we go to print out I, and now I is 5, and we print it out. And then we increment it by 3. And still, 8 is going to be less than or equal to 10. So we print out 8. And then we increment it by 3 again. And then I is going to be 11. And at that point, the loop is going to stop. And so you can manipulate the counter variable and the way that you alter the counter variable and the starting value of the counter variable. And you can then influence how many times the loop is going to execute and why it's going to stop and so forth to get different behaviors. And so loops allow us to create programs that are going to have much more powerful behaviors and accomplish many more things. So for example, we can make a program where the user enters 5 numbers and we're able to find the average of those 5 numbers. So let's actually give that a test now. We're going to say here I is equal to 0. We're going to say here I plus plus. Then we're going to say I is less than 5. So we know that this is going to run the loop 5 times, right? Because we're going to go from 0 up until but not including 5 by 1. And we know that's going to execute the loop 5 times. But what we'll do this time is instead of doing a printf of I, we're actually going to ask the user for a number. And we're going to add that number to a total. And then when the loop is done, we'll take that total and we'll divide it by 5. So let's actually create some variables here. I'm going to create a variable called number, set it equal to 0. I'm going to create a variable called total. I'm going to set it equal to 0. And then we're going to say here printf, and we'll say enter, and we'll say maybe %d here. So that way we know which number. We'll say enter number %d, and then we'll say here I plus 1. Then I'm going to say scanf %d. We're going to take that number, we're going to store it into number. Then we're going to add that number to the total. So we'll say total is equal to total plus number. And then what I'm going to do first is I'm just going to do a printf of the total when the loop is over. So I'll just say printf total %d, and we'll print out the total there. And so what I've got here is I'm saying enter number %d. And I'm going to say enter the number I plus 1. So I is going to be 0 at first, that'll be 1, right? And then the next time through the loop, it'll be 2, 3, 4, 5. And I'm basically asking them to enter, a number 1, 2, 3, 4, 5. Then I'm going to say scanf, accept an integer, store it into the number variable. Then I'm going to say add that number variable's value to the total, okay? And this is going to happen 5 times because of the way we've got the counter set up. And so let's run this here. Let's just get the total first. So we'll say here GCC, we'll recompile it, we run it. So it says enter number 1, I'm going to say 20. Enter number 2, I'm going to say 30. Number 3, I'll say 10. Number 4, I'll say 30. And then number 5, I'll say 10. And that gives us a total of 100. And so now what we could do is take this total here and we could divide it by 5, and that would give us the average. So I'll say here printf, and then I'll say average, and I'm going to say %d/n. And I'm going to say here, I'll just do it right here. I'm just going to say, instead of making a variable, I'm just going to do it right here in the printf. I'm going to say total divided by 5. Okay, so there's our complete program there. And we'll do a clear, recompile and run it. It says enter number 1, I'll say 9. Number 2, I'll say 12. 3, 60. 4, 20. 5, I'll say 45. And we get an average of 29, a total of 146. Those numbers both seem correct to me. And we're now, using this program that can actually do some work for us. Like we can enter in whatever numbers we want. It'll total them up and average them for us, right? And what's nice about this is that we've got this loop that's able to carry out these instructions again and again for us. Can you imagine if we had to enter in maybe 30 numbers? Maybe we're trying to enter student grades in and we're trying to find the average grade. Could you imagine if we had to enter 30 grades in without using a loop and we had to have this code again and again 30 times? It just wouldn't be practical, right? So loops are absolutely essential to writing programs that are going to have any amount of complexity to them whatsoever. And so that's why we like loops. They're useful in situations like this. They help us write code that makes more sense. One thing you'll notice I did use these expressions as arguments to printf here. So I'm giving it an integer here for %d, the placeholder there. I'm giving it an integer here for the %d placeholder here. But what I'm giving here is an expression. And so what happens is this expression will be evaluated. So the integer that gets used for the %d here, it gets evaluated. So it becomes like 1, 2, 3, 4, 5 because we add 1 to 0. This total is going to be divided by 5. That's going to produce some result. So we divide 146 by 5, we get 29. And so, that's what's actually going to be placed here where the placeholder is. And so just be aware that you can do that as well. So there's no reason why the number of times that our loop body executed had to be fixed in terms of some specific endpoint here. We could have come up with our own endpoint programmatically, maybe by asking the user for a value, for example. So by programmatically, I mean somehow having our program determine, exactly how many occurrences should take place. And we could actually ask the user, for the total number of numbers. So we could say here like int, we could say total numbers, and then we could say is equal to 0, but then we'll ask the user for that. So we'll say here printf, and we'll say how many numbers. and we'll ask them, and then we'll say scanf %d, and we'll store the result into total numbers. And now we're going to have the loop go up until total numbers here. So our loop is going to go up until total numbers. What this means now is that we can programmatically set how many numbers we're actually going to total together and find the average of. So we'll save this and we'll clear it here and do a compilation and run it. And so it says how many numbers? This time I'm going to say 8. And then I'll say 5, 6, 7, 8, 9, 10, 11, 12. And we get an average of here 13. And I get a total of 68. So this worked differently this time. Notice how we had 8 numbers that we were asked for this time after I entered how many numbers. And that's because I said here, how many numbers, and I stored the result that the user put in into total numbers. And then we have the loop go up until total numbers now. So I can run this program and I can give different values now. So I can say clear, I could say recompile, run it, and I could say total numbers. This time let's say 10. And I could say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? And we're programmatically determining how many times our loop is going to execute in terms of the total value that the counter is reaching towards. Now, you'll notice this though, average 11. That doesn't seem right for 10 numbers here. So what's going on is we have our first bug in a program. And by bug, we don't just mean necessarily a compiler error. A compiler error is a really obvious bug to spot, right? If your program won't compile, the bug is obvious and the compiler is trying to help you find it. Now, this kind of bug can be harder to spot because if you just run your program, you might think average of 11, I guess that's right. But it's clearly not in this case, right? Because we've got 1 to 10 numbers here and average of 11. So that doesn't make any sense that the average is higher than the maximum number. So the problem is here is look at this. I have total divided by 5 still. That's how I'm calculating my average. And I've now got more than 5 numbers potentially. So I'm going to say here total divided by, and I'll say total numbers now. And that should fix the bug, right? Because I'm dividing by the right number of numbers now to find the average. So I'll do a clear, do a recompile, run it. This time I'll say 10. I'll say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we get total of 55, average of 5, and that seems about right? Because 5 is the middle number here. And so this is how we could, fix that bug, is identifying what went wrong there. But as you write programs that are more and more complicated, you're going to want to sort of trace back errors like that you find to try to determine how could it have come to that conclusion? How could it have produce that output value given the code that I've got? And you're gonna have to look at your code and analyze it and try to figure out where things could have gone wrong. In general, when you're trying to debug things like that, my suggestion is to throw in as many printfs as possible. So just put a lot of printfs into your code and print out the different values of different variables you've got. And that can be very useful for helping you to debug and understand what's going on inside your program, that it's producing an incorrect result. So this is another example of a while loop here. We could do another example of a while loop. Let's do a while loop that is going to run an indefinite number of times. So like this loop here, we're programmatically setting the endpoint for the loop. And that's one way of kind of making a loop that's going to vary in terms of how many times it's going to execute, is we can, set the total occurrences of the loop's execution using the endpoint here for the counter variable, and that's one way. Another way we could do it is we could have a loop that will execute an indefinite number of times. In other words, an unknown number of times. So let's try to do that here. What I'm going to do is I'm going to make a loop that is going to find the maximum number that was entered. And the loop is going to exit when -1 is entered. So whenever the user enters -1, that's when the loop is going to stop executing. But until then, it's going to keep asking the user for more numbers, and it's going to keep track of the maximum number. And I'm going to say that the maximum number is always going to be a positive number. So we're going to assume that the user is only going to enter positive numbers here. So we're going to say here int number is equal to 0, and that'll be the number the user enters each time. And then I'm going to say int, and I'm going to say max, and I'm going to say max is equal to -1. So we're going to say that users are always going to enter positive integers, and we're just going to assume that they're always going to enter positive integers. So if I set max equal to -1, what I'm doing is I'm saying, let's assume that the maximum number is -1 to start. And therefore, any number that the user enters next, if I compare it to max, it's going to be larger than that number. It's going to be larger than max. And therefore, I can actually set that as the new maximum initially. And so let's make our loop now. I'm going to say here, while number doesn't equal -1. Then I'm going to say to the user, printf, enter a number. I'm going to say scanf, store the number into number. And now I'm going to put an if statement inside my while loop. And I'm going to say, if the number is greater than max, set max equal to the number. And then when I'm done here, I'm going to printf the max number. So I'm going to say max, and I'm going to say here %d, and I'll output the max number here. So watch how this program works, and then we'll go through it step by step together in terms of the code. So we'll do a recompile here, and then we'll run it. So it says enter number, I say 5. Enter number, I say 10. Enter number, I'll say 7. Enter number, I'll say 12. And then I'll say 4, and then 15, and then 2. Then I'll say -1, and it quits, and it says max 15. So my program was able to determine the maximum number that was entered here. And it was able to quit when I entered -1. So what's going on here is we have what's called an indefinite loop, because this loop is going to execute an unknown number of times. And what we're doing is we're asking the user for a number each time. And if that number ever entered is -1, that's when the loop is going to stop. So that's why when I put in -1 there, that's why it stopped, because at that point, we've entered a number that is -1, and number is no longer not equal to -1 at that point, and so the program stops. Here we're saying if the number is greater than max, max is equal to number. And what we've done is we've started off with the assumption that the maximum number is -1, and that is a number that is so low that we know there's going to be a higher number than that, because we've said that we're positive the user is only going to input positive integers. So like 5, 10, 7, 12, that kind of stuff, right? And so here, the first time through the loop, we're going to determine that the number, whatever it was entered was 5, is going to be greater than the max number. And we're going to set that number to be the new maximum number. And what happens now is that each time we enter another number, we're doing a comparison here. And we're seeing if the number entered is greater than the current max number, set max equal to that new number. Then by the time the loop is done, at that point, whatever number we've encountered that was the maximum number, max will have been set to that number, just by definition of how this if statement is checking out the previous maximum number. And then we're going to printf the max value here. And so it's a simple little algorithm here, but now we have this program that can determine the maximum number entered. So something like this, where we have now an if statement inside a loop like this, number one, we call this a nested structure, because the if statement here is nested inside of this loop body here. It's embedded inside of this loop body here. So we call this a nested structure. But number two, once we start doing things like this, it can be difficult to understand what's really going on in our program. It can be difficult to understand how it's happening that we're finding a maximum number here. And this is why I say just throwing printfs into your code to understand what's happening can be a big help. So one thing we could do is we could say here, after every iteration of the loop body, let's do a printf of max, because I'm not sure how it's working. Let's say I'm unsure how it's working. So let's do a printf of max every time through the loop body, just to help me understand what max is at each iteration of the loop. So let's now do a clear. We'll run it again. So it says enter number. I'll put in 4. Max is 4. Okay, that makes sense, right? Because number was 0 initially, but then we read in a new value for number. Max was -1 initially. Now we read in 4 for number. 4 is going to be greater than -1. So max is now equal to 4. And we print out the max value, right? Now let's say I enter number 2. I enter the number 2 and max is still 4. So what's going on there is that, yeah, we entered a number 2, but this isn't the case, right? Like 2 is not greater than 4. So therefore we never set a new maximum number. If I enter a number 10 though, Now what's happened is that number 10 is greater than the max because 10 is greater than 4. We set a new maximum number and we can recognize that here. And then I say -1 to quit and I get, max 10 here now. And so this is why I say if you're ever unsure as to how your program is working, if you're ever unclear about it, just throwing in lots of printfs and print out the values of your variables, that can be a very, very helpful debugging tool to help you understand what's going on inside your program as it is running. Because if all you have to look at is the sort of end output value of your program, it can be very difficult to try to understand how your program got there. So the trick to debugging, even if you're like a senior developer, even really experienced developers will still throw prints into their code to figure out what's going on. And so I would encourage you to use that technique when you get confused. So one other type of loop we should mention is one that you generally want to avoid, and that's an infinite loop. That's when you have a loop that doesn't stop. So how could that happen? Let's do an example here. I'm going to say int I is equal to, let's say 10. And then here I'm going to say while I is, let's say, less than 20. Now I'm going to say printf, and we'll print out I. I'll say I colon %d/n, and we'll output I on a new line each time. And then what I'm going to say here is instead of I++, I'm going to say I is equal to I minus 1. So we're going to take 1 away from I each time. I could also do this with I minus minus. So like I++ adds 1 to I minus minus will take 1 away from I. Let's run this and see what happens. So I'm going to say clear, do a recompile, and run it. And look what's happening. The loop is going on and on. I actually had to kill the program by hitting Control-C. But you can see the loop is just going on and on here, and it's getting into very high numbers very quickly. We got like 101 or 108 1970, 108 1971, 108 1972, and the loop will just never end. So what's going on here is that we have an infinite loop because we're setting I to 10 and we're saying while I is less than 20, keep doing this loop body here. But instead of doing something to I that would make it eventually no longer less than 20, we're doing the opposite. We're actually decrementing I by 1 each time, right? So I is just going to get further and further away from 20. It's going to be more and more less than 20 each loop iteration, right? And so the loop is just going to go on forever. And we would call this an infinite loop. Now, sometimes people will create infinite loops on purpose in certain specific scenarios. But for the most part, when you have an infinite loop, it's probably a sign that you have a bug in your code. And you may just have to sort of kill your program process by hitting Control-C on the command line or whatever the equivalent is on the system you're on. So a while loop is one type of loop in C, but there's actually 2 others. And one of the other ones is called a do-while loop. So a do-while loop is actually guaranteed to run the loop body at least once. So with the while loop here, it's not guaranteed that we're going to run the loop body for sure even once. Because if I said here like I is equal to 25, then at that point, 25 is not less than 20. This loop body is not going to execute even once. So I could say clear here. I could say recompile it, and then we'll run it, and nothing happens because the loop body doesn't execute even once. A do-while loop is different in that it guarantees the loop body will execute at least once. And so a do-while loop looks like this. We'll say here I is equal to 0. Then I'll say do. Then I'll put my block here. Then I'll say while, and I'll say while I is less than 5, semicolon. And I'll do sort of what I did in the past. I'll say here printf, and I'll say I colon %d, and we'll output I. Then I'm going to say here I++. And at least let's see what happens this time here. So let's do a recompile here, and we'll run it. And I get I0, I1, I2, I3, I4, kind of like I did in the past. And so far it doesn't look too different. But what's going on here with the do-while loop is that the condition is checked after the first execution of the loop body, which means that the loop body is guaranteed to execute at least once. This is just a syntax thing, but just notice the semicolon here. You do have to include that when you're making a do-while loop after your condition here. And so this isn't the most interesting case for a do-while loop. I mean, it's good that we can see that it works just like a while loop in some cases. Like this looks like our first example for the while loop there. But let's do an example where it doesn't look like that. Let's do an example that's a bit different here. So we're going to say here I is equal to 25. So 25 is obviously greater than 5 here, right? And so 25 is not going to be less than 5. But if we recompile this and we run it, we're going to get I colon 25. And so this is an example here where despite the fact this condition is not true, this loop body runs at least once. One practical case for using a do while loop would be to do input validation, where we ask the user to enter a value. And only if that value is entered correctly are we going to proceed. If they don't enter it correctly, we're going to ask them to enter it again because there's something wrong with it. So let's just say, for example, we got some number. We'll set it to 0. And we want to ask the user to enter a number. And for some reason, that number has to be greater than 0. So we're going to say here do printf, and we'll say enter number, and maybe we'll say greater than 0 here. And then we'll say scanf, and we'll store that number into number. And we're going to do this loop so long as the number is less than or equal to 0, because we said that the number has to be greater than 0. So long as the number is less than or equal to 0, we're going to keep doing this loop here. And so if we do a clear and then a recompile here, it says enter number greater than 0. So if I put in like -1, it's going to keep asking. If I put in 0, it's going to keep asking. Only if I put in a number greater than 0 is it going to stop. And this would be an example of doing input validation, where we're basically validating the input the user has given us to ensure that it meets the requirement we need, to ensure that it's greater than 0 before we proceed with the rest of the program. We might want to give the user some indication that the number they've entered is incorrect. We might want to give them a reminder. So we could say something like, if number is less than or equal to 0, printf number must be greater than 0, just to give them a reminder as to what they need to do. So other than that, though, this is an example of using a do while loop in a practical way here. So now we're just telling them number must be greater than 0 there. And this would be sort of a practical example then of using a do while loop to help us solve a problem, which is that we know that for sure we're going to have to ask the user to enter the value at least once. We know that for sure. So we might as well have a do while loop where we're going to ask them that for sure at least one time. And then only if the number is not conforming to what we need it to, are we going to ask them again. And so this kind of fits the case of the do while loop doing something at least once pretty perfectly. Now let's talk about the third type of loop in C, the for loop. And the for loop is useful because many loops follow this sort of structure to them. We can say here like int I is equal to 0. We can have our counter variable. We can have some condition like while I is less than 10. And then we can increment I. We can update I somehow, right? And we can printf I. And we've got our program that we had before. And we shouldn't be too surprised that we're going to get here I from 0 to 9 if we do a recompilation and run it. Now these three pieces here, the initialization of I to something, the condition here, and the updating of I somehow. Those three pieces are extremely common to see in a loop. And so what a for loop does is it gives us a nice, concise way of expressing these things. So a for loop works like this. I would say here for I is equal to 0. I would say here I is less than 10. Then I plus plus. And notice how I have these semicolons here. I have semicolons here separating these three statements here. So these are actually individual statements. Like this is setting up I equal to 0. This is checking if I is less than 10. And this is incrementing I. And then I could put my printf in here to output I there. And we're going to get the same result as before. So we could do a clear, recompile it, run it. We get I from 0 all the way to I to 9. And what's happening here that's nice is that I've got everything on one line. In fact, it even turns out that I don't need this. I could actually delete this, and I could actually say int I equal to 0 here. So I could actually declare my counter variable right here. And this will actually be okay. I will actually exist within this block here. I will be a variable that is defined and that we can use within this block of code here. So I can use it here, and I can increment it here, and that's all fine. So I can even kind of remove that variable declaration as well and put that inside here. And what's nice is that all of the important information for how my loop is going to function is on one line. And so the readability of the code is improved because I don't really have to kind of dart my eyes around. So before, what we had before with the while loop there, imagine that I had a lot of code there. Like imagine that I had like a lot of if statements in here, like if, and doing some work here, and then maybe like an else, and then doing some work here, and maybe there's an if in here, doing some more work, and it's just a big long piece of code, right? If I'm looking at my loop and I want to figure out how it works, I've got to like look at the condition. I might have to figure out where the variable is being initialized. Maybe that also is up somewhere, separated by a bunch of code as well. And then I got to look for the update of this counter variable. So I'm gonna have to scroll to the bottom of the loop to find that, right? And so I've got to move around quite a bit to understand how the loop is working. I've got to scroll around quite a bit just to understand what's going on with the loop. Whereas with what I had before with the for loop there, what was nice about it was all on one line. So if you were the developer trying to understand how this loop works, you've got one place to look where all the information you need is located there. So for loops work like this. We'll say here for int I is equal to 0. And this we could say is the initial statement. And what it's doing is it's setting up any sort of counter variables we need. The next thing is the condition. And the condition works like the conditions in other loops. This condition here is going to check to see whether something is true or false. If it's true, the loop is going to continue and the loop body is going to execute again. If it's false, the loop will stop executing. And then this here is the update statement. And we could say here like I++, and this is going to update counter variables. And we could then say in here printf, and we could print out I again, and we're back to our loop that we had before there. And so we could do a quick little recompile just to make sure we've got it working correctly here. Run it there. We get I from 0 to I to 4 this time. And those are the three pieces, is the initial statement that sets up the counter variable, the condition or the test expression that tests the counter variable somehow, and then the update statement that updates the counter variable. Now, one thing is we said that this int I equal to 0 meant that the I variable only exists within the body of the for loop. So if you've only got one statement, then that is the body of the for loop. If I tried to use I outside the body of the for statement, then it's not going to exist. And we're actually going to get some trouble here. We're going to try to compile it here. We get error use of undeclared identifier I. So that's what we mean when we say I just doesn't exist outside of the for statement body, which in this case is just one statement. So outside of that for statement body, we just can't use it. We can't access it. So just be aware of that. That's actually called variable scope. It's something we'll talk about more when we talk about functions in just a little bit. So let's put some of the ideas we've learned together and make an application that's going to convert, say, meters to feet. And we'll make a table. So we'll make a table of conversions, and we'll start from some initial value for meters. We'll step by a certain step value in each row of the table, doing the conversions, and then we'll end at some kind of end value. So once we've exceeded the end value, we'll stop. So we're going to need some variables here. We'll say double initial. I'm going to have to make the font a bit smaller here just because we need to be able to fit in more code here. So I'll say double initial is equal to 0. And then I'll say step is equal to 0. And then I'll say stop is equal to 0. And that'll be our initial value, our step value, and our stop value. But what I'm going to do is I'm going to ask the user for these values. And we're going to use our input validation style to do that. So I'm going to say here do, and then I'll say printf initial, and I'll say m for meters. And we're going to ask the user for the initial value. And I'll say scanf, and then I'll say %, and then I'm going to say lf because we're storing a double value here. And then we'll have and initial. And this will be the initial point at which conversions will take place. And I'll say here while initial is less than 0, because we need an initial value that is going to be at least 0, because we're not going to work with negative distances, say. And then what we should do is we should tell the user that the initial value must be greater than or equal to 0 if it's not, because otherwise they're not going to know why they got it wrong. So I could say here, if initial is less than 0, we're going to warn the user. We're going to say here, printf must be greater than or equal to 0. So it's got to be at least greater than or equal to 0. And we'll put that there. And And let's just do a test of this portion of the code so far. So we're going to be writing a longer program here. And whenever you do that, it's never a bad idea to just sort of stop at certain points and check to see if the code you've written so far is correctly. Because if you write a lot of code and then figure out you've got a bug, it's going to be harder to trace it back later and figure out where that bug is. So let's just do a compile here, and we'll just do a quick little test just to make sure this logic is okay. So initial, if I say like -6, it's not okay. If I say 0 though, it's going to be okay. So it's looking pretty good. So the step value is going to be what we're going to increment our conversion by each time in terms of the meters that we're converting to feet. So the step value is going to have to be greater than 0, because if we have a step value of 0, we'd be adding 0 to our converted value each time. We're going to be adding 0 to the meters value that we're converting each time. And that wouldn't be very useful. The table would just go on and on forever. So we can't have a step value of 0 or less than 0. It's got to be greater than 0. So we'll input the step value, and it'll look pretty similar to this. So I'm actually going to copy and paste the code because it's very similar. And I'm going to say here, printf, I'll say step. And then here I'm going to say step. And then I'll say if step is less than or equal to 0, I'm going to say must be greater than 0, because it's got to be greater than 0. And so long as the step is less than or equal to 0, I'm going to continue to ask for step values here. Okay, so we'll do a recompile here, run it. So for the initial, I'll just put in something reasonable like 5. And then for the step, I'll try 0. If I put in 0, it says must be greater than 0. If I put in 0.125, even that's okay. Well, I put in 0.124, but you get the idea. Even that's okay because it's at least greater than 0. So that's the initial value. That's the step value. Now we need the stop value. And the stop value is the point at which we're going to stop doing conversions in our table of conversions here. So the stop value also needs to be greater than or equal to 0. So we're going to do a copy of this initial loop here, and we'll just put in stop here because we're basically doing the same thing. We're just going to make sure that our stop value is greater than 0 or equal to 0. Otherwise, it's not going to work. So now we're also accepting a stop value the same way we are the initial value. Now what I want to do is I want to make a for loop that's going to output a table, a nicely formatted table with conversions from the initial value going by the step value up to the stop value. And so let's actually make the table in a simple way, and then I'll show you a way to pretty it up a bit and make it nicer. So I'll zoom in a bit here because we can kind of leave this code up here now because we kind of know what this does, right? We went over how to do this type of code before with the do while loop, so nothing too surprising here. And we'll kind of zoom in on this portion now here. So let's do the conversions here. I'm going to say for, and I'll say double, and I'll say conv for the value we're going to convert is equal to initial. And we're going to keep going until this value is no longer less than or equal to the stop value. And then we're going to increment by the step value each time. So I'm going to say here, and we can put these on different lines here if it's getting too big. We could do it like this too. This is also valid. So I'll say here, conv plus equals, and now I'm going to say the step value. So what I've got here all together is I've got a for loop that's going to start off at some initial value. And conv is going to be like our counter variable that represents our conversion that we're doing. And then we're going to go up until and including the stop value. And we're going to increment the value we're converting each time by the step. And so that's the three portions of our loop there. There's the initial statement there, there's the condition there, and there's our update statement there. And all I've done this time is I've put them on 3 separate lines just to kind of make our code a little easier to read than having it kind of bleed onto the next line here. And then what we'll do is we'll output our table of conversions. And I'll make it kind of an ugly table, and then I'll show you how to pretty it up after. So then I'll say here printf, %f, and we're going to output the conversion value, so the meters value that we're currently going to convert, and then I'm going to multiply it by the number needed to get the number of feet in meters. So we're going to say conversion times, and I'll multiply it by 3.28084. So this is going to take the amount of meters and convert it to a number of feet, and then we'll output that value as well. And so, like I said, this is going to be not a very pretty table, but it'll be a table. We'll do a printf here with a new line, just that way it's separated from our input there. So, okay, let's save this here. We'll clear here, and we'll give this a run and just see how she goes. So I'm going to say, starting off with we'll say 1 meters. Stepping by 1 meters, let's stop at 8 meters. And here we now have this table of conversions where 1 meter is 3.28084 feet. 2 meters is 6.56168 feet, and on up until 8 meters, right? And this is what I mean when I say we have this table of conversions here. Now, if I wanted to alter the step size here, that's going to influence how each row of the table is converted in terms of the amount that the previously converted value is incremented each time. So I'll just say clear, we'll run it again. I'll say initial 1, this time I'll say step of 2, stopping at 8. So now we convert 1 meter, but then the next time through the loop we convert 3 meters, then 5 meters, then 7 meters. And so we're stepping by 2 each time we do a conversion now. And we're stopping at 8, which means that we're not actually going to convert the next value after 7 because it would be 9. It would be past where we wanted to stop doing conversions. And that's kind of a nice little way of setting up a table of conversions with only a few values. We could say something like this. We could say clear, we'll run it. I could say initial is 0.5. And then I could say step is 0.0, we'll say 1, and stop is 0.6. And now we have this table of conversions, and they're all very small values here because we've got like 0.50 and we're going up until 0.59, and we're doing a conversion of each one of these values here from meters to feet, right? And the conversions are accurate here, and we're still stepping by 0.01. And this would be another way of doing a table of conversions here. Now, one thing that is sort of interesting here, notice how it doesn't go up until 0.60. You'd think it would, right? Because we said stop at 0.6. We're incrementing by 0.01 each time. So why doesn't it go all the way up to 0.6? So that again is one of those quirks we need to be aware of when working with doubles and floats in C. Because remember that decimal values like this, like 0.6, remember that the precise exact value is not being stored. What's being stored is a number that is very, 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 very close to that number. And we say that that is a certain level of precision that we get. So when we do a comparison here, and we're comparing, 0.6 as it's been incremented here to 0.6 here, that comparison may not actually come up as being equal, because here we've started off with 0.5 and we've added 0.01 to it, whereas here we've just got the number 0.6. And because each time we're adding these numbers that are not really 0.01, they're a number that's very, very close to 0.01, it's not going to be quite the same as this number here necessarily. And so we get this sort of weird behavior here where it should be equal, we'd think, but because of the way the floating point values are stored and because of the way double values are stored, we're not going to get that behavior that we expect necessarily. So it's not a problem. It's just something to be aware of. Just be aware of the fact that doubles and floats can behave strangely in ways like this. And it has to do with the fact that they're really stored as sort of a series of fractions, we could think of them as, that get us very close to the number, but not actually at that number exactly. So let's pretty up this table a bit. Let's make it a bit nicer here. Let's first add some columns here, some column headers here. We'll say here printf, and I'm going to say meters. Then I'm going to say here, we'll do maybe 10 width columns. So I'll say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then I'm going to say feet. So 1, 2, 3, 4. And then I'll do a printf here, and I'm going to do just a row of stars. So I'm going to have like 20 stars. I'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I'll copy these. So we've got 10 stars here after the other 10 stars. And then that'll give us like a row of 10 stars there. So that should make it a little bit nicer here. I'll have to remember to put a new line here. This will make it a little bit nicer in the sense that I should have some column headers. So I can do a recompile here and then run it. And we'll say initial, we'll say 1, step, we'll say 2, and stop, we'll say maybe like 13. And now we have this column here, we have meters, and then we have feet here, and we have this sort of, separator here. And so it's starting to look a little bit nicer, but notice how like the meters data is sort of bleeding into the feet data. And notice how the feet data here is actually kind of starting off in what looks almost like the meters column, or at least sort of more over to that meters column there, right? It'd be nice if we could somehow align the data so that the meters data is stuck to the meters side, the meters column here, and the feet data is stuck to the feet side or the feet column there. And there is some ways we can do that with printf. So with these placeholders here, you can actually use some additional, essentially, arguments to these placeholders to modify how things are output. So I'll show you that here. Let's actually make a bit of space here just so we can kind of check things out here. So I can always put my arguments for functions on different lines like this. So I'm just putting the arguments on different lines here so I can focus in on this and just show you how to modify this here. So what I could say for starters is this. I could say here 0.2 and 0.2. And what that's going to do is it's going to limit the number of decimals that are output to 2 for each one of these. So we could say here clear, recompile, run it, and I'll say initial 1, step 2, stop 13. And now look what we got here. We only have 2 decimal points. And when it does the output, it'll just sort of round up to whatever makes sense in terms of this last digit here. But we're only outputting 2 decimal digits here now. And that's now kind of making for, smaller numbers. In some sense, they're actually nicer looking than these ones too, right? Because like, look at this, 7 point, and we got all these zeros here. To some extent, like 7.00 is nicer and cleaner, right? So this is something we could do to modify how the floating point value is output. And we're essentially giving like arguments to this placeholder here. And there's a whole table online that you can find. There's multiple tables out there that go over all the different ways to affect how your placeholder behaves. And this one here is basically determining how many decimal digits of output we get. Another thing we can do is we can specify a column width. So I could say here 10, and I'll say here 10. I'm actually going to move them right together now. So what this means is output the floating point value into a column of length 10. This means output the floating point value into a column of length 10. So we've got the 10 and then dot 2, and the 10 means the column size, the dot 2 means the number of decimal points. And I just put them right together. So these are still 2 placeholders. They're just right next to each other now. So we'll do another clear. We'll run it again. And we'll say initial 1, step 2, stop, we'll say maybe 15. And we get the table here now. We get meters and feet. And now they're both in columns of width 10. So you see now that like the meters data all stops right here. It all stops like right at the edge of where feet is about to start. And the feet data here, it looks like it's all kind of shifted over now to the right. So what you've got here is this is a column or a field, we should say, of length 10. This is a column, or we should say a field of length 10. And we're basically outputting the number into a field, into an area of spaces with that amount of width that we've specified here. So there's one more modifier I could use. So these are right aligned fields. So the data is being output into a right aligned area of 10 characters. If I want to make it left aligned, I could say minus and minus. And then that'll make the data left aligned in that field there. And we'll just throw one more printf at the end here in that's going to just say /n, just to put our table on a new line. So do a clear here. We'll do one more recompile and run it. And we say here initial 1, step we'll say 3, stop we'll say maybe 19. And here's our table here. So we've got meters and feet, and we've got 1 meters up to 19 meters, and it's being converted to feet each time. But now we're shortening the number of decimals we output. We've got them both being output into columns or fields of length 10, and we're left aligning our output in that 10 space field. So that way it's kind of got this nice pretty look to it now. So this is just an example of how we can use placeholders and use some of these essentially arguments to placeholders to modify how our data is output, to output it in a more pretty looking way, to make a nice looking table like this. And so at this point, we've put together a bunch of ideas we've learned. We've got variables here. We've got different types of variables like doubles. We're using do while loops with an embedded if statement here to give the user some feedback. We're doing some input validation. We have a for loop here, and we're doing some advanced printf stuff. So we're only like 2 hours into this, and we're already able to make, a reasonably sophisticated C program at this point that's able to do some useful work for us. So, at this point, we should be pretty happy that we've gotten this far this quickly. So there's one more type of control structure we should talk about called a switch statement. And I'll just kind of go over this one here by deleting this code here. And a switch statement is a little bit like an if statement in the sense that it's not about repeated execution of statements. It's about branching, where we're going to decide which groups of statements are going to execute. So an example of a switch statement would be something like this. We'll say here int number is equal to 0. And then we're going to say switch and then number. And what we have here is interesting. It's not a condition. It's just something that's going to evaluate to a value. That's all. So it's just going to be number. It's going to be the value number here, which is going to be 0 initially here. And then what we're going to have here are cases. So I'll say here case and I'll say 0. Then I'm going to say printf and I'll say case 0. And I'll just zoom in a little bit here. So let's just give this a try here. I'm going to say clear. We'll do a recompile. We run it and we get case 0. So what's going on here is that we've set number to 0. The switch statement is going to look at number. It's going to look at the value of whatever is here. And it's going to find the case for that value. It's going to go down here and it's going to find the case for that value. And so here we've got case 0 and we're going to say printf case 0 and then it's done. Now, if number was say 1 instead, that case is not going to execute. We get nothing because switch works by going through and checking to see one by one for any cases in here. Is there a case that matches the value of this number here? And it's going to start from the top and go down to the bottom. So we could then say here case 1 and we could say printf. Now I'm going to say here case 1. Okay, so we'll do a recompile, run it, and now we get case 1. And so we could say here number 0 again, and let's see what happens if we do number 0 here. We'll do a recompile, run it, we get case 0, case 1. So a switch works differently than an if statement in this sense, and it's a big important difference, is that we have this value here, and we're going to go through and then find the matching case. And once we found the matching case, we're going to start executing the statements underneath that case. But the way that a switch works is that execution is going to just fall through to the next group of statements by default. So execution falls through, and we call it fall through logic because it's kind of like we reach the end of this statement here, we reach the end of this group of statements here, and then execution is just going to fall through. It's not like the next case is going to be checked. Execution just continues, and execution is just going to keep on continuing. So we could have like a case 2 here, and we could say here printf, and I could say case 2 exclamation mark /n. And now if we do a recompile and run it, we're going to get case 0, case 1, case 2, because execution just keeps falling through at that point. Once the matching case has been found, execution just keeps going through. Now, what we could do to prevent this is we could use what's called a break statement. So if I say here, break, what happens is execution does not fall through. And the execution is actually going to go down here after the switch is over. So we could say printf, switch over. And execution will actually go down there after the break is encountered, just like in a loop. And so if we do a clear here and run this, now we're going to get case 0 and that's it, because the break is what breaks us out of the switch and moves us down here. Now, I could put breaks in wherever I want. So I could put a break here. And again, we're going to get fall through until that case, until that break. So we have number 0, so case 0 matches, we printf case 0, we printf case 1, and then we hit this break, and then that's when the fall through logic is going to stop. That's when we're going to break out of the switch. So we can really manipulate which cases are going to execute with these break statements. Another thing we can do with a switch is we can have a default case. So I could say here default, and I could say here printf, and I could say default case. And what's going to happen is if none of these cases match for our value here, then the default is going to execute. And for the default, we don't really need a break because at that point it's going to fall through and it's going to end up down here anyways. So it's all good there. We don't need a break there. So then if I say something like number is equal to, let's say 3 here, that's going to match then the default case because it's not going to match the first two. So we could do a recompile, we could run it, and we get default case. And so a switch could be a good tool to use when you have some value and some finite number of cases that value could match. And maybe you can handle all the other cases with the default. For those kind of situations, a switch is going to be good. Now, in general, though, I don't really like to use switches when I can avoid them. They tend to be a little more difficult for people to understand how to use them. So you have to remember how the break works. You have to remember how to include the break, right? And a lot of times developers will forget that. A lot of times developers get confused by them. And so a lot of times you can just do it with an if statement anyways. So maybe just stick to an if statement. In some languages like Python, they actually took out the switch entirely and they just make you use if statements. So like I said, it's not my favorite control structure, but you should know that it exists. You should know it's a thing you can use. So next, let's talk about arrays in C. So arrays are actually pretty important. They're one of the first real data structures we use in C. And a data structure is a way of dealing with a collection of information, a collection of data. And basically the problem that arrays are solving for us is, what if I have a bunch of related data I want to store? Like let's say I want to store a bunch of student grades. I could say like int grade 1 is equal to, let's say maybe 75, int grade 2 is equal to, let's say 88, int grade 3 is equal to, maybe we'll say like 72, int grade 4, and on, right? We could say is equal to maybe 92, int grade 5, and we're just kind of keeping going here. Int grade 5 is equal to, maybe 79 now. And we've got 5 grades here, right? And this would be one way of storing 5 grades. It'd be one way of storing this collection of 5 grades that we want to work with. And we could do things like calculate an average of the grades, right? So we could say here like int average is equal to, and we have to say like grade 1 plus grade 2 plus grade 3 plus, and then we'd have to keep going, grade 4 plus grade 5. And then we have to take all of that and divide it by 5, and we could compute an average this way. The only problem with this is not going to scale very well. This is not going to handle larger and larger numbers of grades very well at all. So we could say like grade average here and just output it here. We'll just output the average. And we'll just give it a recompile and run it. And oops, what did I forget to do? I forgot the semicolon. Put that in there. Recompile and run it. And I get an average of 81, and that looks correct, right? But this is not going to scale well at all. Like imagine I have a class with 200 students in it. Am I going to make 200 grade variables? And then am I going to like write out, grade 1 plus grade 2 plus grade 3 on to plus grade 200? Our code is going to be an absolute mess if we try to do that. So this is not a good way of dealing with a collection of data, like a group of related data. We need a better way than this. So the better way to do it, or at least one better way to do it, is with arrays. And arrays are kind of like our first data structure. They're our first way of handling a group of data in a more sensible way. And the way they work is like this. I'm going to say here int grade. Now I'm going to say open bracket, close bracket. I'm going to put a 5 in the middle. So what this does is it declares what's called an array. Now an array is a collection of data in memory that can all be addressed, that can all be accessed using this grade variable here. So what goes on is basically in memory, C has gone out and allocated space for storing these grades. And we have now grade, and we now have like 5 boxes in memory. And these boxes have an index. So we could say like index, and we could say here 0, 1, 2, 3, 4. And that's how we have our data stored now, is at these 5 indexes here. And we actually start counting from index 0. So what I can do is I can store data at these 5 boxes in memory. So I could say like, grade 1 is like 92, or grade 0 is 92, I should say. Grade 1 is 85, grade 2 is 72, grade 3 is 73, and grade 4 is maybe 95. And I could then store these values in these 5 boxes here, in these 5 positions, these 5 slots in memory for storing integers. And I could do that like this. I could say grade 0 is equal to 92. So when we do this, when we say open bracket, 0, close bracket, what I'm doing this time, this is actually different from this one here. What I'm doing this time is I'm accessing this element of the array, and I'm accessing this box in memory with this index, and I'm storing 92 into it. Then I could say like grade 1 is equal to 85. I could say grade 2 is equal to 72. Grade 3 is equal to, we'll say 73, and grade 4 is equal to, we're going to say 95. And these are our 5 positions in memory. These are our 5 boxes in memory that we're using now, and we're accessing them by their index here, 0, 1, 2, 3, and 4. And this here, this starting from 0, we call that 0 indexed. We'd say it's a 0 indexed array because you start counting from 0. And starting to count from 0 is actually a thing in programming. It's actually a common thing in programming. So even though it seems a bit unusual to start counting from 0, in programming, it's not that weird. And once I've got these grades stored like this, I can access them as well. So I could say here like printf, and I could say here grade, let's say grade 2 is equal to %d. And now I'm going to output grade 2 here. And so what I'm doing is I'm accessing the value here and I'm using it to print out an integer here. And we could say save this. I could say clear. I can compile it. I can run it. And I get grade 2 is equal to 72. And so what we're doing here is we're accessing the value in our array at index 2 when we use this syntax here to get at it. Now, what I could actually do is I could actually use a variable here to actually access different indexes in my array. So let's do it like this. Let's say here for int I is equal to 0, I is less than 5, I plus plus. Now I'm going to say here printf, and I'll say grade %d is equal to %d slash n. I'm going to output I. I'm going to output grade at I. And so what I've got here now is I'm now outputting grade at the index I is equal to an integer here, and that integer here is going to be grade at the index I. So I'm outputting I for this value here inside this string here with the grade and the brackets here around it is equal to %d, and I'm going to output the value in the grade array at that index here. So we could do a recompilation here and run it, and we get grade 0 is 92, grade 1 is 85, grade 2 is 72, grade 3 is 73, grade 4 is 95. And we're programmatically accessing with a variable here the different indexes, the different values at each index in our array here. And so this now allows us to write very powerful code when we can access our array using a variable to determine the index that we're accessing. Because now all of a sudden, if I want to write my average code to find the average of the grades in this array, I no longer have to write out, grade 0, grade 1, grade 2, grade 3, 200 times. I can write a loop to process that. So I'll show you what I mean here. I could say here, int total is equal to 0. And I'm going to say here for int I is equal to 0, I is less than 5, I plus plus. Let's add to this total each time the value of grade at that index. So we're going to go from 0, 1, 2, 3, 4, and we're going to add each time, just like we went through the grade array here, we're going to add each time the value to total, which starts off at 0. And then we'll do a division of the grades total by 5 to get the average, right? So we can say here printf, and we'll say average %d slash n, and we'll take the total, we'll divide it by 5. And then that'll give us the average of those grades there. So we can say clear here, we can compile it, we can run it, and we get an average of 83, which looks to be correct. And what's nice now is that this array could be like 200 integers long. It could be 2,000 integers long, doesn't really matter. And we can just programmatically with a loop go through it, total up the numbers, and then print out an average afterwards after we've calculated it based on the number of elements in the array. And so arrays are absolutely critical for writing programs that are going to scale to handle large amounts of data where we have like large collections of data, whatever it is. It could be student grades, could be like employee salaries, could be like city addresses, whatever it is. If we want to deal with large amounts of data, we're going to have to put them into arrays or possibly some other data structures as well, but typically something like arrays. And so just to be clear here, I can access and use these array values just like I can variables. So I could say here like grade 2 is equal to, we'll say grade 2 plus 5, and that'll change 72 to 77 by taking 72 and adding 5 to it and storing the result into grade 2. So if I do a recompile here and then run it, we see now grade 2 is 77 by the time we print it out. So I can use these here pretty much the same way I can my other variables, and that's okay as well. Another thing I should mention is how to initialize an array. So here we have like grade 5, and I've got like grade 0, 1, 2, 3, 4. There's a couple ways I can initialize an array. One way is I can say up here equal to, and then I can say my list of grades. So I can say like 92, 85, 72, 73, 95. And what happens is that these 5 elements here, these elements of my array, that's what we call these individual pieces of data in the array. We call them array elements. Those individual elements are going to be initialized to 92, 85, 72, 73, 95 in order from 0 to 4 there. So, I do a clear here and I compile it and run it, and we're going to get the exact same result as before. So this is another way of initializing our values. Now, if I do it this way, I can actually just take out the 5 here. And I can take out the 5 there because the C compiler will be able to determine the size of this grade array here based on the number of elements I've got here, based on the number of values I've got here, right? So it can tell like, oh, they've got 5 values, so make the array of length 5. So if I save this here and I recompile it and run it, this will also work okay. Now, one thing we might wonder about is like, well, what happens if I want to increase the size of my array? Like, what if I want it to be larger than 5? Or what happens if I access values that are outside of the array length? Like, what if I try to access the value at grade array index 6? What's going to happen? So we could try some of those things and see what happens here. Like, we've got here up until index 4, right? So we could try an index that's beyond that, like grade 5 or grade 6, implying that there's like 6 or 7 elements in the array. So let's try to do it. We'll try to say grade 5 is equal to, and maybe we'll say here 100. In programming, it's always okay to just try stuff and just see what happens. It's a good way to learn. So you're not going to break things. And if you do, it's kind of okay. The compiler's going to yell at you or the program might crash, but that's okay. Not a big deal. So we'll do a clear. We'll do a compile here, and we've got a warning. It says array index 5 is past the end of the array, which contains 5 elements. And so it's giving us a warning already. Now, if we try to run it here, it actually runs okay. So what's going on there? That we got a warning, but it's running okay. So what's happening there is that we're getting a warning because C can tell. C can tell that like you've only got 5 elements here. Therefore, this grade array is only being declared with 5 elements worth of space. It can only store 5 integers. But this will actually work sometimes because the way that C allows us to access data is a lot like, let's say looser than other languages. It's a lot less restrictive than other languages. C will let us try to do things, and it won't always generate an error. It won't always crash the program when we do. But what we're doing here is considered unsafe. That's why C is giving us a warning like that. Because technically speaking, our program doesn't really control this position here in memory. So remember, all this data is ultimately stored in memory. And so what's happening when we try to access index 5 is that all this data is laid out next to each other in memory. And when we say go access grade at 5, we're actually going to access the sort of next position in memory to where our array is. And there could be anything there. There could be any data there. But we're basically taking that spot in memory and we're putting 100 there. So we're accessing data that we really shouldn't be. And this could have bad effects. And that's why we're getting the warning. But C is an interesting language in that it will let us do that. It'll actually let us get away with that. And it just sort of trusts us to know what we're doing. So just be aware of that you can kind of do things with arrays like this, like go outside of the index bounds, go outside of the length of the array. And C might let you do that in terms of compiling the program, but you shouldn't do that in most cases unless you really know what you're doing, because you're probably accessing memory that you really shouldn't be accessing. So just be aware of that as well. So we could make arrays of any type we like. We can make float arrays and double arrays, but one special kind of array is a type of car array. So if we have a car array like this, we're going to say here car, and we'll say maybe my data is equal to, we'll say 5. I'm going to say my data at 0 here is equal to A. I'll see my data at 1 is equal to B. My data at 2 is equal to C. And my data at 3 is equal to D. And what we've got here now is a sequence of characters in memory. So we've got something that looks like this. We've got like here in memory, my data, and we have indexes. So we have the 5 indexes again, same as we had last time. So we're going to have here like 0, 1, 2, 3, and 4 in memory, right? And at index 0 here, we're going to have stored A, and then we're going to have stored at index 1 B, and then index 2C and index 3D. And these are the indexes here, and that's the data we've got stored there. Now what we can do is we can create a string. So strings in C are character arrays that end with a particular special character called the null terminator. So I'm going to say here, my data for is equal to \0. So \0, this is the special character null terminator, and this character signifies the end of the string. It's what ends the string. And so what we could do is we could say here printf, and I could say, my data at 2 is equal to %C, and we could output like an individual character like that. So we could say my data 2, we could output that individual character. And I could say like clear here and do a recompile here and run it, and I get, my data 2 is equal to C here. We could also do a printf though of the entire string. So I could say here printf, and I'll say %s, I'll say /n, %s, /n, and I'm going to output my data here. And this %s is the placeholder for outputting a string. And when I say my data here, I'm basically giving printf access to the entire array of data here. And printf knows now that the string ends at this character here because of the null terminator. And so it'll print up to the D basically. And so if I do a recompilation here and run it, I get APCD there. And so that's how to print out a string. That's how to define a string, is with characters in an array and a null terminator. Now, it would be a real pain if we had to specify all of our strings like this with characters individually and then a null terminator. So they give us shortcuts in C. So what we could say instead is this. I could say here char s1 is equal to, and I'll say this is my string. So I'll say this is my string, semicolon. And what C will do is it will actually create now a character array S1 that's big enough to hold all the characters, plus it adds room for the null terminator, and it puts a null terminator into the character array too. And so this is an easy way of initializing a string now. And you'd have like what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 characters here. So let's just do a double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 characters. Let's do a printf now of each one of these characters individually using a loop. I'm going to say here for int I is equal to 0, I is less than 18, I plus plus, and we'll do a printf now of each character. We'll say s1 %d is equal to %c. We'll output I, we'll output s1 at I. So we're doing what we've done in the past, which is outputting each element in the array, and we're outputting the index here according to the counter variable I, according to its current value. And then we're outputting the actual value here, the actual character here individually by accessing the array at each index. And we'll just throw a /n in there to get them on a new line. And so we could do a clear, we could do a recompilation, we could run it, and we get here, S1 is 0, S1 at 0 is T, S1 at 1 is H, S1 at 2 is I, S1 at 3 is S. And that makes sense, right? Because we have this as our first characters in the string there. Then we have a space character, so we can't really see it. And then if we keep going down, we're going to get to, my string at the end here, and that's it. And we could do a printf of the entire string at once. So we could say printf /n %s/n. And here what we're doing is we're putting in a new line. Then we're saying we're going to give you a string as an argument, and then a new line. And we're going to print S1 then. And we should get this is my string all printed out together. So do a recompile, run it, and we get this is my string all together there at the end. Now you'll notice that we didn't go up to the null terminator. So there's 18 characters here, but there's going to be a 19th character because of the null terminator, right? If I change this to 19 to go all the way up to that 19th character, remember that it's 0 indexed, right? So 0 up until 18 is going to be 19 characters. So if I were to go up to that 19th character, which is index 18, I get this. I get S1 at 17 is period. So S1 at 17 being period is not too confusing. But S1 at 18 is nothing. That's supposed to be the null terminator. What's going on there? So what's going on there is the null terminator is a non-printable character. So you can't actually see it. We could kind of force it though. We could kind of get around that here. So I'm going to make a loop body here now, a proper loop body. And I'm going to say here if S1 at I is equal to the null terminator. So this \0, that's the null terminator. It's a special character, even though it looks like it's two characters. And we've got like a single quote here, which makes us wonder, well, can we really do that? There's two characters here. I thought for, single quotes, we could only have one character defined. Well, this \0, even though it looks like two characters, like /n, it's really stored as one character, as one piece of data. This actually is valid because that's really just one character. And so we're going to say that if we've encountered the null terminator, which is going to happen when I is 18, right? Let's print it out especially. We're going to say here printf, and we'll say here null terminator. We'll say S1%D is equal to, we'll say NT for null terminator here. And I'll say here I. Otherwise, do the regular printf. So otherwise, do the regular printf where we're just going to print out the character as we did before. So we could clear this here, do a recompile and run it. And now you can see that, yes, when we did reach the 18th character, we were able to detect that that was in fact the null terminator. And we print out, that character in a special way here. We say S1 at %D is equal to, we put an NT for null terminator. So we could have done this instead. We could have said \0, and that would print out \0. So / is a special character in C strings, and it's used to do special things like print out a new line or things like a tab as well with /t, that'll give you a tab. And so if we actually want to print out / and not use it as a special character, you say \\. That's just the thing. People always forget too. I always forget. So / is this character, / is this character. I always forget that personally. So anyways, so \\, that'll give us a / and then a 0. And that would be a way of like actually printing this out on the screen. So we'll just do a clear and a recompile. And you see we actually get \0 printed out there as well. So, that's processing a string. Now, one thing that would be really nice is what if we could determine the length of a string? So right now, we're just sort of knowing that the string is 19 characters. We just know it because we just looked at it and we literally counted it out, right? That it was 19 characters when you include the null terminator. What if you don't know the length of the string you're dealing with? And that's something that might happen, right? Because maybe the user gives us a string and maybe we don't know the length of the string. So, what if we got something like this? What if I say here, I'm going to say here car, and I'm going to say here S1 is equal to, let's say 20 this time. Then I'll say printf enter to ask the user to enter a string. And I'll say scanf %s. Now here, instead of saying and S1, I'm just going to say S1. And what this is going to do is it's going to read in a string and store it into S1. And it will put the null terminator on there for us. Now, I don't put the and there, which is interesting. We're going to have to explain that later though, because that involves a bit of a more tricky concept called pointers. Now, we're just going to put S1 there and it is going to store the string that we put in into S1. And then what I'll do is I'll do a printf of S1 just to make sure we've got it correctly. So I'll say here S1 %s/n, and we'll output it just to make sure we've gotten it okay. So we'll do a clear here now, and we'll just do a recompile here and run it. So it says enter. I'm going to say my string here, and I get S1 my string here. I could say, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, what's happening here? Because I've got this like character array that can store up to 20 characters. And yet in the case here, you can tell that's clearly not 20 characters. There's only 10 characters there. So even if we include the null terminator, we've still only got like 11 characters, right? So we can store strings into character arrays that are larger than the string itself. So we could loop through this string here and I could say like for int I is equal to 0, I is less than, we'll say 20, I++, and we could do a printf of all 20 positions in S1. We could say here like S1 %D is equal to %C, and we're going to output each, position, each index in S1 here and its value. And if we were to recompile it here and we run it, we say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You'll see here we get like, this data here from 0 to 9. We get that S1 here is going to be the null terminator. We can't see it because we're not doing the special thing to print it out, but we know that's going to be the null terminator. And then the rest of the array is available to be used. You can tell there's some junk data in it. So we warned you about that. We said that, if we don't actually initialize our variables in C, there could be junk data in them. So there's some junk data in it there. But this means we can store things of varying length into S1. So I could say ./d, and I could say like enter. And this time I'll say like 0, 1, 2, 3, 4. And now you can tell that like I've got, 0, 1, 2, 3, 4 stored in there. That's going to be the null terminator, and the rest of it's blank. And I could say like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 0, 1, 2, 3. And, we've got now 0 to 9 stored in there, and then 0, 1, 2, 3, and then that'll be the null terminator there. So what's going on here is interesting for a few reasons. One is we can store strings of varying length into a character array. And what really makes the end of a string is not the length of the character array. What really signifies the end of a string is the null terminator being there. So we could write code to work with strings based on the null terminator being there. That could be one way we do things. So we could say something like this. We could say here like int I is equal to 0. And let's say we want to print out any zeros in the string. So anytime we find a 0, we're going to print out that we found a 0 in the string. So what we could say is this. We could say like while S1 at I doesn't equal the null terminator, keep going. And so long as S1 at I doesn't equal the null terminator, we're going to keep going. And we're going to say here like if S1 at I is equal to the character 0, we're going to printf found 0. And we'll just printf found 0 like that. And then we're also going to increment I each time in this loop here. So we'll say here I++. Okay. And then we can then find how many zeros we've got in our string by looping through it one character at a time until we encounter the null terminator here. So let's just give this one a try. We'll say clear, do a recompile, run it, and I'll put in like 0, 1, 1, 1, 0, 5, 0, 2. So there's 3 zeros in there. So we expect to be seeing found 0 3 times. And we get found 0 3 times. Then we get S1 and we get the rest of the string here. So if I want to process a string one character at a time like this to maybe search it for certain information or whatever it is I want to do with the string in terms of processing it, I could use the null terminator like this as a way of signifying the end of the string. And then if I want to give strings of different length, I could do that. So I could say here like 1, 2, 3, 0. I'm only going to get found 0 once. But this string is a different length than this string. And yet I'm able to process that okay with this loop, not really working with the length of the string. Really what I'm working with is the fact that we know that strings end with the null terminator. And so I go from 0, incrementing by 1 through each character of the string here. And we know that we're done when that character at I there is the null terminator. Now, with strings, some things can get messy just because of the fact that they are ended with the null terminator and not with, say, like a, array of a given length or something like that. So we could say here, let's run it here now. I'm going to say here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm about to put in 30 characters, but my character array here only stores 20. And look what happens. Abort trap 6. And we did get like found 3 zeros here. And we did print out S1 here successfully, but we get this abort trap 6. So we're not going to get particularly good behaviors if we don't respect the fact that our arrays can only store strings of a certain length safely. So now what we're doing here with checking for the null terminator, this will work, but there's other ways of working with strings. So strings are such a common thing to use in C and really a lot of languages out there that they give you another library. So this stdio.h library, pretty much every C program you ever write will include that because you're pretty much always going to want to print things to the screen and things like that. Now, another common library to include is the string.h library. So we're going to say here include string.h. So string.h is another library that comes with C. So like stdio.h comes with C, string.h comes with C, and you're always going to have access to it. And the compiler is going to know where it is and how to include it. Now, what string.h gives us is a bunch of functions for working with strings. Now, it would take too long to go over all of them, and I post different videos going over each of the functions individually and things like that on my YouTube channel. So I'd actually point you towards those, but let's actually go over some of them here. So let's make a string here now. We'll say here car S1, and I'm going to say it's equal to this is the way. So the string is this is the way here. And then what we could do is we could get the length of the string. So I could say here like int length is equal to, and I'm going to say strlen s1. So strlen, that's a function that comes with string.h. And if we include it, we have access to it. And what it does is it finds the length of the string. And it finds the length of the string without the null terminator. So it doesn't include the null terminator in the length of the string. So in the case of this string here, we expect it to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 characters long. So I could say printf here, length. And then we could output the length of the string here. So I'll say clear, do a recompile, and run it, and we get length 16. So then instead of writing a loop that works based on the null terminator being found, we could write a loop that works based on the length here. So we could say here like for int I is equal to 0, I is less than the length, I++, and we could do a printf here, or we could have it do some work. Like maybe we're going to have it count the number of i's in the string. So we could say like here int num i's is equal to 0. And then we'll say here like if the s1 string at I is equal to the character I, then we're going to increment num i's by 1. And then we'll do a printf here with the number of i's. So we'll say like number of i's, we'll say %d/n, and then we'll say here num i's. Okay, we'll do a recompile here. We run it, and we get the number of i's is 2, and that makes sense because there's 2 i's in there, right? And we could change it to another character like say h, and there'd be 2 h's in there. Or we could change it to say w, and we'd only expect 1 w. So we could say like num w. We'll say num w's now. Just to be consistent here, we'll change it to num w's everywhere. So we'll say number of w's now, and we should only find 1 w now. And we find 1 w. So we could write then loops to work with our strings that are going to maybe look at each character and do some kind of analysis, like counting the occurrences of a certain number of characters or something like that. And we can do it now based on the length of the string as opposed to, searching for the null terminator. Now, there's all kinds of functions that come with string.h. Another one that's interesting is called string cat, and this does string concatenation. So we could say here, I'm going to say here car S1, and I'm going to say here 50 is equal to the first sentence. Then I'm going to say here car S2 is equal to the second sentence. So what I've got here is 2 strings, the first sentence and the second sentence. And this is going to store this string into S1. This is going to store this string into S2. Now for S1, I deliberately made the array much larger than necessary to store this string. In fact, it's big enough that it could actually store both strings. And that's because I'm going to use the strcat function to concatenate the strings. And so the strcat function, the string concatenation function, is going to concatenate the strings. It's basically going to append this string to the end of this string. So we'll call it here, I'm going to say strcat, then I'm going to say s1, s2. And what this does is it takes this string here and it concatenates it on to the end of this string here. So it basically kind of takes off the null terminator from the end of this string and then puts this string from that position onwards. So then if I do a printf of S1 after doing this, we're going to get the first sentence and the second sentence. So I'll do a clear here, do a recompile and run it, and we get the first sentence and the second sentence, one after the other, because this function here concatenated this string onto the end of this string here. Now for that to work, it was really important that this array here was large enough to hold both strings. If that didn't work, it would be a bad time again, right? It'd be things that we don't want to happen would happen. Now, there's all kinds of functions in string.h for manipulating strings as well as comparing strings. And I'll just show you one more because like I said, there's just too many functions to show you all of them. And I'll leave those for other videos and your own sort of research. So what I'll say here is car s1 is equal to, and I'll say this is a string. Then I'm going to say car s2, and I'm going to say this is a string. If I want to compare two strings for equality to see if the characters in one string match the characters in the other string at each index in the string, that's what strcmp can do. It compares two strings and it'll return 0 if they're equal. So I could say like if strcmp s1, s2 is equal to 0, we could do a printf and we could say s1 and s2 are equal. And this will determine if they're equal. So we could do a clear here, do a recompile, run it, and we get S1 and S2 are equal. If there was something different about them, like if I had a character A here instead of, if I had a capital case A there instead of a lowercase a there, then what's going to happen is we're going to get they're not equal. So I'll say else, if we don't get that, printf, S1 and S2 are not equal. So we could run this now, and we'll just say like aren't equal here. Aren't equal. Okay, do a recompile here, run it, and we get S1 and S2 aren't equal there. And that's because there's a difference. Like this is a capital A, that's a lowercase a. And so this is another function we've got in this library that's super helpful because the function is going to return 0 if the strings are equal and something else if they're not. And so we can use that to help us write code to, determine if two strings are equal and maybe do things differently based on that result. Now, like I said, this library here is extensive. If we're going to go over all of it, it would take like, a couple hours to go over every single function in it and every single variation of every single function. But this isn't the only library. There's other libraries we can use as well that also provide other functions to work with strings and do things like math operations, do things like time and access time, the current system time, and things like that. So another library related to this string.h library is the ctype library. So we're going to include ctype here. And this is another library, and this one allows us to analyze characters. It allows us to look at characters and determine if they're lowercase or uppercase. So we could do things like this now. We could say here like car, and I'll say S, and I'll say like this is, and I'll say the, and then I'll say way. And I've kind of got a mix of uppercase and lowercase characters in here. One thing I can do is I can determine which characters are uppercase, which characters are lowercase. So I could say here for int I is equal to 0, I is less than, we'll say the length of the string. So we'll say here int length is equal to strlen_s. Then we'll put length here. Then I'll say I++ here. And we'll do a check to see if each character is uppercase or lowercase. So we'll say here printf, and we're going to output the character. So we're going to say printf will output each character one at a time. So we'll say printf %c, and then we'll say s at I. And then I'm going to say uppercase if it's an uppercase character, or lowercase if it's a lowercase character, or nothing if it's neither. So we're going to say here if is upper, and I'll say s at I. So is upper is a function that comes with the ctype library, and it's able to determine if a character is a uppercase character or not. So if I say is upper s at I, I'm checking each character in this array here as I loop through it to see if it's uppercase or not. And if it is, I'm going to printf, I'll say upper, and then /n. I'm going to say else if is lower s at I. Let's do a printf here, and I'll say printf lower. So I'll say printf lower. Else printf, just put a /n for a new line at the end there. So we're going to check each character now from 0 up until the length of the string, and we're going to print out each character. If it's an uppercase character, as detected by is upper, which returns true if it's uppercase and false otherwise, we're going to print out upper. If it's a lowercase character, we're going to print out lower. And if it's neither, we'll just throw on a new line. And then this will give us a printout of all the characters in the string and let us know if they're uppercase or lowercase. So we'll do a clear, do a recompile and run it. And we get T is uppercase, H is lower, I is lower, S is lower, I is uppercase, S is uppercase, T is lowercase, H is uppercase, E is lowercase, W is uppercase, A is lowercase, Y is uppercase, right? And characters like dot, like the period there and the space, they are neither uppercase or lowercase. So we don't get anything in terms of the output of it being uppercase or lowercase or whatever. Now, the other thing we could do is we can also use functions in this library to flip the case of the characters in the string. So we could look at each character and we could say, well, if it's an uppercase character, don't just print out upper. Let's actually flip it to lowercase. And there's actually a function called toLower that does that. So the way that function works is like this. I'm just going to comment out this code for a second here. I'm going to comment out this code. And what we'll do is we're going to say here, S at 0 is equal to toLower S at 0. So S at index 0 is the uppercase character T. The toLower function accepts a character as an argument. And what it does is it returns a value. It returns the character converted to lowercase. So it'll take an uppercase character and convert it to lowercase. If it can't do anything with it, then what it does is it just leaves it alone. And so this will take the uppercase T, convert it to a lowercase t. And then if I did a printf of S here, so we're going to say here S, %S, we'll output it. I'll do clear and I'll do a recompile here. We get this is the way with a lowercase t. So by applying this function here toLower to an uppercase character here at S0, I was able to convert it to a lowercase character. And what this does is this function returns a value. So far a lot of functions we've been using like printf and that, what they're doing is they're basically, printing out something to the screen or storing some data in the case of scanf. toLower, just like strlen, what it does is it returns a value. And in this case, what it's doing is it's returning a character. And basically this evaluates then to like the character lowercase t, and we store that character into S0 there. So what we could do now is let's actually go back to our loop code here. Commenting out your code like that, that's a common thing to do in programming when you're trying to figure things out, is you can always just sort of throw comments around a block of code to kind of temporarily disable it. And then when you need it again, because you want to maybe get back to fixing that part of the code, you can uncomment it to get it back to active code that's actually going to be compiled. That's a little technique you can use when you're programming too. So now let's actually, instead of just printing out whether the character is uppercase or lowercase, let's actually convert it to lowercase when it's uppercase, and we'll convert it to uppercase when it's lowercase. So I'm going to say here now, instead of printing out the characters, we're going to say if the character is uppercase, we'll say here S at I is equal to toLower S at I, and we'll convert it to lowercase now. So I'll put on the next line here. I'll say S at I is equal to toLower S at I. And then else if is lower, we're going to say S at I is equal to toUpper S at I. And I don't need this last case here now. So if the character is uppercase, we're going to take that character and we're going to make it lowercase, and we're going to store the result into that same position in the string. And then same thing if it's lowercase. If it's lowercase, we're going to take it, convert it to uppercase, and store that in that same position in the array. And then we can do a printf here at the end. We can say printf s, and we'll print out the resulting string here. And so if we do a compilation here and run it, we take this is the way formatted like this, and we output it like this. We could do a printf before and after maybe just to make it even clearer here. So we could say printf before, and then we'll do the printf after there. And then we can kind of see the before versus the after directly on top of each other. So you can see we took every uppercase character, made it lowercase. We took the lowercase characters, made them uppercase. And that's just a cool thing we could do now with the C-type library, which is another library that we can access and use in C. So we're using more and more functions now. We're using functions like string length here that accept a string as an argument and return the length of the string, and then we assign that value to length. We're using functions like toLower that accept the character as an argument, potentially modify it and return the modified character, which we assign to this, character array element here. And as we write programs that are larger and larger, it's going to turn out that we really do need to split them up into functions. And what we're going to do is we're going to create and use our own functions. And that actually really becomes necessary for a couple reasons, really. One is just that it's not practical to write all of our code for a complex program in the main function. At a certain point, we just sort of can't really think about or debug or read our program if we just have, say, like tens of thousands of lines in the main function. At a certain point, what we're going to want to do in order to make our programs comprehensible and understandable as a reader is to decompose them and to split them up into different functionalities that we then access as functions. And it's going to turn out, actually, if we go really far into programming, we keep going, that eventually we're going to make our own libraries of functions. We're going to make our own collections of functions. So in the same way we've got like this string library here, eventually what you'd end up doing is make your own libraries of functions and group together functions with a common purpose into a library. Now, what we're going to talk about in this little mini course here is how to make our own functions, because that's the first step, is we got to know how to make our own individual functions. So let's cover that now. Let's actually make and use our own functions. Now, another reason why we might use a function is because there's some task, there's some functionality that we want to carry out in different sections of our code. So finding the maximum of two numbers is not too tricky, right? Like if we have two numbers, we say int a is equal to 5, int b is equal to 10. If I want to find the max number between a and b, I can just throw an if statement in. I can say if, a is greater than b, we'll say that max is a. So we could say like int max is equal to 0, and we'll set max to a if a is greater than b. So we'll say max is equal to a, and then we'll say else max is equal to b. So if a is greater than b, we'll set max equal to a. Otherwise, we're going to set max equal to b here, right? And this is just a little two-line if statement here, right? But if I needed to do this everywhere in my code that I want to find a maximum number, that's going to get pretty repetitive. It's the same thing over and over, right? And it's going to increase the size of our code relative to just being able to say max AB and just getting a max value in return and setting it equal to max here. So we could say like maybe call it find max or something like that, right? We can make a function called find max that finds the max between A and B and returns the value. This is only one line of code. And it's pretty simple to understand what's going on here, that this would find the max between A and B and return that maximum value. So this is already shorter, and we're only talking about functionality that is very trivial, like finding a max number, very trivial functionality. Now imagine we have like 100 lines of code that does something, maybe does something more involved, like takes two strings and, finds the words that are most common between the two strings. And so it's a more involved function, right? Something like that. Imagine we've got to put the code for that all over the place in our code. That's going to be a mess. So what makes far more sense is that for these sort of things that we want to repeatedly do all over the place in our code, we package them together in a function that we can just sort of call to carry out that functionality. So let's go over how to make and use one of these functions here. So the first thing we'll do is we'll create a function here. I'm going to make a function called findMax. And at first I'm going to make it up here. I'm going to say int, and I'm going to say findMax. Now I'm going to say here int a and int b. So what this is this is my first function here. And this is the function name. So that's the name of the function. These are called the parameters of the function. So these are basically variables that are going to be local to this function. So these are variables that I'm going to be able to use and access inside this function in the same way that when I had like int I with my for loop, and I was then able to access the integer I inside the for loop. Same idea with these, where A and B are going to be accessible inside the block of the function in the same way I here is accessible in the block of the for loop here. And so these are going to be parameters, they're called. But what's going to happen is when I call the function, I'm going to pass it specific arguments. So I'm going to give the function specific arguments, and A and B are going to be set to those argument values, to those specific values. And then this here int, that's what's called the return value. So we're going to return a value from this function, and then we could then say assign that value to a variable, or maybe use that value in an expression or something like that. So all this function is going to do is it's going to look at A and B, and it's going to return the maximum value of A and B. So I'm going to say here, if A is greater than B, return A, else return B. So it's a simple function. Now what I'm going to do is I'm going to use the function. I'm going to do what's called calling the function, and I'm going to use it inside of main here. So I'm going to say here, int max is equal to find max, and I'm going to say here 10 and 5. Now 10 and 5, these are considered arguments. So these are things that I'm passing to find max. We would say that I'm passing the values 10 and 5 to find max. And when find max executes, the control flow is going to jump up here now. The control flow is going to jump into this function now. And when find max executes, A is going to be set to 10 and B is going to be set to 5, because that's the argument values I've got here. I've got 10 and 5. So A is going to be set to 10, B is going to be set to 5. Then we're going to check, is A greater than B? Yes, it is, right? So we're going to return A. And at that point, what's going to happen is this function call here is basically going to evaluate to the value 10, because that's the max value between the two. And then max will be set to 10. And so when we call a function control flow, the execution of statements is going to jump to that function, and it's going to start executing the statements in that function until it encounters a return value in the case of a function like this that is returning a value. So this function here is returning a value. And so the expectation here is that the function will eventually have a return and then some value here. And so we could then say printf max, and we could printf the max value that's returned. So we can say max %d/n, and I'll print out max, and we'll see what we get. We should get 10, but we'll just give it a try here. So I'll say clear, do a recompile and run it, and we get max of 10. Now, if I change this to 12 here, I'm going to get a max of 12 if I do a recompile and run it. And what's going on there is that, again, the function is called. This time, though, A is going to be set to 10, B is going to be set to 12. The statements in the function are then going to execute with that assumption, with those values, right? And so we're going to get now that, 10 is not greater than B. This is going to be false. So we go down here to the else case, and we return B, which is set to 12. And that's why we get 12 back from this function call. And that value gets assigned to max, and then we print it out. And so that's the basic idea behind a function, is that we call it to do some work, and typically a function will return a value. Doesn't have to. I'll show you in a second an example of one that doesn't, but it doesn't have to return a value, but it typically does. And when it returns a value, we actually use it here and in an assignment, and we assign that value to max. Now we could use the value returned by the function in an expression. So we could say something like int, we could say here result is equal to find max, and we'll say plus 10. And this should take 12 then and add 10 to it. And we could say, let's print out result now. And we're going to get here, we should get back 22, right? Because we're going to take 12 as the max value here. And then we're going to add 10 to it. So we should get back 22 now for a result. So we can run it there, and we get back 22. So we can use the return value that we're going to get from calling the function however we like, really, in an expression, and that's fine. One thing that's important to understand is how variables work when we call a function. So we need to talk about what's called variable scope. So variable scope is basically where a variable exists and which variable will be accessed when we actually go to use a variable name. So for example here, the result variable, because it's declared inside of this block here, it exists within this block. And so we actually can't use the result variable inside of find max. Let's see what happens if I try that. If I try to say here printf, and I'll say, let's say result %d/n result, we'll try to print out result. This is not going to go well. So I'll do a clear here, I'll do a compile, and I get error, use of undeclared identifier result. And it's pointing me towards that exact line there. And what's going on here is that the result variable, the one that I'm using right here, just doesn't exist inside of find max. It just is not a thing there. Same thing with A and B. So A and B, those are called parameters, and parameters have the scope of this function here. And therefore we can't use A and B in main. So if I try to say like printf, and I say like A %d, and I'll say B %d, and then I'll try to print out A and B, we're gonna get a similar thing here. It's not gonna go very well. If I do a clear, I do a recompile, we get two errors now. We get like error use of undeclared identifier A, and we get error use of undeclared identifier B. So these variables here, we would say that they have local scope or they have function level scope. So like A and B, they have the local scope of this function here. We would say they have function scope. You could say local scope or function scope. People will know what you mean if you use those terms. The result variable here, same thing. It has function scope. It has the scope of the main function. In other words, it can be seen in the main function. It also has what we'd call like local scope. So you could say local scope 2, same idea. Now with variables, so long as we're just sort of mentioning this, we can't use them before they've been declared. So I can't use result up here. I couldn't say like printf result before it's been declared. That also will not work. So long as we're talking about variable scope, we might as well talk about that. So one thing we've got here is we've got the find max function defined above main. Now, typically this is not what you do when you're writing a C program. And the reason is if we've got like maybe let's say 12 or 20 or 30 functions defined in this file, we've got to then scroll down quite a bit to find main, right? Because it's going to be kind of buried underneath all those function definitions. And so what you actually typically see is the function definition split up into two parts. What's called a function declaration and then a function definition. So we can split it up like this. I'm actually going to take this here. I'm going to copy it. But here I'm going to leave one little piece. I'm going to say semicolon, and I'm going to delete the function body here. We call this the function body. I'm going to delete that. And I'm going to leave this here. We call this the function definition. And this is defining what the find max function is. It's saying that the find max function is going to accept two int values as parameters, as arguments, and it's going to return an int value. And this is the function definition. It basically tells the C compiler that yes, when you see the find max function being called, it's okay to use it because the definition for that function is going to be provided later. Then down here, what we do is we provide the definition. So down here, we provide the definition for the function and we define find max, we give the function body. So we repeat this same sort of function prototype it's called here, the function declaration here. We basically repeat the same information from the function declaration. And we then provide also the function body at that point. And this is actually considered the more normal format for defining functions in a C program. So we can clear this and compile it and run it, and we'll get the same result as before. And all that's happened is we've split it up. And the idea here is that I could then have like, maybe let's say like, 10 definitions here, but I don't have to scroll down too far to find the main function, which is probably the thing I want to look at first. And then if I do want to look at any one of these function definitions, I can always find it in the file down here. And so this is actually the typical style to be used when you're actually creating functions in a C program. So it's very important that we understand the relationship between these arguments here and these parameters here. So let's go over an example to do that, just to make sure we understand it, because if we don't, we could really run into trouble with our program logic and being able to figure out what's going on. So I'm going to make a function that's going to triple a float value. So I'm going to say here float triple, and it's going to triple the float value that it's given. So I'll say here float n. And there's my function declaration. Now let's provide the definition down here. I'll say float triple, and what I'm going to say here is n is equal to n times 3. Then I'm going to return 0 here. So I'm tripling the number, right? I'm taking n and I'm multiplying it by 3 and I'm storing the result in n. And I can just return 0, right? Because I've already tripled the number. And then what I'll do here is I'll say here float x is equal to 5. And then I'll call triple. I'll say triple x, and then I'll printf x just so we can see it after we're done. So I'll just say printf, and let's just printf what we get for x now. And I expect that we should get, 5 times 3 is going to be 15. So I'll clear this here. I run it, and I get 5. So what's going on here? So what's going on here is that what is passed to the triple function is not x. It's not like we're passing like x on some kind of deep level where then n is really able to then modify x. What's actually happening is that the value of x is being passed, and the value of x is 5.0. So it's actually as if we had done this. It's as if we had passed in 5.0 here. And this variable here, n, it has no relationship to x, other than the fact that it gets passed that value. It's not like it's somehow tied to x, so that when we modify n, we're going to modify x. And it's really important that we understand that distinction here. So we can pass it x, but what we're going to have to do to modify x is return n here. Because at this point, when the function runs, n is set to whatever the value of x was, which is 5.0. And then from that point on, n has nothing to do with x. So we say, n is equal to n times 3. We can modify n, and then we can return n, and that's fine. But unless we actually take this return value and use it in an assignment statement, it's not like it's going to modify x. So we'd have to say like x is equal to triple x to actually have it modify x. So we can compile it here and run it, and now we get x15. Functions can also have their own local variables. So I can make a function here called add. So I'm going to say here double, I'll say add, and I'll say double x and double y. And this function is going to add x and y together. And I'll provide my function definition down here again. And my function definition is going to look like this. I'm going to say here double result is equal to x plus y. Then I'm going to return the result. Now this is a simple function. I could just say actually instead, I could just say return result. But if I want to, I can also create my own local variables inside this function here. And result would be a variable that's local to this function. It's a variable that has the scope of this function. So it would only exist inside this function, but I can create it and I can assign values to it and I can use it how I like inside of this function body here. Now let's just give this function a quick test here. I'm going to say here printf, and I'll say %f, and let's output the result of adding together. We'll say 10.5, and we're going to say here 5.9. So what I'm doing is I'm actually calling the function right inside my printf here, because ultimately printf is being told expect a floating point value or a double here with the %f placeholder. And then what I'm doing is I'm providing that value by calling the function, because I've called the function with 10.5 and 5.9. And then ultimately what happens is the function returns a value, and I'm using the value as the value for this placeholder here now. So we can do that as well. That's totally legal in C. And we can then clear this, give it a quick test here and run it. And I get 16.4, and that makes sense given the numbers we've got there. So another thing we can do with functions is we can define functions that call other functions we've defined. And we can kind of have a chain of functions like that are using each other. So let's actually make now a mult function. I'm going to say here double, I'll just change this one. I'll say double mult, and I'll say here double mult, and I'll make it short now. I'm just going to say return x times y. So return x times y. You could even put it on one line, just so you know. You could technically do this. You could technically say return x times y, and this is legal. This will basically take in a variable x, a variable y, it'll multiply them and return the result. And we've just got our block on one line. And this is actually okay. We can actually do this in C. So then next, I'm going to make a power function, and I'm going to have it use my mult function to actually implement its behavior. So I'll say double power, double x int n. And this function is going to compute x to the power of n. So if I call it with like 3 and 3, then it would be 3 times 3 times 3. If I call it with like 2 and 4, it'd be returning 2 times 2 times 2 times 2. So we'll do the function definition down here now. And what I'll do is I'll make a result here. And the result is initially going to be x. And what I'm going to do is I'm going to assume that the power function is being called with a value of n that is 1 or greater. So n is going to be at least 1 or greater. And what I'll then say here is for int I is equal to 0, I is less than n, I plus plus, we're going to actually then compute, or actually I'll change this to 1 here. I'll change that to 1. I'm going to say here, let's compute the power by using mult. So I'm going to say here, result is equal to mult result by x. So I'm going to basically keep on taking the result, which is initially x, and multiplying it by x. And I'm going to do it from 1 up until n. And then we'll return the result here. So we'll return the result. And then let's test this function out. So let's test out our power function here. So let's say printf, we'll print out the power here. And I'll say power of, let's say 2 to the power of 3 first. And we'll give it a first little test here. So I'll clear this, recompile, run it, and I get 8. So it seems to be working. Let's give it another try here though. Let's say power of 2 to the power of 1. And that should be then 2. It should just be 2. And we just get 2, so that seems okay. And we'll just try something else here now. We'll try like 5.8 to the power of, let's say 9 here. And we'll just give this a compile here, run it, and we get a very large number here. And that does seem to be correct though. So that's now an example of having one function that we've created use another function we've created to carry out its work. And as we write programs that are larger and larger, we're going to find that this is what happens. We get this sort of decomposition into a chain of functions that use each other and call each other to carry out the work they've got to do. Another type of function we can have is what's called a void function, which doesn't return a value. So let's actually get rid of these ones here. We'll make a void function now. So I'm going to make a function that's going to print two numbers. I'll call it void print2, and it'll take in maybe float A and float B, and it'll print out two floating point values here. And we'll define the function down here. So we'll say here void print2 float A float B, and it'll just do a printf of these two values. So we'll just say printf %f, and then we'll do a new line, %f, a new line, A and B, and we'll print out the two numbers. And then I could define two floating point values. I could say like float x is equal to 2.5, float y is equal to 4.2, and then we'll call print2. So we'll say here print2, and we'll pass it x and y. Now if I do a recompile over here and I run it, we get 2.5 and 4.2 printed out. And the big difference between a void function and other types of functions is there's no return statement. So we just don't need a return statement with a void function. I believe if we try to put one in, we're going to have a bad time. I believe the compiler will complain about that and say error void function print2 should not return a value. So void function basically means a function that does not return a value. And we might use that if we want to print things out or maybe accept some input from the user or something like that that doesn't actually involve returning a value. What about passing arrays to a function? How does that work? We can do it, but it works differently than when we pass these sorts of parameters here, just regular variables like these. And I'll show you what I mean here. So we're going to make a function here that's going to add 1 to every element in an array. So we'll call it void add 1 int array. So it'll accept an array as a parameter here, as an argument here. And then we're going to say here int length for the length of the array. And then we'll provide our function definition down here. And we're just going to have a loop that's going to add 1 to all the elements in the array. So I'm going to say I is equal to 0, I is less than length, I plus plus, and I'll say array at I plus equals 1. So I'm not going to provide a proper thing like this, proper body like this for the for loop, because I can fit it on one line, and because it's a simple thing, I'll just stick it right there on one line. But basically what we're doing is we're taking every element of this array here from 0 up until, but not including the length of the array, and adding 1 to it. And this should kind of raise some alarm bells for us, because we said that you couldn't modify parameters. We said that you couldn't modify things like this before, right? But here we're apparently depending on it, because it's not like our function is returning an array or something like that. So let's see what happens here. I'm going to say here int, and I'll make an array called A, and I'll say it's equal to, we'll say 2, 4, 9, 1, 3, 5. And we've got 6 elements in the array. So I'll call the function add 1 with A and 6. So I'm passing it the array A, and I'm saying it's got a length of 6. Now let's do a printf of all the values in the array. So I'm going to say here 4, int I is equal to 0, I is less than 6, I plus plus. We'll do a printf. We'll say printf array, or we'll say A, %d is equal to %d slash n, will output A, I will output A at I. And just doing our usual printout of an array here. So let's see what happens here now. We'll do a clear, run it, and compile it. And look what we've got here. A0 is 3, A1 is 5, A2 is 10, A3 is 2, A4 is 4, A5 is 6. And they've all been incremented by 1. And so in the case of an array, somehow what's happened is that we've actually affected the array A in this environment here, main, in which we called the function. So like when we passed A to this function here, somehow this function is able to actually modify A in this environment here in main. And then when we loop through and we print it out, we can see that things have been updated, right? Because like A0, it should be 2, but really A0 is now 3 after we've called this function. So something has happened here that we don't understand. So what's going on here is that memory addresses matter a lot more in C and come up a lot more in C than they do in other languages. So what is A? We know A is an array, And we know that we can access the elements of the array with this syntax here. But when we just say a like this, and we just pass a to this function here, add 1, what is that really? So it turns out that this is actually going to be a value, and the value is going to be a memory address. And we could actually print out the memory address of a. So I'm going to say here, printf, I'll say printf, and then I'll say a colon %p/n a. And let's print out a, and not like an index of a, not like an element of a. Let's print out a itself. And this %p, that actually stands for pointer. What it stands for is a memory address. And we're going to print out the memory address that is this value of a. So a is ultimately a memory address, and we're going to print it out here with this %p. And we could save this here, and we'll just do a recompile here and run it. And we get that a is this number here. And this number here, there's some letters in there, but that's because it's a hexadecimal number, but it's really just a big number. That number is a memory address. And it turns out that's the memory address where this data is stored in the array. And what we could do is we could also print out here array. So we're going to print out array in the same way. I'm going to say printf, and I'll say here array %p array. We'll save this here, and then we'll do a clear, recompile, and run it again. And I get that a is this number here, and array is this number here. And look, they're the same. 234900, 234900, they're the same number. So what happens here is actually something pretty special, and something we're going to have to talk about to make sure we really understand C and how to program in C. And that is that a here is really a memory address. It's really the memory address where this data here is stored. And when I pass a to the function here, add 1, what I'm not really passing is the values of this array. It's not like I'm passing in the values 249135. What I'm passing to the function add 1 when I give it the argument a is actually the memory address of this array here. And so the value that gets passed is the memory address of the array. And so this array here, int array, it is also going to be referring to this same array in main. Now, regular variables don't behave like that. Like if I just had a variable like int x, and I set it to 5, and then I pass x to a function, so I could say like add 1, and I could say like a5 or something, or ax here. At that point here, we'd only be passing the value 5. So regular variables like x are not going to behave this way, but arrays are. With arrays, we're going to be passing in not the values 249135. The value we're passing is actually the memory address, this thing here, where a is stored. And then when we go to use the array in this function here, we're actually using that same array in memory, and we're accessing the same array in memory when we access it like this and we modify the values of it. And that's a really important property of C. So the next thing we've got to talk about is how C works with memory with what are called pointers. So pointers are one of the most important concepts in C. They tend to be a tricky concept. So let's go over it piece by piece here. So let's say we've got a couple variables in memory. We'll say like int a and int b. And we say that int a is 5 and int b is 10. So these have been described as boxes where we store values, right? Like a and b are both sort of boxes in memory where we store values. Well, every box in memory has an actual address, kind of like a street address. So we've got, say, like variables here, like a and b, and they have some value, right? So they have the value, let's say 5 and 10. Each of these variables also has an address. So each variable is also stored at some address in memory. And it's literally just how the computer sort of organizes itself, that memory is stored at particular addresses. So, variable a here, we could say this is stored at address like 55. And then b here will be stored at 56. Now addresses usually look kind of uglier than that. They're usually some longer number like this because your computer has all kinds of memory. It has tons of memory in it, and therefore the addresses are these very long hexadecimal style numbers. But we could just say for simplicity that A is at address 55, B is at address 56. Now, sometimes, as we've seen with the array that we were passing to that function there, C actually works with these addresses. Sometimes C actually passes around and manipulates and does computations involving these addresses here. So that can be done with what's called a pointer. So a pointer looks like this. I'm going to say here int star p. So int star p, what this is saying is make a variable called p. So it's going to make a variable called p. But a stores an int and b is going to store an int. That's the type of thing that these variables can store. This here, int, it might make you think that p is going to store an int. What p actually stores is a pointer to an int. So p actually stores a pointer, and it's going to store a pointer to an int. So p also has some address itself, like p does have some address, but it stores not an int, it stores a pointer to an int. So what does pointer to an int mean? Pointer to an int basically means that p stores a memory address. So whenever you hear the term pointer in C, a pointer stores a memory address. So we could say, for example, that p is going to store b's memory address. So we can do that like this. I can say here p is equal to and b. So the last time we saw this was when we used scanf. We use that and there. Now we can tell you what it is. So the and operator means get the memory address of this thing here. So go get its memory address. And so what happens is we're going to get the memory address that b is stored at and store it in p. And that's what p is going to store. So the value that p stores would be b's memory address. And because p is storing b's memory address, we would say that p points to b. That's where the terminology pointer comes from. We would say that p points to b. It's sort of got this association here where p is storing b's memory address, and therefore we can actually use p to access b. And that's why it's kind of important that we know the type of the thing it's pointing to. So the pointer here, p, the expectation is that it is going to be pointing to an int value. So again, the memory address that p is going to be storing, that should be the memory address for some int value. And the reason why we need to know that is because we might actually want to access that value. And we can access that value by doing what's called dereferencing the pointer. So here, I'm going to say here printf, and I'm going to say here %d, and I'm going to dereference the pointer. So I'm going to say here star p. So star p, this is another operator. And this one, this star here is different than this star here. We use this star to declare a pointer. This star here is used in a different way. It's what's called dereferencing the pointer. And when we dereference the pointer, what we do is we go get the value at the address that p is pointing to. So that's probably the most confusing part of pointers. When we dereference a pointer, we go get the value that p is pointing to. In other words, we don't get 56. We go get at the address 56, the value that is there. So p is storing some address, and when we dereference the pointer, instead of getting 56, we go to address 56 and we get its value. So this should actually output 10 here because p has been set to store the memory address of b, and then star p means go get what's at that memory address, go get the value at that memory address that p is storing. So we go to address 56 and the value there is 10, and that's what we print out. So let's actually clear this here, recompile it and run it, and we now get 10. And we could use this operator wherever we want. So we could say something like this. We could say like, well, a is equal to a plus, and we'll say here star p. And so this will go get 5 and add it to whatever p is pointing to. P is again, pointing to the value at address 56 here, and therefore it's going to go get 10 when we dereference it like this. And so we get 5 plus 10, and we assign the value to a, and then a should now be 15. So we'll print out a next. We'll say printf, and we'll print out a here. We'll say a colon, and we'll say here %, or we'll say here a here, like that. And then we'll just do a recompile here, run it, and we get that a is 15. So we can use these dereferenced pointer values wherever we like, wherever we could in an assignment or an expression, and we'll get the expected result there. So I could always change what p is pointing to, for example. Let's actually print out what p is pointing to. Let's say printf, and we're going to say here p colon %p. So %p is what allows us to print out a memory address. So I'm going to say %p, and I'm going to print out the value that P is storing here. And when I use P like this, without the dereference operator, without the star operator there, then all I'm going to print out is whatever P is storing. Just like if I said like B, I'd be printing out the value of B. Here I'm printing out the value of P. And the value of P, what P is storing, is some memory address, right? And we'll do the same thing for B. I'll say printf, and I'll say this time and B colon. So I'll say and B colon, and I'll say %P/n, and I'm going to print out and B. So remember, the AND operator goes and gets us the memory address of this variable here, of this thing here. And so what it's going to do is it's going to get us the memory address of B. And we're going to print out that. We're going to print out that memory address. We're using %P to print that out. And so this, because we assigned AND B to P, we should get the same value here for P and for AND B, just to show that, P is in fact storing B's memory address. So we'll do a recompile here, run this, and we get that P is storing this memory address, and the memory address of B is this memory address here. We could also go get the memory address of A, so we could say here and A, and I'm going to say here and A, and then we could print out A's memory address as well. So we could do a recompile, run it, and there's A's memory address. Notice that they're very close. Notice that the numbers are very similar here. Like this memory address for B, it's almost identical to the memory address for A, just slightly different here at the end. And that's because of the way that C creates variables. When C creates variables in a function like this, it's going to be creating them with this sort of stack type structure where each variable gets created next to the previous variable that was created. And that's how these types of variables are created in C. So we could also change what P is pointing to. So I could say here like P is equal to, we're going to say and A now. And now P is pointing to A instead. So if we did a printf again of P, we would find that now it's going to be storing whatever A's memory address is because we used and A to get the memory address of A. So we'll say here, clear, recompile, run it, and we get that P is now storing A's memory address. So we're getting P is now storing A's memory address. And so what we could do is we could then manipulate A via P. So what I could do is I could say here star P is equal to star P plus 1. So what's going to happen here is we're going to go get what P is pointing to, right? The value of A. It's going to be 5, right? So now, instead of storing, say 56, P is now storing 55, right? And we say star P, we go get what P is pointing to, which this time is A, and we go get its value. So we go get 5. And then we're going to say 5 plus 1, and that's going to be 6, right? And then we're going to take that result. We're going to take the result of this expression, and we're going to store it into star P. So star P is not, the value, the variable P. Star P is what P is pointing to. And so we're going to go get this result, and we're going to store it at what P is pointing to, which is A, and we're going to store then 6 there. And we'd increment it to 6. And so if we did a printf of A after this, if we said printf, let's print out A, and not the address of A, the value of A. So we're going to print out the value of A here. We should get 6 now. So we run it after this, and we get A6. So again, like we set P to point to A. So P is now storing A's memory address. We print out P, we see that P now stores the same memory address that A is located at. And that makes sense because we just stored it there. And then we say star P plus 1, and this goes and gets what P is pointing to, which is A. Go gets that value there. And we add 1 to it, we get 6, and we store it at the memory address that P is pointing to. That's what star P does. It gets us access to that variable that P is pointing to, and we store 6 there. So then when we go to print out A, that's why we get A6 there. And so pointers are these powerful tools that we have in C. This ability to access and use memory directly is one of the reasons why people might refer to C as a more low-level language. So even though we said C is a high-level language in the sense that it's higher than machine code, a lot of people would say that C is a bit of a lower-level language. And one of the reasons why they would say that is because you can access memory directly like this. So one of the useful things we can do with pointers is to do what's called pass by reference, or more accurately, pass by pointer. So we're going to make a function here called void, and we'll call it add1, and it's going to take in a pointer here. We'll call it A as an argument. So it's going to accept a memory address as an argument. And what we're going to have this function do is add 1 to the variable pointed to with this pointer here. So we'll provide the function definition down here. And what we're going to say here is star a is equal to star a plus 1. And what we're going to do is we're going to add 1 to whatever a is pointing to. So here we're going to make a variable here called, let's say b. We're going to set it equal to 5. Then I'm going to call add 1, and I'm going to give it the argument and b. So what I'm doing here is I'm making a variable called b that's an int, setting it to 5. And I'm giving the memory address of b to this function here, add 1. Now it takes in a memory address. That's what int star a is. It's a memory address, right? It's a pointer to some int variable. And that's exactly what we're giving it here. So then what's going to happen is this add 1, when it's called, is going to be given the memory address for b. It's going to access that memory address with this dereference here, with this dereference operator. It's going to say like star a, which is really going to be a memory address for b, right? And so it's going to access that value and it's going to add 1 to it, and it's going to store it in that memory address for b. So we're actually going to modify b in this calling environment in main where we call add 1. So we could printf b afterwards, and we're going to find that it's now going to be 6. So we'll just print it out. We'll do a clear, recompile and run it, and we get b6 now. And this is what's called pass by reference, or more accurately called pass by pointer, because what we're actually passing here as a value is the memory address of b. And that's why this function is actually able to access and modify b in the main function here. Now I say pass by pointer is more accurate, but pass by reference is the more common terminology people use for describing what we're doing here rather than pass by pointer. So you'll typically see that term used. So we could just printf and b and printf the value of a here just to make it more clear what's happening. Let's do a printf of and b. So I'm going to say here and b %p/n, and I'm going to print out the memory address of b. And then here, let's do a printf of a. So I'll say printf, and we'll say a colon %p/n, and we'll print out a. So here I'm going to print out the memory address of b. That's why I have the %p here. And then I'm going to print out the memory address of a. That's why I have the %p here. But for a, because it is a memory address, because it is a pointer, pointers are just memory addresses, we're going to just say a here instead of and a. So we'll recompile this, run it, and we get that and b is this memory address, and a is this memory address. So what's happening when we say star a is we're actually accessing this memory address. We're accessing the value there, and we're able to manipulate it. We're able to use it in an expression. We're able to assign to it. And it's, again, just the same view as before, where you've got like basically some kind of variables in memory, you have some kind of address, and you have some kind of value, right? And we have a variable here, b, and it's got some address, whatever it is. It could be like, 72. And it's got some value, and the value is going to be 5, right? And then when this function gets called, what's happening in memory is that a variable is being created, and it's called a. And a is a pointer, and b is an int. And what's happening here is that a is going to store the address for b. So a is storing as its value the address for b, right? And we would say that a, in this case, is pointing to b. And it happened when we actually passed in this argument here, and b. That's when we passed in the address for b, right? And then just like any other parameter variable, it gets set to that value there. And so a is storing b's memory address. And when we dereference it, we're saying, go get what's at that memory address and use it. So we go get the value 5, we use it in the expression here, we turn it to 6. We go get the memory address here, and we store the value over here in that memory address. And that's what's going on there. And this aspect of C is called pass by reference. And it's important because what it lets us do is write a function that could then modify multiple variables in the environment in which that function is called, which is a pretty powerful tool. So I could say here like int star b, int star c, and we could then modify 3 variables in the main function or whatever other function is calling add 1 at one time, at a single time here. So let's actually make these 3 variables now. Let's say here int x1 is equal to, we'll say 1, x2 is equal to 2, x3 is equal to 3. And then we're going to make our add one function modify all three of these variables. So I'm going to say here add one int star a, int star b, int star c. And I'm going to say here star a is equal to star a plus 1. I'll do the same thing with b and c. So I'll say here b and c. And then when I call add one, I'm going to give it three memory addresses now. I'm going to give it x1, x2, and x3's memory address. I'll say add one and x1 and x2 and x3. And then we'll do a printf of each one of these afterwards. We'll say x1 %d, and I'll say here x1, and then we'll do the same thing for x2 and x3 here. So I'll say x2 and x3 as well. And what I've got here now is the ability to modify three variables in the main function by calling one function. So we do a recompile here, and oh, I forgot something here somewhere. So it says line 17 here. So I'll go to line 17 and see what I forgot here. So, oh, I forgot. I put a semicolon on the end there. I gotta take that away. It must have happened when I copied it from the function declaration up top there. So we'll do a recompile, run it. And I get x1 is 2, x2 is 3, x3, that should say, is 4. So we're now able to modify three variables here. I changed x1 from 1 to 2, x2 from 2 to 3, and x3 from 3 to 4. And I'm able to modify all three of these by calling one function. And that's a pretty powerful feature now, because before I was really limited to one return value. And if I can only modify one thing at a time, like only have one return value that maybe I assign to something in main, that's going to be very limiting. But instead, I can now modify as many things as I want in this calling environment here where I call the function using this pass by reference technique. So let's circle back and talk about arrays again, because we said that in that one example, the array was really a memory address. So let's actually kind of talk about that again and see what we mean by that. So let's make a function again. We'll call it void add one again. And I'm going to say here int array, and we'll kind of recreate that function we had. We'll say void add one. We'll add a length to this actually. We'll say here int length. And then we'll copy this, throw it down here, and we'll make it so that it adds one to the array again. So we'll say for int I is equal to 0, I is less than the length, I plus plus, we're going to add one to the array. We'll say array at I, we'll say plus equals 1. And we'll call this function again with an array here. So we'll say here int A is equal to 1, 2, 3. We'll call add one with A and a length of 3. And then after it's done, we'll just print out the values of A after calling it. So we'll say I is equal to 0, I less than 3, I plus plus, and we'll just do a printf of A. So we'll say printf A %d is equal to %d / n. We print out I, we print out A at I, and we're printing out the array again after we call add one in the main function here. So we'll just give this a quick compile here and run it. And we get A0 is 2, A1 is 3, A2 is 4, and we had given it 1, 2, 3. So this function has successfully added 1 to all of the array elements again. And we said that this behavior here was because the array that we're really passing in here, A, is really a memory address at this point. So what's going on is something we can describe better now. So when we use an array like this, just A, just like that, with no, open bracket, close bracket to access an index, we say that the array decays to a pointer. That's the terminology we use. We say that the array decays to a pointer. And what we're really passing then is the memory address that these values are stored at. It's sort of the first memory address actually of this first element here that we're passing. And add one is then going to actually accept that memory address. And this here int array is then actually going to be referring to that same space in memory. It's going to be referring to that same position in memory. And that's why when we modify the array, it actually modifies A in the main function here. So it turns out what we could do is we could actually say here, instead of int array, open bracket, close bracket, like it's an array, I can say int star array. And then down here, I'm going to say int star array. We're going to do a recompile now. And when we run it, we get the exact same result. So what's going on here? I've now actually got a pointer here. I'm not just saying that we can sort of treat an array like a pointer or that the array is behaving like a pointer. I actually have a pointer here now and it's working. So what's going on here then? It turns out that we can very often treat arrays like pointers and pointers like arrays. Not always, but very often. So let's actually go over that a little bit here. Let's actually create a pointer here, p. So I'm going to say int star p. And I'm going to actually have p point to the first element in this array here by saying p is equal to a. So remember that a is the memory address of the array. It's the memory address where the array data is stored. And A is really the memory address of this first element there, because that's where the data begins, right? Like if you had the array in memory, you'd have like some address for each position. You'd have like address, and you have like the index 0 would be at a given address. And so you'd have like index 0 would be at some address 55, let's say. And then maybe index 1 would be at 56, and then index 2 would be at 57. And then you have different values at each address. So you could have like value, and you could have like 1, 2, 3. And that's kind of what it looks like in memory, is the data in the array is all next to each other in memory, in subsequent memory addresses, in contiguous memory addresses, right? So you got like 55 would store 1, 56 would store 2, 57 would store 3. And when we use an index for the array, when we say like A1, what we're essentially saying is at the memory address of A, go over 1 and get the value there. If I said like A2, we're saying like, okay, at the memory address where A is stored, go over 2 slots and find the value there, and we get 3. So that's actually how the indexing is really working. So when I say here, P is equal to A, what I'm doing is I'm actually creating a variable P. So I've got some variable P now, and P has its own address, whatever it is, like 58 or whatever, right? And it's then storing 55. So P is basically becoming a pointer that points to the first memory address in that array, whatever it is. We're going to say 55 for whatever reason, could be any number. And what we could then do is we could actually then access these array elements using P. So if I say this, if I say printf and I say %d/n, and I'm going to say here P0, and we're going to do a clear here, and we'll do a compile here, and we run it, I get that P0 is 1. If I said P2, then it's actually going to be 3. And what's happening is that when I use this notation here, I'm using what's called array notation to specify what value I want at this memory address shifted over by this many indexes. So that's actually what's called array notation. And typically you're using array notation with things that you've declared as arrays, but we can use array notation with pointers as well, because what it's really saying is like at this position in memory, which is going to be 55, right? So at this position in memory, let's say 55, shift over by 2 and get the value there. And that's what's really going on there. So P at this point is really just storing the same memory address that A is. So if we said here like P:, we're going to say %P, and we'll print out the memory address that P is storing. And we'll say printf A:, %P, and we'll print out the memory address that A is storing. They're really the same thing. They're going to store the same memory address, right? So they're the same thing because we basically said assign the memory address that is A to P. We don't have to say and A here because A being an array, really A is the memory address. It's only when I say like 1, am I saying go get the value at that memory address shifted over 1, or A0 would be like go get the value at that memory address. And so when we say P is equal to A, we're actually assigning the memory address where this array is stored to P. And then I'm accessing it here the same way I do when I access A, because they're really actually the same thing. So if I said here like printf, and we'll say here A2 is equal to %d, and I'm going to say here A2, I'm actually really accessing them in the same way. And I'm using what's called array notation to do it. So we're going to get, P23 and A23, and they work the exact same way because they're both really just the memory address. And when we say like P2 or A2, what we're really saying is from that memory address, get the value that's shifted 2 slots over, shifted 2 positions in memory over. So that's actually why in this function, this works. Because yes, array here is a pointer, but that's kind of what it was all along, right? It was always a memory address that we were passing. And when I say here array I, we're doing the same thing we are here. It doesn't matter that it's a pointer or an array because functionally at this point, they're the same thing. It's a memory address. And when we say like array at I, we're basically getting the right index starting at that memory address. Now, this is what's called array notation. There's also what's called pointer notation. So pointer notation is another way of getting at values that are kind of shifted over from a given memory address. So pointer notation looks like this. I could say here printf, and I'm going to say here star, and I'll say p plus 1, and then I'll say is equal to %d/n. And then over here, I'm going to say star p plus 1. So this is called pointer notation. It's also called pointer arithmetic because we're adding 1 to this pointer value here, p. And what this is going to do is it's going to go get, using the star operator, it's going to dereference the memory address of the pointer shifted over by 1. So because like the pointer here stores the same memory address as the first element of the array here, it's got that memory address of the first element of the array. When I say plus 1, it shifts it over 1, and we're going to get value 2 here. So we could then say printf star p plus 1, and we could say clear here. We could run this. And for star p plus 1, we're going to get 2 because we're basically saying like from the first value in the array here, add 1 and shift over by 1, and then we get 2. And this star operator kind of dereferences that position in memory. So p plus 1 basically says, go get the next slot in memory, like move over by 1 slot in memory. And then the star operator says, go get the value in memory at that spot. So this is kind of shifting over by 1 spot in memory. This star operator dereferences that spot in memory, and we go get the value at that spot in memory. And I can do the same thing if I said printf star p plus 2 and star p plus 2, and I can also get at the third element of the array with star p plus 2 because we're shifting over by 2 spots now in memory. I can also use pointer notation with arrays. So I could replace p here with a, and it'll be the same thing. I could just say like a, and a here, and then this will actually shift over from a. But a, remember, just holds the same memory address as p, right? So it's actually going to be the same thing. We can clear this, we can compile it, and we can run it, and we get a plus 1 is 2, and a plus 2 is 3. And all that's happening is the same thing. We're basically saying get the memory address of a, shift over by 1 memory address, and then the star operator takes that memory address and gets the value there. So, if we said star a plus 2, what's going to happen is the a plus 2 is going to say, take that memory address, go over by 2 positions in memory. Then the star operator dereferences it and says, go get the value 3. And that's why we print out 3 here for star a plus 2. And that's called pointer notation. And when we use this sort of arithmetic here by saying like pointer plus and then some number, we call that pointer arithmetic. So at this point, you might be thinking like, what's the difference between arrays and pointers? It seems like we can use them interchangeably. So you can't always use them interchangeably. So for example, like one thing I can't do is I can't assign values to a. So my array here, a, I can't treat it like a pointer and assign values to it like this. I couldn't say like a is equal to p, right? If I try to do this, if I do a clear here and do a recompile, I'm going to get an error here. It says array type int is not assignable. And so I can't change a. I can't change what memory address a is storing. And that's a big difference between arrays and pointers. So this pointer arithmetic here and this pointer notation, generally speaking, when possible, I try to avoid using it because it tends to confuse people. But there are some situations here and there where it does become useful. And I'll show you one example of that. Let's say we've got our array here, int a, and we're going to make it bigger. We're going to say like 4, 5, 6, 7, 8, 9, 10. So it's storing 10 values now in a there. And we've still got our add one function here, right? That accepts as an argument an array or a memory address, a pointer, which are all kind of, we're learning pretty similar things functionally. And what we're going to say this time is when we pass a to add one, I'm going to use pointer arithmetic. So I'm going to say here A, but then I'm going to say plus 5, and then a length of 5. So what's going on here is when I pass the memory address A to add 1, I'm going to shift it over by 5 positions in memory. So instead of passing in the memory address for this first element here, I'm shifting it over by 5. So it's going to be 1, 2, 3, 4, 5 over. And it's actually going to be the memory address for this element here that I'm going to pass. And then I'm only going to pass in a length of 5. So it's actually only going to work then with this back half of the array, because add 1, it doesn't know anything about this array so much as it knows it has a memory address, right? Like add 1 doesn't know about the length of this array beyond what we're telling it here. All it really knows is it has a memory address here, which is actually going to be a memory address now for this element here, 6. And when it accesses the memory address with this array notation saying like array I, what it's really doing is shifting over from that memory address by the index given here, right? So it's going to shift over like 1, 2, 3, 4, up until but not including 5, right? And so if we then do a printf of the values afterwards, we're going to find that only the back half of the array has been updated. So I'll say printf here, we'll say a %d is equal to %d, and we'll output I and a at I. And we'll just do a clear, recompile, and run here. And look at this, only the back half now has been updated. So we get to 5, and then at what would be, the value of 6, we've now got 7, 8, 9, 10, 11. And the back half of the array has been updated, but not the front half. And that's because we use pointer arithmetic here. We said that instead of passing to this function the memory address of this first element in the array, we shifted that memory address over by 5 using pointer arithmetic. So instead of that, we actually passed in the memory address for 6. And then when this array notation is used to access different indexes in the array here, what's really going on is we're just basically shifting over the memory address that we're accessing. So we're going to access 6, then 7, then 8, then 9, then 10. And we only go up to a length of 5, so it's not going to go past 10, right? And so then what we've got here is a practical application of using pointer arithmetic to alter the portion of the array that this function is actually going to alter and modify. Another big application for pointers in C is what's called dynamically allocated memory. So let's go over that. Regular variables in C, they exist on what's called the stack. So when I make a variable A and I set it to 5, and I make a variable B and I set it to 6, what happens is, like we've explained already, they get created in memory, right? There's some position in memory, some address that's set aside for A and B. And you have like variable A, variable B, and there's some memory address for them, and there's some value, right? And we said like addresses could be whatever we want. Addresses could be like 12, 13, and the values here could be 5 and 6, let's say. And this is what's called the stack. So this is what's called the stack. And it's called the stack because as functions are called and as we create different variables, they basically stack next to each other, on top of each other in memory, we can think of it as, and that's why it's called a stack. And if we have main call some function, so if main calls some function, and maybe the function is defined here, and the function also creates some variables here, like C and let's say D, and maybe we'll change it to like 8 and 10 here, then those are also going to be placed on the stack. So like main would call func, and these variables would then also go on the stack, and you'd have like C and D. And then these would be at like memory addresses, let's say 14 and 15, and you'd have the values for these variables. You'd have like 8 and 10, and this is called the stack. Now with the stack and the variables all being next to each other in memory, what happens when we create an array like this, like if I said here int e10, what happens is that this here is also going to be placed on the stack. So you'd have like e would be the next variable on the stack, and you'd have like e0, and e0 would be at address 16 here, and the value could be whatever we set it to. We could set it to whatever we want, right? And you'd have like e1, and this would be at address 17, And you have some of their value here, whatever it is, right? Whatever we set it to. And then this would go on up until E9. And at that point, that would be like what? I guess it'd be 25 here. That would be, another spot in memory there. You'd have some value there. And then if we made another variable here, we'll say int f is equal to maybe 9. That would then be, again, another variable on the stack, this time at address 26, and value whatever we set it to. We set it to 9, so it's going to be 9. Now, because of the way the stack works, with variables stacking on top of each other in memory, essentially we can think of it as, or maybe we say beneath each other in memory, either way we want to think of it as. With variables stacking on top of each other like this, what's going to happen is we can't modify the size of an array. We can't later say, you know what, we want to make E an array of size 11 now. We can't resize it and say like E is actually going to be an array of size 11 now. We just can't do that because the next position in memory, is going to be occupied by F, right? So we can't just sort of enlarge E. C doesn't allow us to do that with variables that are created like this. And that's where dynamically allocated memory comes in. So dynamically allocated memory allows us to create blocks of memory that we could actually resize later if we want to. And sometimes that's important in computer programs to be able to dynamically create and reallocate different sizes of memory. So with this here, like we're limited. Once we've made E an array of size 10, that's it. We're beat. We can't change it because the next position in memory is occupied by the next variable on the stack. With dynamically allocated memory, it doesn't work like that. So one other thing I should say about the stack, just for your own curiosity's sake, when this function returns and it's done working at this point here, these variables basically get eliminated from the stack. So like the stack would kind of be reduced back down to this, because at that point, this function's returned and all these variables that were doing a lot of work inside this function, they're no longer needed. And the stack kind of gets reduced back down to whatever variables were in main at that point. So that's just one thing that's interesting to know about the stack. Now, dynamically allocated memory, where that's going to exist is what's called the heap. And the heap is basically a special place in memory that actually is, we can think of as being at the bottom of the big block of memory our program has. And the stack is at the top of that big block of memory. So the heap is actually down here and the stack is up there. And the stack grows downwards, the heap grows upwards. So the heap is actually kind of down here in the big block of memory. If you think of the addresses just going on and on forever, like 14, 15, on and on forever, the heap is at the bottom and the stack is at the top. The stack grows down. The heap is going to grow up. But the heap is a little bit different though too, because the heap actually doesn't necessarily contain blocks of contiguous memory in the same way the stack does. And we'll kind of get into that as we talk about dynamically allocating memory. So if we want to dynamically allocate memory, we're going to have to use a couple functions that are included in a library called stdlib. So we're going to have to include, in addition to stdio.h, we're going to have to include stdlib.h. And stdlib.h includes a few important functions: malloc, calloc, realloc, and free. So what I can do to create dynamically allocated space on the heap is I have to use malloc or calloc to do that. So what I'm going to say here is int star a. And a is going to be a pointer to that block of space that I'm going to dynamically allocate. And so a is going to contain a memory address, and it's going to contain a memory address for that data on the heap that I'm going to create space for. So when I say a is equal to malloc, malloc is a function that goes out and actually creates and allocates that block of space on the heap for us. And what I'm going to say here is size of int times 5. Now what this is going to do is it's going to tell it, go out and create space for 5 integers. And size of int is going to return the number of bytes that it takes to store an int value. And when we multiply it by 5, that's going to have the effect of giving us enough space to store 5 int values. Now what malloc is going to return is the memory address of this block of space on the heap. It's going to return a pointer. And that's why we're using this int star a to actually store that pointer. So a is a pointer, a is going to store the memory address. A is going to store the memory address that malloc returns for that space on the heap. And we have to give it the number of bytes on the heap that we want. So you typically see code like this, like size of the thing that we want to store multiplied by the number of things of that type that we want to store. And once we've got this, we're going to have what's called a dynamically allocated array. So a can actually store 5 int values. And we could say here like a0 is equal to 1 and a1 is equal to, we'll say 5. a2 is equal to 7. A3 is equal to 9, and we'll say that A4 is equal to 11. And then we could loop through A and we could print out these values. We could say like for int I is equal to 0, I is less than 5, I++, and we'll do a printf of all these A values here. So I'll say like A%D is equal to %D, and we'll output I and A at I, and we'll get these values here. So once I've gone out and allocated this space, I can use array notation to access all the different indexes of memory that are available in that space to set those values and print those values and do whatever I want with them as I could any other kind of block of memory on the stack. So we'll do a recompile here, and we get A0 is 1, A1 is 5, A2 is 7, A3 is 9, and A4 is 11, which makes sense given that's what I set the values to here. And really all we're doing is we just got this block of memory, we have a pointer to it, and we're accessing it with array notation. So somewhere on the heap, we basically have, A0, A1, A2 on down. Now, obviously, in a real situation here, we have much more than this meager amount of memory here. The stack and the heap are, as a practical matter, going to be separated by a lot of memory addresses. So there's a lot of memory typically available when you're working with C nowadays. And the difference in memory in terms of the addresses in memory between the stack and the heap, we can assume is a very, very large space. And so don't worry about the stack somehow colliding with the heap. And as we create more space on the heap, more blocks of memory on the heap, they tend to be created right next to each other. But depending on whether there's things already on the heap or not, that's not always the case. So we can't depend on that. Now with malloc, when we use malloc to go get this block of memory, it actually doesn't do anything to somehow clear the data that was there. So when we use malloc, say, and we get this block of memory here for A, there could be values in there already. There could have been values in there that are just garbage values like 55 and, 67 and just all kinds of different values in there, right? And there's nothing that would have prevented that with malloc. Malloc just goes and gets that block in memory. It doesn't do anything to clear that space and somehow make it blank for you. That's what calloc does. And calloc works pretty similarly to malloc. With calloc, we're going to say this. We're going to say calloc, and it's going to return a pointer to a block of memory that's been allocated. And instead of one argument, for some reason they decided to do it like this. You actually give 2 arguments. You say the number of things that you want to allocate space for, and then you say as the second argument, the size of those things. So if we want to allocate space for 5 integers, we say 5 as the first argument, and the second argument would be the size of integers. Now when calloc returns a pointer to this block of memory here, it's going to set all those values to 0. So it sets all the values in that block of memory to 0. And the advantage here is that we're then dealing with basically clean memory, we could say. We know what's there. Now, calloc does come at a cost, because what happens is, in addition to what malloc does, like going out and allocating this space for us, calloc actually has to go through and set all those values to 0 to ensure that they're 0. So calloc is actually going to be a more time-consuming function than malloc to use as a result. And we just have to be aware of that. Now with calloc, we're going to get the exact same results, mind you. If we save this here and we do a clear and a recompile here, the results will be the exact same. So calloc just basically ensures for us that the memory is actually going to be clean to use. It's going to be all zeros initially when we go to use it, so we know what is there. Now, whether we use calloc or malloc, one of the important things we need to do whenever we dynamically allocate memory like this is to free that memory after we're done with it. So we're going to say here free A. And what free does is it takes this block of memory and it makes it available again. It makes it available again for other calls to calloc or malloc to allocate that memory. So it basically takes this block of memory and it doesn't delete the things here. So like if there was content here, like if there was just some random content here, it doesn't do anything with it. It actually just leaves it alone. It keeps it there. But what it does is it makes this space here in memory, it makes it available again. So other things could then allocate that space and use it for whatever they want. And that's actually really important that we remember to free it. If we don't free it, what could happen is what's called a memory leak, where we don't actually have access to the memory to free it in the future, because maybe we've changed the pointer or something like that, and we've lost track of the original memory address, the original pointer to that space. And at that point, we have a memory leak where we have memory that's been allocated, it's been set aside for storing data, but we can no longer free it either. The other thing that can happen is we can just run out of memory. So if we just keep on allocating more and more memory and never freeing it, we can just run out of memory. So that's another problem that we can have if we don't free our dynamically allocated blocks of memory. So we always have to call free, and we always have to free the memory we've allocated. The fact that we need to do this manually is why people say that C has manual memory management, where the programmer has to manually manage memory, manually set aside the memory and allocate it, and manually free it. And that's in contrast to languages like Python and Java, where when those programs are executing, there's essentially a process called a garbage collector. And what it does is it checks to see, is there any variable in memory referencing a block of memory that's been set aside? And if there's no longer any variable that's referencing a block of memory that's been set aside, then what happens is the garbage collector automatically frees it for you. And so a lot of people would say that Python and Java are actually easier languages to program in. Now that garbage collector actually does take time. That's a process that's running, right? So it takes time. And so that's why C, some people would say, has higher performance. And these are the sort of trade-offs that we get into when we talk about whether to use one programming language or another. So one of the big reasons why we would use dynamically allocated memory, as opposed to just say making an array of length 5, is that we can actually enlarge the space that we've allocated. We can actually use realloc to go out and allocate a bigger block of memory. And it's sort of like if we had an array and we could just make it bigger. And that's one thing we can't do with regular arrays that we declare on the stack. So let's actually go over an example of that here. I'm going to say here int star numbers, and numbers is going to point to a block of memory where I'm going to store integer numbers. And what I want to do is I want to find the average of numbers that a user inputs, but I don't want to limit the user in terms of how many numbers they can input. So I want to be able to theoretically accept as many numbers as the user is willing to enter. So I'm going to use dynamically allocated memory to actually keep track of a block of memory, and I'll just make it bigger using realloc if I ever need a bigger block of memory. So what I'm going to say here is numbers is equal to malloc size of int, and I'm going to say times 2 initially. So I'm going to say that this block of memory is initially going to store 2 int values. But what I'm going to do is I'm actually going to keep track of the size of this block of memory in terms of the number of ints it can store. So that way, if the user is going to enter in more numbers than the size of numbers we can store, I can then increase the size and reallocate a larger block of memory for this data here. So I'm going to say here int size is equal to 2. Then I'm going to say size here instead. Then I'm going to say down here free numbers after I'm done with it, just to make sure that I remember to free up the space after I'm done working with it. And then what we're going to do next is we're going to continually ask the user for input. And we're going to say that when they enter -1, that's when we're going to quit. So I'm going to have a int value here called input. It's going to be an int variable called input. That's going to have an initial value of 0. And I'm going to say while input doesn't equal -1, keep going in terms of asking for more input. And we're going to say here printf, and I'll say like enter, and I'll say, -1 to quit. And we'll just ask the user for numbers again and again. And we'll then scanf the value and we'll store it in input. So we'll say scanf %d, and we'll store it in input. Now you know why the and symbol's here. Just a reminder of that this is actually giving the memory address of input here, right? And that's why scanf can actually modify this value, this variable here, in the calling environment here. And then what we'll do is we'll keep track of these numbers in this space here that we've allocated. And I'm gonna have to have some kind of counter variable to keep track of how many numbers we've actually accepted so far. So I'm gonna say here I is equal to 0. That'll be my counter variable for keeping track of how many numbers I've actually accepted so far. And I'll say, okay, numbers at I is then equal to the input value we just got there. Now, if the input is ever -1, that's when we want to quit. So we're only going to do this if the input is not -1. So if the input doesn't equal -1, then at this point, we're going to actually store the inputted value into this number space here. Now, the other thing we're going to have to check at some point is we're going to have to check, have we stored so many numbers that we're now equal to the size of numbers we can store at this space? Because at that point, we're going to have to reallocate more space. We're going to have to allocate more space to store the numbers that we want to store. So let's actually zoom out here for a second, just so we can fit all this in here. And what I'm going to have to say then is, okay, if input doesn't equal -1, we've stored at numbers I input, we'll increment I. So we're going to increment I, so that way we've kept track of the fact that yes, we've stored another number here. And then here I'm going to say if I is equal to size. So if I is equal to size, what this means is that we are going to attempt to store a number beyond the capacity of this block of memory to store numbers. Because if I'm going to store a number at like numbers index 2 here, right? Then that would be the third position in this block of memory here. But I've only got 2 slots of memory allocated. So if I ever equals the size, that means that we're about to go beyond what this block of memory can hold. So what we're going to do if that's the case is we're going to increase the size by 2. We're going to say size plus equals 2. And then we're going to realloc more space. So I'm going to say here numbers is equal to realloc numbers. And then I'm going to say here size of int times, and we'll say times size. So times size there. And we're basically then saying like, okay, go get more space for this data block here, numbers. And it should be the size of an integer times our new size. And what's going to happen is realloc is going to go out and increase the size of the block of memory allocated to store this data here. And what it typically does is it actually just enlarges the existing block. It just sort of makes it bigger. Sometimes what happens though is it can't make it bigger. It can't make it bigger because there's other things next to it in memory. And if that's the case, what realloc will do is it'll actually copy all of the data in the block that was, say, originally allocated by malloc. It'll copy all that data to a new place in memory that has this increased size. So if realloc can't just sort of make the existing block bigger because there's other things next to this block of memory already, it'll actually find a new place in memory that is this size and then copy everything in that old block to that new block in memory. So realloc basically makes our dynamically allocated array bigger, and now we can store numbers up to this increased size that we've increased by 2 here. So when this is all done, what we'll do is we'll actually loop. We're going to create a loop here. And I is actually, at this point, the number of elements we've stored here. So we could say here like int num elements is equal to I. And then we'll make a loop here. And we've already used I as a counter up here. So I'm going to say here for int j is equal to 0, j is less than num elements, j plus plus. So I'm going to use j instead of I because we've already used I up here. And what we'll do is we'll add each one of these numbers here to a total. So I'm going to say here like int total is equal to 0. And then I'm going to say here total plus equals numbers at I, or numbers at j, because we're using j as a counter variable. I'm used to using I, so I kind of went to that automatically. And then we'll do a printf and we'll find the average. So we'll say printf, we'll say average, %d/n, we'll do total divided by the number of elements that we found. And this here is basically handling the inputting of the numbers. This here is handling finding the average of those numbers, and then we're going to print it out. So let's actually clear this here. We'll do a recompile, and then when we run it, we can put in as many numbers as we like. So I can say 5, 10, 15, 20, 25, then I'll say -1, and we get an average of 15. And what's going on here is that even though I only allocated space for 2 int values, whenever the number of values we've entered equals the size of space we have allocated, we increase that size by 2, and then we reallocate space for that new size here. So after we entered 10, the next time through the loop, when we get to enter 15, at that point, space for 2 more int values is going to be allocated. And we can actually throw in a printf here just to make that explicit. We'll just kind of throw in a printf just to make it very clear what's happening here. We'll say printf realloc for %d, and we'll say ints. And then we'll say here size. And we're basically then going to say like reallocating space for this many ints now. And we'll kind of print out the new size there, just so we can keep track of what's happening here. So we'll do a clear, we'll run it, and now we'll say 5, 10, and then we get realloc for 4 ints. I say 15, 20, realloc for 6 ints, 25, -1, and I get average 15 again. And what's happened is, each time through the loop, once we've actually reached the space that we've got, whether it's 2 or 4, the next time through the loop, we recognize that. We say that like, okay, we've entered as many numbers as we have space for, go allocate more space, and we reallocate more space. And when we do the reallocation, it's not like it blows away whatever was in memory. Whatever was in memory is still going to be there. So these values we've stored, they're still there in that resized block of memory, in that resized dynamically allocated array. All that's happened is that realloc has just sort of enlarged the space, or if it can't enlarge the space where it is currently, what it does is it, like I said, it copies it to a new location in memory, and then it just kind of continues on there. And that is realloc. And it's a very powerful tool because now we can dynamically create and use and expand different sizes of memory in our program, which really opens up the possibilities of what our programs can do. 2 other really important concepts for working with data in C are called typedef and struct. And we'll go over those next. So we'll just get rid of this code here. So typedef and struct allow us to essentially define and use new types. So I'll zoom in a bit here so we can just sort of make the code bigger again. And typedef and struct, they basically allow us to make new types. So what I can say here is typedef int, and then I'm going to say inches. And what typedef does is it creates a type synonym for int called inches. In other words, I can use inches as a type now. And when I use inches as a type, what it's going to be creating is an int value. So then what I can do is say here, inches person1 is equal to 181, and inches person2 is equal to 179. And what's going on here is that when I use inches, it's a synonym for int. So really it's like if I said int person1 and int person2. Now the reason why we'd use typedef is because in theory, using inches here is going to improve the readability of our code because it's more accurately stating what this type of information is that's going to be stored inside person1. And we could then say like printf, and we could say person1 %d/n, and we'll output person1's height, and then we'll say printf person2 %d, and we'll output person2's height. And we can use %d here because person1 and person2 fundamentally are just int variables, and so that's why we can use the int placeholder just fine with them. So if we then save this, do a clear, and recompile this here, and run it, we get 181 for person1 and 179 for person2. Now that's typedef, and typedef is about making a type synonym. It's about making a name for something. Now it's often used in conjunction with struct. Now struct is a tool that allows us to group related information together. So a struct allows us to group together information that we might call a record of information. And that's in contrast to how arrays allow us to group together information. So if we have like an array of grades for a class, we might say like int grades and then have like 30 people in the class. So we're going to have 30 potential grades here. And we can store a collection of grades in an array like this, and that's okay. But what about a student? What if we want to store the information for a student? A student has a first name. A student has a last name. A student has an age. A student might have a student ID. Those pieces of information, if we want to store them together in one unit that we can reason about, that's where struct comes in. Struct allows us to group together data like that to form basically a record of information with different fields. So let's say I use struct to define a new type for points in 2D space. So I'm going to say here, struct point. Then I'm going to say int x and int y. Because if it's a point in 2D space, then it's got an x coordinate and a y coordinate, right? And we're going to have then points that exist in some kind of xy 2D space. And when I say struct point, I'm basically creating a new type of thing called point. And I can actually make points by saying struct point. I can declare points by saying struct point. So I could say here, struct point p1. Now, points are going to have two pieces of information associated with them. They're going to have an x value and a y value. So I could initialize these values by saying p1.x is equal to 5 and p1.y is equal to, let's say, 3. And what I'm doing is I'm initializing these values here, x and y, that each point is going to have. So if I have a point struct, it's going to have a x value and a y value associated with it. And we call these members. We would say these are members of the struct. And they're kind of like fields in a record. And so when I say p1.x, I'm initializing this point's x value to 5 and this point's y value to 3. And then I can access these variables with p1.y and p1.x. So I could say like printf, and we could say like open bracket %d close bracket, and I'll output p1.x and p1.y, and I'll output it in this sort of tuple type format, almost as if it is a point in 2D space. So I'll clear this, recompile it, and run it, and we get 5 and 3. And what I've basically got access to now is these two variables, x and y, that are tied to this specific point struct here, p1. And it's basically like I've got this new type of thing. So I could make another point. I could say here like struct, and I could say point p2, and then I could then have a point variable p2. So I could say like p2 x is equal to 10 and p2y is equal to, we'll say 4. And then I could print out these values too. So I could print out, p2x and p2y. So I could say p2x, p2y here, and we'll output those values now. And we get 10 and 4. So I can make as many of these as I want. And that's basically how a struct works. Now we can initialize these values here. We can initialize these variables here in a couple different ways. One way I can do it is like this. I could say struct point p3 is equal to, and I'm going to say here 1 and 2. And then we're going to do a printf of p3x and p3y. So I'll say p3.x and p3.y. And watch what happens here. So I do a recompile, I run it, and I get 1 and 2. So this syntax here, it's kind of like the syntax we use to initialize arrays, but this time we have this struct here, p3. So what happens is these values get assigned to the struct's members in the order that they were defined up here. So like x would get 1, it would get initialized to 1 because it's the first member that's defined up here. And then y would get initialized to 2 because it's the second member that's defined up there. And this is one way of initializing a struct. Another way to initialize a struct is to use this notation here. I'm going to say here struct point p4, and I can say this. I could say here dot y is equal to, we'll say 7, and I'm going to say dot x is equal to, let's say 6. And then I'll do a printf of p4. And we'll say p4.x and p4.y. And we'll do a recompile and just run it again. And we get 6 and 7. So what's going on here is that I can use this dot notation. So I can say open squiggly bracket, close squiggly bracket, and then I say dot, the name of the member, is equal to, and I initialize it to something. Or I can say dot, the name of the member, and I can initialize it to something. And we can then initialize these members out of order. So I initialized y first to 7, and then x to 6. And it's kind of out of the order that they were actually presented up here. And that's fine. We can do it with this style of syntax there for initializing struct values. So one thing that's kind of a pain with struct is that I have to say struct and then the type and then the variable name here. And that's just an extra thing, right? It's an extra piece of text there, an extra keyword to use. What would be nice is if I could say just like point p4 and just make the variable. And we can use Typedef to help us do that. So let's actually delete this stuff here. And now I'm going to say here, Typedef struct. And then down here, I'm going to say point. So what I'm doing here is I'm saying for this struct, give it the name point. So Typedef struct, and this defines the struct, and then give it the name point. And then I can say things like point p1 is equal to, and I could say here like dot x is equal to 6 and dot y is equal to 9, and we could printf the point here, and this will work. So we can just say point instead of struct point. So we could just say here like p1.x, p1.y, and we'll get the expected behavior here when we recompile it and run it here. We get 6 and 9 there. And so that is a way of using Typedef and struct together to just sort of simplify this creation of this new type here. Now, one thing I could do with Typedef and struct is I could also have things like arrays and pointers and strings as my struct members. So let's just say instead of point, I'm going to make a student type now. And we're going to say that students are going to have a first name. So let's say car first name, and we'll say like 50 characters, and we'll say car last name, and we'll say it can hold 50 characters. And then we'll have like an age. So we'll say like age as well. And students can then have a first name, a last name, and an age. And I can use the student just like I'm using point here, but with first name and last name to initialize those values, I might want to use some kind of string copy method to do that. So what I'm going to do is I'm going to include string.h, the library again for working with strings, because this library includes an strcpy string copy function we can use to set up a student's first name and last name. So I could then say like student, and I could say like s1, and then I could say s1.age is equal to, let's say 20. And then for setting the first name and last name, I'm going to say strcpy, and I'll say s1.firstname here, and then I'll say, let's say Devin, and then we'll say strcpy, I'll say s2 last name, and then I'll say Smith. And then we've got here a student s1 that has members age, first name, and last name that we've initialized to 20, Devin, and Smith. And we could print out this student's information as well. So we could say here like printf, and we'll say like first name, maybe we'll just do it like this. We'll say %s/n, %s, and we'll print out the first name and last name. So we'll say s1 first name, and we'll say s1 last name, and then we'll print out their age. So we'll say printf, and we'll say age %d, and we'll print out s1 age. And we could then clear this, compile it, run it, and we get Devin Smith, age 20. Now I can also pass a struct to a function. So we can make a function that accepts a student as an argument and does something with it. Maybe it prints it out or something like that. So we can make a function declaration up here. We'll say like void print student, and it's going to accept as a type a student. So I'm going to say here student, and we'll say student s. And what I'm going to do is, because I defined student here, I'm actually going to make sure that I put this function declaration here beneath the typedef. So that way the student type has been defined when I actually use it here. Then I'll copy this, and we'll provide a function definition down here. And what I'm going to do is I'm actually just going to copy this. So I'm going to copy this out, put it down here, and I'm going to say s.firstname, s.lastname, s.age. And we'll print out the student that's passed to this function here, print student. So then up here, what I'll do is I'll call print student. So in my main function now, I'm going to call print student, and I'm going to give it the student here, s1. So S1 is going to be passed to this print student function here, and then it's going to print out the student details just like it did before. So we're actually going to get the same output here. So if I do a recompile and run it, same output as before. Just now what we're doing is we're passing this student here to this function. So now one question, and this would be a great question, is this a pass by reference? So like if I modify the student's age here, is it going to be modified in the calling environment here in main? So is it passed by reference or is it passed by value? Are we actually passing in the values for this struct here? So let's actually give this a test. Let's actually try to change s.age. So we'll say like s.age is equal to, let's say 25 now. And then outside of this function, in the main function, we're going to do printf, and we'll print out the age again. So we'll say /n age %d /n, and we'll print out s1 age. So we'll give this a recompile and run it, and we get age 20. So maybe it's not too surprising that an int value behaves like that, but what about one of these character arrays here, first name and last name? Before, when we were passing arrays to functions, we determined that they were passed by reference. But what about when that array is part of a struct like this? Let's see what happens. And whenever you're unsure about how something's going to work, just messing around with a code like this and just doing an experiment, it's always a great way to learn. So I'd encourage you to do that. So I'm actually going to change the first character in the first name to K, so it'll be Kevin Smith instead of Devin Smith. And then we'll do a printf up here of the first name and last name in addition to the age. So we'll say like /n, and we'll print out the first name and last name in addition to the age for S1 here. So I'll save this, clear this, do a recompile and run it. And we get Devin Smith age 20, Devin Smith age 20. So modifying the character array in the function here had no effect on the struct in main. So what's going on here? So structs are actually passed by value. So the other sort of way of passing values to functions is pass by value. We were doing pass by reference, pass by pointer before when we were actually using pointers to pass values. Structs actually work pretty similar to other variables like int in the sense that the actual values for this struct are passed into this function here. And then this student s struct here, this is its own struct that just has the same values as this other struct here, S1. And when we modify it in this function, we're actually not modifying S1 as we can see over here. We're actually just sort of modifying the struct that exists inside this function here. So what's going on in memory, just so you know, is actually kind of interesting. Like if we have some student defined in memory, so we've got our variables here, and we have like a student variable here. So we'll say like S1, right? S1 has certain properties, has certain members. So it has like age, it has first name, it has last name. And all these things are stored in memory somewhere. They're all, at some memory address. And so this would be like maybe at address like 5. This would be taking up addresses like 6 to, let's say, I guess 56. This would be taking up addresses like 7 to, let's say, like 107, because these are arrays. And, there'd be certain data stored there. So like for age, it would be the value 20. And for this, it would be Devin. And for this, it would be Smith. And these would be the values stored at these addresses. So what happens when we call a function and we pass it a struct is that these values basically get duplicated on the stack in memory. So it's kind of like we copy all of this and paste it, and then it would be, S, and it would start at address, I guess, 108 here, and you'd have value 20 there. And then from 108 until, we would say, roughly like 159, or 158 there, we'd be taking up some memory to store 50 characters for a first name, and then like 159 here up until, we'd say like 209 here to store a last name. And what would really happen is that all of this data here would actually be copied in memory and reproduced on the stack here. So that's actually something to be aware of, because the sort of danger here is that what if our struct has just like massive arrays of data in it? That means when we call a function, all of that data is being copied and duplicated on the stack. So that actually could be a problem if we had huge amounts of data in our struct here. And so one thing we can do with structs as well is we can actually use dynamic memory allocation with structs. So let's say, for example, that we want to make a dynamically allocated student. We would just say student star S1, and S1 would be a pointer to a student type thing, to a student in memory. And we could then allocate space for it by saying here like S1 is equal to, we could say calloc, and then I'll say 1, and I'll say size of student. So the size of function is going to work with student, and it's going to allocate space to store one student. We could have used malloc as well. I could have said like malloc, and I could have said like 1 times size of student, or really just 1. Either way, this will work the same. So I'm going to say calloc though. I'll say calloc, and I'll say 1 student, and then I'm going to free S1 after I'm done with it. But what I'm going to have then at S1 is a pointer to a student's worth of space on the heap. And I can actually access and modify those member variables as well. So what I could do is I could say like star S1 and go get that thing in memory, go get the student in memory. And I could say dot age is equal to say 20. And then I could say printf, and I could say here like age %d, and we could say here star S1, and I could say age. And I could clear this and do a recompile here and run it here. And oh, you know what I forgot to do? I forgot to include stdlib.h. So I'm using the malloc, calloc, free type functions now. So I have to include stdlib.h. That's why I'm getting that compiler error there that's saying like, hey, we don't know what these functions are that you're trying to use. So I'll clear this, run it here, and I get age 20. And what's going on here is like calloc has returned a pointer. It's returned a memory address to some space on the heap that's been set aside to store one student's worth of data. And when I say star S1.age, it goes and gets the thing at that space in memory, and it accesses its age member variable, and we set it to 20. And then I'm able to actually print it out here as well. Now this syntax here of dereferencing the pointer and then accessing the member variables, that's a bit clumsy. It looks kind of bad. We just don't really like to do it that way. And C provides you a shortcut syntax, and it's this arrow type syntax. So we could actually say S1 age. And what this does, this sort of arrow here, is it says at the block of memory pointed to by the memory address here, S1, go get the age member variable in that block of memory. And we're going to set it to 20. And I could then say like S1 age here. And I could print it out this way. And if I do a recompile and run it, we get the same thing as before. It's just that this syntax is way nicer looking. And so basically, if we have a struct that's on the heap, we can access the member variables of that struct when we have a pointer to it by saying like the pointer and then arrow and then the member variable, and we're able to access it. And it's kind of outside the scope of the course to really get into it. But essentially what this is doing is it's basically kind of skipping ahead to the place in memory where this member variable would be stored based on how much space it takes to store each member variable. So it kind of skips ahead to like where in that block of memory we would be storing that piece of information. And we don't really need to know about that, but just so you know, that's what's happening there. And I could then, have functions that will actually then accept a pointer to a struct as an argument. And then we could then do pass by reference with structs. So maybe instead of like print student here, I could say like void, we'll say like age student. And what this will do is it'll add 1 to the student's age. So it's going to say that it's going to accept as an argument here a pointer to a student struct. And we're going to then make the function definition down here. And what age student is going to do is it's going to take the student here and it's going to increment its age by 1. So we're going to say here s age plus equals 1. And so then what I could do is I could call this function here age student with our student here, S1, as an argument, and S1 is a pointer, right? So that's an acceptable way to pass S1 to this function, which is expecting a pointer. And then we could print out the age after this call here. So we'll print out the age after we've made a call to age student here. And then we'll do a recompile and we'll run it. And I get age 20 and then age 21 after the function call. And what's happened here is just we've used pointers to do pass by reference in the exact same way as we did before. So we call age student with S1, which is a memory address for this student struct that exists on the heap. And then we access the age of that data on the heap, of that struct on the heap, and we increment it by 1. And then when we print out the age now in this function here, that thing in memory, S1, that S1 is pointing to, it's been altered. And so that's why we get this effect here. So we can do pass by reference with structs. And oftentimes that's how we see structs being used actually, because of the fact that when we do pass by value with structs, there's this potential to, pass some huge amount of information and require a huge amount of information to be copied on the stack. Whereas here, we only have like this one student struct that exists in memory. And when I pass a pointer to it, when I pass a memory address to it, it's not like the entire thing is being duplicated in memory. We're just passing in a memory address to that same struct that already exists in memory. So on the topic of pointers and structs, structs can also contain pointers to things as well. So let's actually delete some of this existing code here, and we're going to make a new struct. So we're going to say here typedef struct, and I'm going to say here like int data, so it's going to store some data, and then I'm going to say here int star array, and it's going to have a pointer to some data that we are going to assume is a dynamically allocated array. So I could say here, maybe we'll call it something else like info, like this is the name of the type now is info. And I could say here like info A, and I could say a.data is equal to 7. And I could say, info B, and then I could say like B is equal to A. And if I do a printf of b.data now, we're going to find that is going to be equal to 7. So I say b.data, and it's going to be equal to 7. So I could do a clear here, recompile it, run it, b.data is 7. So we can actually assign one struct to another struct. And what happens is very similar to when we pass a struct to a function, is that all this data here in A is going to be copied and it's going to be duplicated in B. Now, if all we've got is, let's say, like data 1 and data 2, like if we've just got some member variables here that are not pointers to potentially dynamically allocated data on the heap, that's not a big deal. So we could say like a.data1 is 7, a.data2 is 10. And then when we say info B and we say B is equal to A, B data 1 is going to be this, and B data 2 is going to be that, and we're going to get 7 and 10 there. And the data just gets copied basically. So we could do a clear, we could do a recompile and run it, and we get 7 and 10. And what happens in this case is not too bad. You've got basically in memory, a.data1, which is set to some value 7, and you've got a.data2, which is set to some value 10. And when we assign it, we say B is equal to A, it just gets copied. So like b.data1 gets set to 7, and b.data2 gets set to 10. And no big deal. Now, what can be potentially dangerous is if we have a pointer in here. So let's say instead, we've got int star array now. So we're going to go back to int star array. And this is a pointer to potentially some dynamically allocated data, some dynamically allocated memory on the heap. So let's say now info A, and we'll say data 1 is equal to 7. And then I'm going to say a.array is equal to malloc, and I'll say size of int times 5. And we'll free a.array when we're done with it. And that's going to be down there. But we've now basically made space to store 5 int values on the heap. And a.array is going to be a pointer to that space. A.array is going to hold the memory address where that block of data has been allocated. And we could assign values to it. So I could say like for int I is equal to 0, I is less than 5, I++, and I'll say a.array at I is equal to, we'll say I plus 1. So it'll be like 1, 2, 3, 4, 5 stored there. Now, if I say this, if I say like B, I'll say info B is equal to A. So I make another struct here, B, and I set it equal to A. We're going to find that B is going to, again, contain the data that A contained, right? So if we do a printf of B, and we say b.data1, and we print out b.data1, just as before, that's going to be 7. So we could do a recompile here and run it, and b.data1 is going to be 7. We could also print out the array elements. So we could say like for int I is equal to 0, I is less than 5, I++. Let's do a printf of b.array at each index. So we'll say b.array %d is equal to %d. We'll print out I, we'll print out b.array at I here. And we're printing out now this array that B has. And we'll save this, we'll do a recompile, run it, and we get b.array at 0 is 1, b.array at 1 is 2, all the way up to b.array at 4 is 5, just like how I set up the a.array here. So it appears that B has a copy of this array here in A, but that's not how it works. What B really has is the same pointer to that same array in memory that A has. So what's really been copied is the pointer, because remember, like with this info here, when we have like info and we say here, let's say info is going to be in memory, we're going to have like a data 1 is going to have the value 7, and a.array, what that's really going to store, remember, is some memory address. So it's going to be like the values here is going to be a data 1 is going to be 7, and a.array is going to have some memory address, whatever it is, like 0x, 1, 2, 3, 4, 5, whatever it is. And when we assign A to B like this, what happens is in memory, these values get copied. And so we get like B data 1 is 7, and B.array is equal to the same memory address. So when we're actually accessing B.array, we're actually accessing the same array in memory that's on the heap somewhere at this location in memory, right? And when we say like B.array here, we're basically just using array syntax, array notation as we've covered it to access the data at that position in memory. And so if we do a printf here of, let's say, we'll say a.array %p /n, and we'll print out a.array. And then we'll do a printf of b.array %p /n, and we'll print out b.array. Let's print out the pointer for each and see what they look like. Let's print out the memory address for each and see what they look like. And when we do, we get the same thing. Like you can tell this is the same value as this one here. It's the same memory address. It's the same array. So that means then that if I were to say modify b.array, I'd also be modifying a.array. So let's just say that I do that. Let's just say that I set b.array at 0 equal to, let's say, 10. Then if I were to do a printf of the a.array, it's going to be modified because it really is just the same thing in memory. They're just pointers to that same, dynamically allocated array in memory. So here I'll print out a.array now. And if I do a clear and a recompile, we're going to find that by modifying b.array and setting, the 0th index to 10, we've actually modified a.array. And again, that's because what's gone on here is that malloc went out and created space on the heap, and a.array really just stores a memory address to that data on the heap. And when we say info b is equal to a, what we're doing is we're just copying into b that same memory address. So when we access b.array, we're accessing the same array in memory as a.array. And we just really need to be aware of that this doesn't do some kind of like deep copy where it sort of replicates a duplicate array in memory. It just copies the pointer, and then B has, that same pointer. And so when we modify B, we're actually going to be modifying the same array in memory that A is pointing to as well. And that's something we just really need to be aware of when we're using structs. Another way of organizing data in our program is with what's called a 2D array. So we've done one-dimensional arrays, but there's also what's called a 2D array. And a 2D array works like this. I'm just going to delete some of this old stuff that we're done with now. And a 2D array looks like this. We're going to say here, int data 2, 3. And what we have now is an array with a certain number of rows and a certain number of columns. So I could say this is equal to, and I could say open squiggly bracket, and I'll say 1, 2, 3 as my first row of data, and then 4, 5, 6 as my second row of data. So 4, 5, 6 there. And this is now a 2D array with 2 rows and 3 columns. So 2 rows, 3 columns, and we're initializing it like this by saying 1, 2, 3, 4, 5, 6. And I could then print out each one of these individual elements by giving the index for that row and that column. So if I wanted to print out 5, say, I could say printf, and I'll say data 1, 1 is equal to %d, and I'll output data at 1, 1. And if I do a clear here and compile it, we're going to get 5 as our output there. Now, interestingly, when we initialize 2D arrays, we could have done it like this. We could have said 1, 2, 3, and then just 4, 5, 6 like this, all one after the other. And based on the number of rows and the number of columns, the data here, the values here, will be assigned to the correct indexes in order. So data 1, 1 will still be 5 if we initialize it like this too. Now, this is kind of confusing, so I've never really done it like that. I've always just said, here's a row, and then here's another row, and that just sort of makes it clear to the reader of the code what's going on, but you can do it that way, just so you know. Now, in order to write code to print out all of the elements in this array here, what we might want to do is use what's called a nested loop. So we put a loop inside of a loop. So we could say something like this. For int I is equal to 0, I is less than 2, I plus plus. Then we'll say here for int j is equal to 0, j is less than 3, j plus plus. We're going to do a printf. So we're going to say printf, and we'll just say data %d is equal to %d. And then I'll say /n here, and I'll say I, j, and data at I, j. And this would be one way of printing out all of the data inside of this array here. Is we've got data %d, which is going to be I. The I index is going to basically keep track of the rows from 0 up until 2. And then j is going to keep track of the column, and we're going to have %dj, and that's going to be outputting the column there. And then we'll say is equal to, and we'll say %d/n, and that's where we're actually going to print out data ij. And between all of this, we'll have gone through then every row, and then this inner loop will go through every column of every row. So we call this loop here the outer loop, we call this loop here the inner loop, and the outer loop is going to go through each row. The inner loop is going to go through each column for each row. And between doing all of these, we'll have printed out every piece of data here, every element in this array here. So we could clear here, do a recompile and run it, and we're going to get, 1, 2, 3, 4, 5, 6 by going first through all the columns of the 0th row, and then all the columns of the second row there, this one here. And this is what's called like a nested loop here. And this is the technique we'd probably use if we're working with a 2D array, because we have to go through basically all the rows and then all the columns. Now, one thing that could get frustrating is we could, throughout our code, be writing these loops that are going to be going up until 2, up until 3, right? And here we've got like 2 and 3. And we kind of know that this 2D array has this many rows and this many columns. But if I ever changed it, like if I ever wanted to make a, say, third row, I could say 3 here, right? I'd have to update that number everywhere. I'd have to update it here. I'd have to update it wherever else it is. And it could be all over our code. And I could put in like a third row here, like 7, 8, 9. And this will work. Like if I do a clear and recompile it, we're going to get, 1 to 9 printed out now with that new row we've put in with 7, 8, 9 also being represented here. But it's kind of a pain if I need to change these numbers everywhere all over my code, because if we're working with 2D arrays, there's a good chance that we've got a fair number of for loops that look like this that are going through the rows and going through the columns. And if I have to update these row and column numbers everywhere, it's kind of a pain. So one of the things that C gives us is what is called a constant. And a constant is a value that is not going to change at runtime. We can change it at compile time when we're writing our code. When we're writing our code, we call that compile time. We can change it then, but when the program is running, it's going to be fixed to some constant value. And there's one type of constant in C we can create with a define statement. So up here, we're going to say number define, and I'm going to say rows 3. Number define, I'm going to say calls 3. So what this does is it creates basically a synonym for 3. And I can use rows wherever I want to use 3. And rows then comes to represent how many rows are in my 2D array here. Calls would then represent how many calls are in my array here. Now I can never change these values while the program is running, but that's okay. We're okay with that. We just say like rows here and calls here. And then down here, I could say rows and then calls here. And what I'm doing is I'm using these constant values. And what's going to happen is that wherever rows is, 3 is going to be inserted. Wherever calls is, 3 is going to be inserted. But when I'm actually reading the program as the programmer, it kind of makes more sense to read it this way, right? That like I is going to go up until the number of rows, J is going to go up until the number of columns. It sort of actually improves the readability of the code. And if we save this and recompile it, we're going to get the exact same result as before. And that's because basically what happens is the compiler inserts 3 wherever rows is and inserts 3 wherever calls is. Now, this is what's called a preprocessor statement. There's a stage of the compiler called the preprocessor. And one of the things it does is it grabs these libraries like stdio.h. Another thing it does is it also looks at these sorts of define statements and modifies our code. It basically goes through our code and inserts the 3 everywhere where rows is and inserts the 3 everywhere where calls is. Now, another big advantage of this approach is if later on the number of rows changes, let's say it goes back to 2, I just change it in one spot. And then it's going to be updated throughout my code. I'm going to have to change this as well because we've only got 2 rows now. But the idea is that let's say I've got loops like this all over my code. I just have to change it in one spot. And then all those loops are going to be set up now to work with the differently sized 2D array now. So I could do a clear, recompile and run it, and we're good. We could also use scanf to actually read in each value as well from the user. So we'll just actually copy this loop body here. And then in here, I'm going to ask the user for each value and use scanf to record it. So I'll say printf data %d is equal to, and we'll ask the user to enter the value. And then we'll say scanf, and I'm going to say %d. And for this one here, I'm going to say and data I j. And for this one here, I'm just going to say I and j. And so what we're doing here is we're basically telling the user, enter the data for this row and this column. And then here we're saying, read in a value that's going to be an int value and store it into the 2D array at index ij. And if we run this one here, we can then set up these values here. So we'll say here, clear GCC to compile it. Oops, what I forgot? I forgot a semicolon. And we'll just do a clear and a recompile and run it. And it says data 0, 0. I'll say like 10, 20, 30, 40, 50, 60. And then when we do the output, we get 10, 20, 30, 40, 50, 60 in the places we would expect. Now with this here, I actually could set all of these values to 0 in a simple way. I could just say this, 0. What that'll do is it'll initialize all of the values in this array here to 0. And that's a simple piece of syntax that we can do to achieve that. So we can actually pass a 2D array to a function as well. So I could say here void print, we'll say array, and then I'm going to say here int data rows calls. And then we'll provide the function definition down here. And this will print out a 2D array. So we'll actually just copy and paste this for loop here, this nested for loop in here, that's going to print out the 2D array, just that way we don't reinvent the wheel. And then I'll just call the function. So I'll just call print array and I'll give it data here. And then this will print out the 2D array. So we'll do a clear here. We'll recompile it and run it. And we can put in some data here. So we'll say like 987654. And then we get 987654. And this function is able to print out the 2D array. Now notice a couple things. Number one, the rows and calls, we can use them in the function here. So these define statements, they're defining this constant for this entire file. So we can use rows and calls wherever we want in this file, not just in the main function. We can also use it in a function like this, and that is okay as well. Now, one thing you'll notice is that I actually provided the dimensions here. And I provided the dimensions because the compiler actually needs us to do that. If we had a 1D array, we could just say this. We could just say int data, and that's okay. Or as we've learned, we could even just say int star data, and that's okay. But with a 2D array, we're often going to want to do this. We're going to want to say rows and calls and just specify the number of rows and calls. It could be hard-coded as a certain number, like 5 and 5, or you could use constants. It's up to you. But we're going to provide rows and columns. Just that way the compiler knows the dimensions of the 2D array. If we don't provide them, we're actually going to get a compilation error. So we can try to clear this and compile it here, and we get error array has incomplete element type int open bracket close bracket. And that's basically the compiler telling us that like, hey, I need more information about this 2D array. If you give the number of rows and number of columns, it will work. So we could then compile this and it works okay. You could also just specify the number of columns. So if you actually take out this here rows, the compiler is able to work with this 2D array so long as it knows the number of columns. So this will actually compile okay as well. And you can run it and we'll get the same result. I could put in numbers here, 1, 2, 3, 4, 5, 6, and we get out 1, 2, 3, 4, 5, 6. I've always just provided both dimensions because typically speaking, when I've worked with 2D arrays, I've had them. So I've just provided both of them. But you can just provide the column value, just so you know, and that will work as well. Now with 2D arrays, they are going to be passed by reference, just like 1D arrays. So I could make another function here, void input array, that's also going to take in a 2D array as an argument. And we could define this function input array here. And I'm actually, again, just going to copy and paste this code here because I've already got it. And this will actually modify the data array in this main function here. So when I call input array and I give it data, again, what's happening is pass by reference. The same as a 1D array is really just a pointer. Same thing with a 2D array. Like ultimately data here is ultimately some memory address of this 2D array here. And so we can actually then modify data in the calling environment here, main, for the same reason it works with 1D arrays. So if I save this here, clear it, and run it, after doing a compile, we could say like 5, 6, 7, 9, 2, 1, and I get 5, 6, 7, 9, 2, 1. And the input array function was able to modify the 2D array in the actual calling environment here. So that way when I passed it to print array, it had those modifications that I made, the data that I had input here. And just be aware of that as well, that 2D arrays are also passed by reference. So now we've actually covered enough concepts to talk about something that you might have been wondering about since the very start of this little course here, which is what is int main void and return 0 doing here? Like main is a function, but it has a return value apparently. It looks like it could accept arguments and it returns 0 here. Why is it doing that? So we can talk about these things now. So first off, the return value of main. The return value of main is actually going to go to the terminal here. So the terminal is something we call a shell, and the shell runs programs for us. So when we compile our programs and we run them, it's actually going to execute them. And technically speaking, what's going to happen is the return value that we give from main is going to be essentially a signal. It's going to be a signal to tell the shell whether the program exited successfully or not. So if I just compile this very basic program here that looks like it's going to do absolutely nothing, One thing it is going to do is it's going to return 0. And that basically becomes the exit status of this program. And we can actually access it from the shell. So if I say here echo $? We get 0. And this here is basically saying output the last program to run's exit status. And we exit with 0. Now, if I said return 1 here, and we do a recompile, and we run it, and then we do echo $? We get 1, because the program has now exited with a status of 1. Now 0 is typically what we want to use as a return value, and that's why I've been using it as the default value. Anything that is not 0 will be interpreted as some kind of failure, some kind of error has taken place, whereas a 0 is for success. So 0 should be the default, but you could return other values to signal that something has gone wrong or something is up, basically. And those values could actually be accessed by the shell and used to maybe determine whether the program behaved as expected or not. You can actually write scripts in the shell that put together these commands we're running here and do things like run a program and then take the results of that program and put it into another program and run it with that data as input. And so we might actually care about these return values here because they signal, did the program behave as expected in the case of return 0, or did something maybe go wrong with something up that the shell should know about by returning a different value there. Our program can also interact with the shell by receiving what are called command line arguments. So command line arguments are actually these things here. So when we run GCC, the compiler, and we say -od, these are 2 arguments, and -o is telling it, I'm going to give you an output file name, and D is the name of the output file, the executable file that we're running here. And then D.C, that's another command line argument, and it's telling GCC, I want you to compile D.C. This here is a command line argument for echo, telling it, here's the thing I want you to print out. And we can actually accept and use command line arguments as well in our program if we specify some parameters for main. So we say here int argc char star argv open bracket close bracket. And the way we accept command line arguments is that argc will contain the number of arguments, including the actual command itself. And then char star argv, what this is an array of strings. So it's an array of strings that we can access and print out. So let's actually just do an example of this. We'll say printf argc %d/n, and I'm going to print out argc. So we'll do a recompile here. We'll do clear recompile, and I'll run it, and I get argc is 1. So we don't have any arguments, but argc is 1. And that's because argc is going to include this ./d here, the actual running of the program itself, the actual executable name there. That's going to be included as one of the command line arguments. And then if I ran ./d and I said 1, I get argc2. And what's going on there is that I've got 2 things now. I've got the name of the program itself, and I've got my first argument to the command here. I could say ./1 2, and then I've got argc is 3 because I've got, the command itself, 1 and 2, ./d 1 2 3, and I get 4, and on and on. And so argc is going to keep track of basically how many command line arguments were you provided, because different programs will accept different numbers of command line arguments. There's not necessarily a requirement for a specific number of arguments. It could actually vary. So what we're going to do now is look at the actual arguments themselves in argv. And so we could print them out individually here. We're going to say here for int I is equal to 0, I is less than argc, I++. Let's print out each one. So we're going to say printf argv0 or argvi is equal to %s/n, and I'll say here I and argvi. And so argv, what this is an array of strings. And so if I say argvi, what I'm doing is I'm accessing the 0th string, the first string, the second string, the third string, and on and on. And we could access them individually. So I could say like printf, and I could say like argv1 is equal to %s, and then I could print out argv1. And what I'm doing is I'm just accessing them here with a loop that's going to print out from 0 up until the number of arguments that I was given. So we'll just do a clear and a recompile here. And we got 2 warnings this time. Warning, argument not used before format string. Oh, you know what I forgot to do? I forgot to say the %d here. So I gotta say %d there, right? Because I'm providing it with I, the index that I want to print out, and I'm providing it with the actual string itself. So I've got to provide both arguments, and I got to have both placeholders there. I forgot the %d placeholder there. So we'll do a clear. And so we recompile it. And then if we run it here, we say ./d, and I'll say ABC. We get argc is 2, argv at 1 is ABC, and that's one where we printed it out with a literal value for the array index here, and we kind of printed it out sort of manually here. And then here we're automatically printing all of them by writing a loop that's going to go from 0 up until the number of arguments, printing out each argument one at a time using I as an index here. And we get that argv0 is D, argv1 is ABC. I could run it again. I could say ./d. I could say 12, AB, and 5. And now we've got 4 arguments, so the command itself, and then the 3 arguments here. And we've got, argv1 is 1, 2, argv0 is ./d, argv1 is 12, argv2 is AB, and argv3 is 5. Now, what we could do is we could actually use these values in our program. So we could actually, do some work with some of the commands that we're given here. So maybe we're going to write a command that's going to print out the first argument by a number of times specified by the second argument. So it'd be something like this, like ./d ABC 5. And then the idea would be that it would print out ABC 5 times. And we could write, a program to do that. So let's actually do that. Let's say here that we're going to look at the first argument and the second argument, and we're going to print out the first argument by the number of times specified in the second argument. So I can get at the arguments and I can print them out like strings, right? So I can say printf %s/n, and I could say here argv1, and I could say here printf %s/n, and I could say argv2. And this would then print out the values that I'm interested in. So I could say clear, recompile it, run it. I'll say ./d, I'll say ABC 5. And I print out ABC and 5. The problem is that if I want to use 5 as, say, the length to go up to, the number of times for a loop body to execute, then I really need to convert that to an integer, because I can't really use a string like that, right? Like I couldn't say like for int I is equal to 0, I is less than argv2, I++, and then do some work in here like print out argv1 this many times, like print %s/n argv1. This is not going to go well because argv2 is a string. If I try to compile this, I'm already getting a warning. It's telling me that we have an ordered comparison between pointer and integer, int and char star. It's basically telling me that like, hey, you're using the wrong type of thing here. This should really be an int. And it's kind of warning me that you're probably about to do something wrong. And what we're going to have to do is we're going to have to treat argv2 like it's an int value. Now there's a function that we can actually use that converts a string to an int value. So I could say here, number sign include stdlib.h, and that includes a function atoi. And atoi will take the string and convert it to an int value. So I could say here, int num times is equal to atoi argv2. And this will take this string here that's in argv2 and convert it to an integer with this function here, and then return it, and then we'll assign it to num times. So then I could say num times here. And what's going to happen is we're going to loop from 0 up until the number of times, and we're going to print out that first argument that we're given each time in this loop body here. So let's try this out. We'll do a clear, do a recompile. We'll run it with ABC 5, and we get ABC 1, 2, 3, 4, 5, 6 times here. Now, why is it 6 times? Because I printed it out up here already, right? I printed out argv1 up here already. I'll take out that one. And then we'll do a clear. We'll recompile it here. And then we'll run it with ./d ABC5. And now we get ABC 5 times. I could say 1, I get it once. 4, I get it 4 times. And the idea here is that I'm now using these arguments here to influence exactly what my program's going to do. I could say ./d, 1, 2, 3, 4, and we get 1, 2, 3, 4 times. And it's just kind of cool that I can now control my program's behavior with these command line arguments. So what we actually have here is a good case for perhaps returning a different value than 0 if the number of arguments provided is not correct. Because if I try to run this program with, let's just say 1 argument, I'll just say ABC here. we get segmentation fault here. And that's because our program is basically assuming that there's going to be a second argument. And when there's not, we get an error. And so what we should do really is check to see, do we have exactly 2 arguments? Because that's what we expect. And if we don't have it, we should probably print out a message to the user saying like, you need to supply these arguments. And we should probably return a value that is not 0 because the program is not behaving in an expected way. So we'll actually do that. We'll do a check. We're going to say here, if argc is equal to 3, then run this code here. Then carry out the expected functionality. If we don't have that argc is 3, then that means that either we've got too many arguments or we've got too few. And at that point, we want to then specify to the user and tell them like, hey, something's up here. You got to provide 2 arguments exactly. And we could say here else, and we could do that here. So we'll say else, and then we'll throw in a printf. We'll say printf 2 arguments expected. And we'll say printf down here, we'll say string to print out. And we'll say that's the first argument. And then, oops, I did something here. And then we'll say second argument is number of times to print it out. Printf second number of times to print. Okay. And then what we'll do is we're going to return 1 here because we're basically going to specify that something went up, something went down, like something bad happened basically. You know, we're telling the shell here that this isn't correct. So we'll do a clear here, recompile it after I find it again, and then we'll run it with /d and we'll say ABC and 12. And it prints out ABC 12 times. And if I do echo $? We get 0 because it exited with an OK status. Now, if I run it though with /d ABC, I now get 2 arguments are expected. The first should be a string to print out. The second should be the number of times to print. And we're getting this warning now, basically telling us that something is wrong. And if I run echo $? It says 1 here. And the shell has basically been told like this last time you ran the program, it didn't work correctly. Something is up. And this would be useful then because I could then put this program into a script and the script could run a series of commands like this on the terminal. And the script would know that something is wrong. And the script could then handle that in a better way than just sort of failing and not working. And just a reminder that the reason why we have 3 here is that argc does include the actual command itself, the actual executable itself. So that's why it does have to be 3 instead of 2 there. Now, one thing we're doing here that's interesting is we're taking this string and we're converting it to an int value. And that sort of type conversion is often something that we want to do in a programming language. And one way to do that in C is with what's called typecasting. So I'll show you an example of typecasting. So typecasting allows us to take a type and convert it to another type. And the general way that it works is you say the type that you want to convert the thing to, and then the expression, the thing that you want to convert to this type. And so it could be something like this, like I want to convert to a double the value or the variable a. And this would be a type conversion from a, whatever type it is, to double. And this comes up every so often in programming. So we could say here like int a is equal to 5 and int b is equal to 2. And if we did a printf of these values, so we'll say %d divided by %d is equal to %d, and we print out a, b, and a divided by b, then when we compile this here and we check out our output, we're going to see that it's 2, that the division of a divided by b there is 2 because 5 divided by 2 when we're doing int division is basically how many times does 2 go into 5, which is twice. What if I want the double result? This is where type conversion might come up. So if I said here double C is equal to a divided by b, we might think that it's going to do a divided by b and it's going to store the result as a double into C. But we're going to find that's not actually what happens. So if I do a printf here of a, b, and then we'll say C here, which is a double value, so I've got %f here as the placeholder, we're going to find that it actually doesn't do that. We get 2.000000 here, but it's a double, which is good, but it's not actually the value we expect, right? Like if we do 5 divided by 2 as a double, we'd expect it to be 2.5 as the answer. but we get 2.00000 and on here. So what's going on here is that C will actually do integer division here because A and B are both int values. Then when it gets the result, then it will store it in C as a double. But int division is actually going to take place because these are both int values. I can use typecasting though to convert A to a double value. So I could say here double A. What this will do is it'll actually convert A to a double value, and it'll take 5 and make it 5.0 essentially. And then when we do the division with B here, what's going to happen is B is actually going to be sort of upgraded to a double at that point, because C is going to see that we have a double over here. And then the other operator is basically going to be upgraded to a double by C at that point. And so what'll actually happen now is division involving double values. And now we get, if I save it correctly, I have to save it and recompile it. Now we get 2.5 over here. And it actually is doing division with doubles now. Now, this might be a little bit surprising that we've got this type conversion here, this typecasting here, and then we've got the expression over here. And we might think that it's converting the result of this expression to a double value. And that's actually not what happens. If I said here like A divided by B, and I actually enforced that this division happens first, and then we convert it to a double, we're going to find that it's actually going to go back to being 2.0. What actually happens is that A gets converted to a double first. And that's another one of those precedence things. It's because this operator here, typecasting, that happens first. That happens first. When I had this here with brackets around A divided by B, that was enforcing with brackets that A divided by B would actually happen first. So it does the integer division first, we get 2.0, and then that gets converted to a double. If I have this though, this actually has higher precedence, and this gets converted to a double first, and then we do the division. And when we go to do the division at that point, that's when C says, oh, we better make this a double to carry out this division. And at that point, it's going to work okay. Another thing we can do in C is read and write to files. So we need files on our system here. So if we do an ls in this directory, it'll show us the files on our system. And right now you've just got d.c and you've got the executable. And ls is showing us the files in the current folder we're in, which is just, a file directory on my desktop here that we're in. And what we could do is we could create files and write to them, or we could open files and read to them. So I'll just show you how to do that as well, because that's another common thing that comes up in C programming. So I'm going to say here, file star is equal to fh, and I'll say write. So file is something that we have access to in C, and that is going to create a file handle variable. And when I say star fh write, this is going to be a file handle variable that I can use to open and work with files. So now what I'm going to say is fopen. So we have to open files in order to write to them or read from them. And I'm going to say fopen, we'll say write.txt, and then I'm going to give as a second argument w. So when we say fopen write.txt, what it's going to do is open up a file called write.txt. And this here is the mode that it's going to open it up with. And we're going to open it up with write mode. So W means open it up with write mode. And then we're going to say fh write is equal to this function call here. So what this function call returns is a file handle. And fh write is then going to be that file handle. So we could actually then access the file and write to it by using this file handle here. Now, if fopen doesn't work, if somehow it just doesn't work, it would return null, and we could check for that. So we could say here, like, if fh write is equal to null, then printf error opening file. And that would be one way of handling the situation. And if it worked okay, if it did open okay, we'd say else, and we could go in here and we could write to the file. So to write to the file, there's different ways of doing it, but I'm just going to say here f printf, and we'll say fh write, and then we'll say hello world, and we'll just write hello world to our file. Seems appropriate. So hello world, if I can spell it right, and that'll write hello world to this file here that we've opened with this file handle. And fprintf works basically the same as printf. It's almost identical. It's just that we give the file handle here as the first argument. So we'll write to the file, we'll say hello world, and then when we're done with the file, we have to close it. So when we're done with the file, we're going to say fclose, and I'll say fclose fwrite. And this basically closes our access to the file and says we're done with it now. And so this should open up a file called write.txt in write mode. It should check to see if it opened correctly. If it didn't, we'll printf error opening file. And we could probably return 1 here, right? Because we're just sort of acknowledging the fact that something didn't go right. Otherwise, if it did open okay, we're going to printf to the file hello world, and then we're going to close our access to it. So let's run this program here, and we'll just see how she works. So we'll say gcc-o d.c, and we'll run it. And it didn't give us any output. And that makes sense because we wrote to the file, right? Not the terminal. If I say ls here, I'll see that I have a file now called write.txt. So our program created that file and it wrote the line hello world to it. I could look at the contents of that file by saying cat write.txt, and then we see hello world there. I could have opened up the file in a text editor, but I might as well just see it on the command line by just saying cat and then the name of the file. And then that'll just actually dump out the contents of the file right here. And so that is opening a file and printing some content to it. We could print out variables as well. So we could say something like val %d here, and then I'm going to say here x, and we'll print out the value of x here. So I could say like int x is equal to 100. And we could then recompile it here and run it, and we'll say cat write.txt again, and we get val 100 here. I could use a loop to write a whole bunch of different values to a file as well. So we could say instead of, int x is equal to 100 and fprintf just that one value, let's actually use a loop now. Let's say here for int I is equal to 0, I is less than 10, I++, we'll write 10 values to the file. We'll say fprintf fwrite %d/n, and then we'll output I+1. And if we do a clear and we recompile it and run it, and then we check with the file contents, we've got 1 to 10 in that file there. I could also use what's called append mode. So I opened the file with write mode. Append mode will open the file, and instead of blowing away and deleting whatever content is already there, what it'll do is it'll actually append the content that we write to the file to the existing content of the file. Because as it is right now with this write mode, if I change this to 5 now, and I save it, and we do a clear, recompile, run it, and check out the file contents, we've got 1 to 5 in there. Those previous values, 1 to 10, they're gone. We obliterated them when we opened the file with write mode. And with append mode, it won't do that. With append mode, it'll actually add on the content that we write to the file to the existing content in the file. So if I say here A instead, and I do a recompile, run it, and check out the file now has 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. If I run it again and check out the file contents, we've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And so we're continually now appending to the file because we opened it in append mode. And that's another way that we could open a file. And that's in contrast to write mode, where if we open up in write mode, I'll change this to maybe say 8 here now. That is going to blow away the existing content. It's going to obliterate it. It's going to delete it. And we can run it. We can check out the file now. And we've got 1 to 8. And the old content in the file is now gone because we're using write mode. And this is writing to a file. We can also open a file in read mode, and we can read from the file. So let's do that. Let's actually do a reading of a file next. So we're going to say here, file star fh read. And I could have called this whatever I wanted. I'm just calling it read and write just to make it clear what I'm doing with it. And I'll say fh read is equal to fopen. And we're going to open up write.txt. And this time we're going to open it up for reading. Now, if we can't open the file, then it's going to return null. So we're going to say here, if fhread is equal to null, we're going to printf file could not be opened, and we'll say return 1 because we've got a problem here. What if we actually couldn't open the file? Because right now we're trying to open write.txt, and that file is in there, right? It's right there. We've actually created it right now. So if I try to run this program, it should work fine. We're not going to get any error opening it for reading. But what if the file didn't exist? Like what if I said here rit.txt, I had a spelling error there, and I try to compile it and run it. Now I get file could not be opened, and the program returned 1. And if we did like echo $? We see that status has been returned as well. And so this is something that we're going to want to have as a best practice, as a check, just to make sure that we've actually opened the file correctly. So we'll say fopen write.txt. We will open the file correctly this time. And now what we're going to do is we're going to read in each line of the file and we're going to print it. We'll just print it to the screen after we've read it in. So we'll say here else, and I'll say fclose to close the file after we're done with it. Now to read in the file, there's all kinds of functions for reading and writing to files. I'm going to use the function fgets. So fgets is one way of reading content from a file. And what you give it here is a pointer to a string, a pointer to an array. And we could say here buffer. And what I'm going to do is I'm going to make a buffer to actually read in this data. So I'm going to say here car buffer 100. So what this is a character array of 100 characters. And I call it buffer because that's actually a common terminology for this sort of array, where we're using it as an input buffer. It's going to store each line of the file into this character array buffer here. And we're going to say fgets buffer, then we're going to say 100, and then we're going to say the name of the file here, the name of the file handle here. So I'm going to say here fhread. And what this will do is it'll read in a line of the file and store it into buffer. When it encounters the first new line in the file, which is going to encounter that almost immediately, right? Because the first line here has 1, and then a new line, and then 2, and then a new line, and then 3. When it encounters the first new line, it's going to stop. Otherwise, it's going to go up until this amount of characters, and then it's going to read the content from this file here, fhread, with this file handle here. And so if we run this here, this should actually store 1 into the buffer. So we could say here printf, and we'll printf the buffer. So we'll say %s/n will output the buffer here. Okay, so we'll clear this here, do a recompile, run it, and now we get 1 output. And what's going on here is that we read the file contents into the buffer using fgets. But the way fgets works is that it's going to stop when it encounters the first new line. So it reads 1 in, and then it encounters a new line, and then it stops. So we only read 1 into the buffer. And it would read up to 100 characters, and it's reading it from this file. And then we printf the buffer. So we printf what's in the buffer, which is just going to be the character 1 at that point. And so if we wanted to read in the remaining lines of the file, we'd want to kind of keep reading until there's no more to read, right? We want to keep reading until we can't encounter any more data to put in the buffer here. So the way we can do that is that fgets will return the special value null when it can't read anymore. So when fgets can't find anything else, that's when it'll return null. So we could say this, we could say while fgets doesn't equal null. So while calling this doesn't equal null, continue to read in content from the file here. So while fgets doesn't equal null, continue to print out the content from the file here. And I'm actually going to take out this new line here because this 1 will include a new line, 2 will include a new line, 3 will include a new line, and on and on. So I don't really need to print out the new line when I print out the buffer each time here. So we'll say clear, recompile it, run it, and I'm printing out 1 to 8 now. And what's happening is I'm reading each line from that file there. And I'm reading in each line into the buffer. And eventually what's going to happen is fgets will have no more to read. And at that point, the function returns null. And that's why we're looking for that here. We're saying so long as fgets doesn't equal null, keep going. But if it ever does equal null, that's when we're going to stop. And it's going to equal null when it's done reading from the file. And so this is actually a common thing to see here is a while loop with an fgets inside of it that actually continues to work until it returns null. And we're just printing out the data each time here. What we could do is we could convert this data to something like an int value and store it in an array too. So we could take this string data here and we could convert it to an int value and store it into an array. So we could say here maybe like int data, and we'll say that it could store up to 10 pieces of data, even though we've only got 8. And we're going to take each string and we're going to convert it now using the atoi function to an int value, and we're going to store it in data there. So we'll say here number sign include stdlib.h. So we have that function, and we're going to take each string here and we're going to convert it to an int value, and we're going to store it into data here. So I'm going to say here int I is equal to 0. We'll say data at I is equal to atoi buffer, and then we're going to say I++. So what we're doing now is we now have this array here of integers that's going to store up until 10 integers, and we're going to keep track of what value we're storing into that array in terms of the position with I. So I is going to be 0, and we're going to increment it each time through the loop here. And then we're storing at each position in this array here the converted value. So we're taking that string here, 1, 2, 3, 4, 5, 6, 7, 8. We're taking that string, we're converting it to an int, and we're going to store it into data there. And then when I'm all done, I could print it out. So we'll say for int j is equal to 0. We could say j is less than I, j++, because I has been keeping track of, in this loop, how many pieces of data we've read in this file here. But instead what I'm going to do is I'm going to say int numLines is equal to I. Just that way it's clear that that's what we're keeping track of. And I'll say numLines here. And then I'm going to print out the values. This time though, from the actual data array itself, where we've been storing the converted strings. So we'll say printf data %d is equal to %d/n. We'll output j and data at j. And then if I do a clear and I run this here, we're going to get data at 0 is 1, data at 1 is 2, on and on up until data at 7 is 8. And the idea here with converting these values to an int is I could do some work with them, like compute an average, which is kind of the standard thing we've done in this course, is computing an average with things. So we could compute an average. We could say like total is equal to 0, and then add up the total of each one of these elements, and then find the average. So total plus equals data at j, and then we'll do a printf with the average being the total divided by the number of lines. And this would be another way of working with the data. So here we're going to say printf the average, which is going to be the total divided by the number of lines that we read in. So we do a clear here, recompile it, execute it, and we get an average of 4, which makes sense given the values we've got here. Now, in both cases here of the character array buffer and this int data array here, I've kind of made assumptions that the line that I'm going to read in is going to be max 100 in length. And I've kind of made an assumption that there's going to be a maximum of up until 10 lines. These are values that are typically defined with constants. So we could have something like this, number define, and we could say here like line buffer is 100, and number define, we could say like num buffer is, let's say, up to 100 as well. And then we could use those constants here. So we'd use like line buffer and num buffer. And so you typically see this sort of buffer type situation where you have these arrays that are set up to store some amount of data. We could use dynamically allocated memory and realloc to actually increase the size of these buffers as we need them. But oftentimes you'll just see some constant value used like this because we can just make an assumption that the lines are not going to be any bigger than this. The file's not going to store any more data than this. And oftentimes that assumption is okay. Now, just so you know, there is actually one other way to make a constant value in C, and that's what's called a constant variable. So we can do it like this. We could say like number define, and we could give it some name, and we could give it a number. And this uses basically the preprocessor of the compiler. And this constant is going to be defined everywhere. So that means that if I have a function here, let's say like void func, this function is going to have access to that constant. So I could say void func down here. I could provide a function definition, and we could just say printf %d/n, and we could output that constant there name. And if we call the function, we're going to get that output. And what happens with the preprocessor style constant is that the compiler actually goes through and as part of the process of creating this executable, just replaces name with 5 everywhere. Now, this has the advantage of it being global. So I can use it in main or I can use it in func, and either one is okay. So we could say here, printf %d/n name, and I can use the constant there as well. So we can do a recompile, run it, and I get 5 and 5. There is another way to do a constant called a constant variable. And the way that one works is like this. We would say here, const int x is equal to 5. Now what this is a regular variable in C called x that's been initialized to 5. But I actually can't now modify x later. So I can use x like a variable in terms of putting it in expressions or printing it out. So I could say like %d/n, and I could say x plus 2 here, and we're going to get 7. So I can recompile this and we get 7. So I can use it just like a regular variable in terms of printing it out or putting it in an expression and, getting some new value from it. But what I can't do is assign to it. So if I tried to say here, x is now equal to 3, I can't assign to it past this first initialization of it. I can initialize it once and then that's it. If I try again, I'm going to have a problem. So I can recompile it here and we get error. Cannot assign to variable x with constant qualified type const int. So we can initialize a const variable once and then that's it. We can't initialize it again. That's what makes it a const. Now the other thing with const is that it has scope. So this variable here, x, it's going to have the scope of the main function that it's declared in. So like other variables, const variables have scope. So I can't access x here in this function. I couldn't say like printf %d x and have that work. If I try to compile that, it's going to complain. It's going to say error, use of undeclared identifier x. So const variables also have scope. And so with the const keyword, we can then, limit the variable scope to a particular function maybe, as opposed to the define statement where the constant is actually going to have what we'd call global scope or file scope over the entire file. And it isn't really a one is better than the other situation. It's a use case situation where if you need a constant across the entire file and all the functions in the file, then a define statement is probably best. If you want to use a constant inside one function only, and maybe you initialize it to some particular value that could change, maybe a const keyword is going to be best. And so it's really kind of up to you and what the situation calls for. Now, one thing that's interesting is we can also have variables with global scope. So let's do an example of that here. We'll get rid of some of this stuff here. And then we're going to make a global variable up here. I'm going to say int x is equal to 10. So this is a variable that I'm declaring and initializing outside of any function. And I'm going to actually have access to it in all functions. So I could say here in main, printf x %d/n and print out x. And if we do a compile here and we run it, we get x10. X is also accessible though in func. So I could put it here and I could also access x inside this function here and we could call it in main and this will work as well. And if we do a recompilation here and we run it, we get x10, x10. So x is a variable that is globally available. And we would say that it has global scope or that it has file scope. You see both terms used. And we could modify the variable. So I could say like x++ here, and I could say x++ here. So by the time it prints out in the function, it's going to have incremented twice. And so we can access x and we could change it and we'll get the expected behavior there as well. And we get x12 there. And again, this is a variable with global scope. Now, the one thing with variables with global scope is they can actually be a poor programming practice. They can be dangerous to use because what can happen is you make a variable with global scope and then you call some function, the function does some work and maybe it returns some value to you or maybe it prints something out. But that function will modify this global state. It modifies this global variable that's sort of like a global state then for your entire program. And unless the programmer is very aware of the fact that that global state might be modified when the function is called, it can actually result in very confusing code because you call a function that does some work, it prints something out, it returns something maybe, but it also modifies this global state. And then if your main function or whatever other function called that function is not aware of that, and it uses it under the assumption that it hasn't been changed, it can be very messy. And so we actually call that kind of code spaghetti code because it's very hard to figure out. And so in general, you actually want to avoid using global variables because it's well known in programming that global variables can make your code harder to understand. You might actually hear the term side effect being used. So when a function does more than just use some parameters and return a value, when it modifies global state, we would call that a side effect. So you might see that term used specifically. Now, one thing that's interesting with global variables is what happens if you have a global variable and a local variable with the same name. So what if I said in my main function here, int x is equal to 2? I can do this. I can make a local variable x that's equal to 2. But how is that going to work when I have a global variable called x? We can actually print out we'll save it here and we'll print out the result here just to see what happens. So compile it, run it, and we get x2. So what's going on there is that when this first printf runs, it actually is going to default to using the local variable x. So this local variable will take precedence over the global variable. This is also another reason why global variables can be messy, because if we start using names globally and we start using the same names locally, it's going to add further confusion as to exactly which one is being used. We would say that we're sort of polluting the namespace when we create a bunch of global variables, because we're kind of taking up space. We're polluting the space of names that we could choose from if we do that. So that's another reason why we generally avoid global variables. So I want to show you one last trick here. So C is a high-level language in the sense that it's higher level than machine code, but it's a very low-level language among high-level languages. It's what we call a systems language. And that's in contrast to languages like Java and Python that are developed more recently, and they typically made a lot of things for programmers easier to do. Whereas C, a lot of things are actually kind of harder to do because the goal of the language is to allow for lower level programming, like making operating systems or compilers or embedded systems, things like that. And so some things that other languages make really easy, C just sort of makes frustratingly hard or a little awkward. So let's say here car buffer 100, and we're going to ask the user to enter a string, and we're going to put that string into the buffer. So we're going to say printf enter, and then we're going to say scanf, and I'm going to say %s, and then buffer here. And we don't have the and here because, again, this is an array we've got here. And when we just use the array name like this, it is a memory address, right? It is basically a pointer. So that's why we don't have to say, and buffer here. We just say buffer. And we're going to store the string that the user enters into buffer. Now let's try to print out the string after we've received it. So we'll say buffer %s/n, and we'll output the buffer. Here we'll say clear, compile it, run it. So enter, and if we say like 1, 2, 3, 4, A, B, C, D, we're good. But what if I do this? What if I say 1, 2, 3, 4, A, B, C, D? The buffer only contains 1, 2, 3, 4. So one of the little sort of frustrating things with C is that scanf doesn't behave as we might expect it to with strings by default. And we might have to use some other technique to read in a string that has spaces in it. Because when scanf encounters a space, it basically stops reading in the string at that point and stores what's been read in so far into the buffer. And so it's just going to read in 1, 2, 3, 4. It encounters a space and it says, okay, I'm done. Put the string into buffer here. So if we actually want to have the user input a string with spaces, we have to use a different technique. And that's where we could use fgets. So I'll show you this here. We can say here, fgets, fget_s, and then we'll say here buffer 100. And then instead of a file name here, I'm going to say stdin. So stdin. So stdin, that stands for standard input. And input from the command line terminal here, that's coming from what's called standard input. You can actually redirect standard input so that it comes from something like a file. But what we're going to do is actually just use regular standard input from the terminal. And this keyword here, stdin, that basically represents standard input. And what we're saying is get, not from a file, get from standard input a string and store it into buffer. And the way fgets works is it's going to stop reading in the string when it encounters the first new line. In other words, when the user hits enter. So if we run this version of it, compile it, run it, I can then say 1, 2, 3, 4, A, B, C, D, and we actually do get the string in the buffer now, 1, 2, 3, 4, A, B, C, D. So we can accept user input with a space in it with fgets and using this standard in here instead of a file. So that's just a trick I wanted to show you, just because there's a lot of things like that in C that can be a little bit annoying. This one can be particularly annoying, so I wanted to make sure I showed you that. All right, so I hope you enjoyed this course on C programming for beginners. Please subscribe to our YouTube channel where we post our free programming courses and tutorials, and check out our website, portfoliocourses.com, where we host our paid courses to help you create projects for a portfolio that will impress employers, including C programming projects.